So this is a review of an entire differential equation course in the undergraduate level. So this is the part one of that. So we can start with the basics. So what we mean by a differential equation? An equation with at least one derivative, with at least one derivative, is called a differential equation. Is called a differential equation. It's called a differential equation. For example, so these are two differential equations. So dy over dx. Here x is the independent variable plus x equal y. So y is the dependent variable. So x is the independent variable so that is normally what is in the denominator. And then y is the dependent variable. Y is the dependent variable. So when you have a ordinary differential equation, there's only one independent variable. If there are more than one independent variable, we call it a partial differential equation. We can talk about that later, but that's not the topic of this course. Good. So another example. So for example, this one, 3 d squared y over dx squared plus 5 dy over dx minus y equal 3. So this is another differential equation because there's a second derivative and the first derivative, and then this is an equation, so it's a differential equation. Okay, and then the next thing is what we mean by an initial value problem. So the next one is initial value problem. So in short, we call this is IVP. So when you see IVP, that means initial value problem. So what's the initial value problem? Initial value problem means a differential equation and a initial condition. So initial value problem means a differential equation plus initial condition. So if you are given these two information and ask you to solve the problem, we call it an initial value problem. So initial value, it can be more than one value depending on the order of the differential equation. If it is first order, one initial condition. So let's write that. So if it is first order, we need one initial condition. And if it is second order, we need two initial conditions. So initial means it given at the starting point. So for example, let's say there's a system that can start at t equals 0. So if the information given at t equals 0, we call it the initial condition. So normally like it looks like y0 or x0 if x is the dependent variable. And then there's another type of problem, what we call boundary value problem. So what happened, it can give you values not just at the beginning but some other point. So just write it just for completeness. So what we call boundary value problem. Boundary value problem. In this course actually we did both. So it's called BVP, boundary value problem. So it's a BVP. That means so you can see the conditions not just at 0 but at some other point, like maybe like t equal b or something. So you can say, for example, y b equal something, like why not. So that is what we call a boundary value, boundary condition. So initial condition looks like y0 equal something like a y1. Yeah, that's not really the right notation, but yeah, something like that. So if that is the case, so if you get a boundary value, then we call it a boundary value problem. If you get initial value, we call it an initial value problem, like that. And then depending on the degree of the degree of the differential equation, you need to give that many conditions all together. So if it is first order, you need only one condition. If it's second order, you need, I should say, at least two conditions, but two is like, yeah, two is the minimum. So if the nth order differential equation, you need n many conditions. Okay, so that's throughout the course. We're gonna use that fact. Good. Now let's focus on the topics. So we're gonna go one by one, and these can reflect the lectures. So in the description, you're gonna see link to the entire lecture, so part by part. So that means if you have some trouble understanding certain topics, you can refer the lecture. Okay, so let's start with the first topic. So we're gonna go with what we call the first one. What we did was like a verifying solutions. So let's start with that. So the first topic is we're gonna do verifying solutions. Verifying solutions. So what happened here? We are not going to find the solution. You are given some expression, and you're gonna check whether that is a solution. So that's the idea. And we're going to solve the problem later. So let's look at a problem like this. An example like that. So let's say verify that. So remember, we are not say find, we say verify. So the solution is given. Okay, so it's a different problem. We are not going to find it. We just verify. So we need to understand the wording here. Verify that x equal c1 e to the minus 3t plus c2 e to the 2t is a solution of x double prime plus x prime minus 6x equals 0. So first verify that that's a solution. So what we normally do is we take the derivatives and plug into the left side and simplify and show that you get 0. That means it satisfies the differential equation. That means that is a solution. So what you did was we verify. We did not find it. Actually, we know how to find this one later when you talk about second order constant coefficient differential equation, but that's not the point here. We just verify that that's a solution. Okay? Because sometimes we can guess. So that's the point. Especially when there are very difficult problems. Okay, so find, and then we can say find C1 and C2 such that normally we put s dot t dot, but right now this is the first time here, so I'm write such that, but later it's be s dot t dot. Okay, such that x0 equals 0 and x prime 0 equal negative 10. It can be just some numbers. It doesn't really matter how we do it. But let's see how we can do this. Okay, so the answer, let xt is a, I'm going to exaggerate, that is a function of t. C1 e to the negative 3t plus C2 e to the 2t. So we're going to use that. And then what we can do, taking derivatives. So taking derivatives, we have x prime t equal. So when you take the derivatives, the e function, what happened? So let's recall the results from Calc 1. If you take a derivative of an exponential function with the constant here, what's going to happen? The constant come out and nothing happens to the rest of the function. So that's the result. So k e k t. So k has to be a constant. Okay, if not, then you have to use the chain rule. Okay, so we can use that fact here. So that means the negative 3 c1 e to the negative 3t plus the same thing 2 going to come out. So e to the 2t. We need the second derivative as well. So let's find the second derivative as well. So the second derivative is we multiply by another negative 3, that means become 9 c1 e to the negative 3t, no change, plus this becomes 4 c2 e to the 4t. Oh, see, we can make mistakes very easily, so be careful. This is 2t, no change. Good. So now what we're gonna do is we're gonna substitute. So we simply substitute that this in the differential equation. So by substituting into the equation, so what we can do, we can start with one side, okay, into the equation x double prime plus x prime minus 6x equals 0. What we can do, we can start with the left side and see what's going to happen. So let's start with the left side. So x double prime plus x prime minus 6x equal, so let's start with x double prime, which is 9c1 e to the minus 3t plus 4c2 e 3t, that's x double prime, and x prime, which is negative 3c1 e to the negative 3t plus 2c2 e 2t, that's the x prime, and then minus 6x. So that means you have to multiply x with a minus sign. So that means a minus. So let's multiply by minus 6. So it's minus 6c1 e to the negative 3t and then minus 6 c2 e to the 2t. Now what we can do, we're going to see whether you're going to get 0. So let's see. So let's go with e to the negative 3t terms. If you look at e to the negative 3t terms, we have 9 here. We have 9 and we have negative 3 and we have negative 6, and you can see that when you add them, they cancel out. So those three cancel out. Now, so that's gone. And now, actually there's a small mistake. So this has to be 2. Good. Now let's look at the 2t terms. So if you look at the 2t terms, and you can see that we have 4, we have 2, and we have negative 6, and you can see that they all get cancelled out. So that's also cancelled out, but I'm going to cancel it in the other direction so that you know what you did. So don't just cancel in the same direction. One you cancel this positive way, other one cancel negative way, you know, with the slope. So then you know what you did. So that means they all cancel out. So you simply get 0. So it simply cancel out and you get 0. That means your expression is actually a solution of the differential equation. So we can write that. So therefore, so you can say that, therefore, that's how you're going to complete the argument. So therefore, like we're doing mathematics means we are making a logical argument. So it's an argument. So like you show the reasons and say the conclusion, the reason and the conclusion. So it's like that. So it's a nice argument. Okay. So let's try to do it like that. It's like much better if you want to do that. Like, okay. So therefore, x equal c1 e to the minus 3t plus c2 e to t is a solution of the differential equation of x double prime plus x prime minus 6x equal 0. So we prove that yes, it's a solution. Now what we can do, now we can use the initial conditions to find c1, c2. So using initial conditions, so we have x0, which is what you do is you plug in to the independent variable, you plug in 0. So that means x0. So wherever you see t, plug in 0. So c1 e to the negative 3 0 plus C2 e to the 2 times 0. So that means we know that e to the 0 is 1. So we know that fact. We know that e to the 0 is 1. So we can use that fact, and then that means you simply get C1 plus C2. But we know that from the condition, it is simply 0. It's given that x0 equal 0. So we use that condition here. Okay. So this is given. This equal to 0 is given. Now, what else we need is we're going to use derivative condition. So we know that x prime 0, which is negative 3 c1 e to the negative 3 0 plus 2 times c2 e to the 2 0. Now again the same argument, so you're going to get negative 3 c1 plus 2 c2, but we know that it's given that this is equals to negative 10. Again, this is given. Okay, so it's not our choice, it's given. Okay, now the goal is to solve these two equations. Okay, so so we have these two equations, c1 plus c2 equals 0, negative 3 c1 plus 2 c2 equal negative 10. Now I'm going to call these two equations are 1 and 2 because it's going to make it easy. So maybe you learn how to solve these equations when you were in high school or middle school. So there are two methods to solve. One is you're going to solve for one and substitute that in the other one. I do not recommend that method because that's long, pretty long for these kind of things. We are not going to do that. What we're going to do, we're going to try to get matching coefficients because that's much faster. And there's a video just to learn like how to solve these kind of equations, and you can learn more about that if you want to watch that, and even like how to go for 2, 3 like that. So we can use that technique here, the matching coefficients technique. So what's the matching coefficients? What we're going to do, and you can see that especially when you see positive and negative, we try to go for that. It's much quicker. So you can see that in the bottom equations, you're going to see negative 3 here. So what you're going to do in the first one also, you try to get a 3 but with opposite sign. So for example, you try to get 3c1. So if you get 3c1 in the top one, now what we can do, we're going to simply add them. Once you add them, you can see that c1 term going to cancel out. So you simply get c2. So that is the fastest way to solve this one. So that's what we're going to do, what we call matching coefficient technique. Okay, so what we're going to do, by 3 times the first one plus the second one. If you do that, because if you multiply by 3, you get 3c1 plus 3c2. When you add c1 get cancelled, you simply get 3c2 plus 2c2 equal negative 10. And then this says that 5c2 equal negative 10. Now what we can do, we can divide both sides by 5, so you get negative 2. So you can see it's very easily. Okay, you get the answer. And then what we can do, you're going to pick one of the equations by, but the first one is easy. So by 1, you can see that C1 is simply negative C2. So just plug in the C2 value here. So it is negative 2. That means 2. You don't want to show all these steps, but since this is the first example of this type, I'm showing all these steps, but later we can ignore some of them, some obvious steps. So we're done. Now you're going to complete that. So someone make an order, so you're going to preserve your results in the best possible way. Okay, that's how you're trying to do. That's why we're writing all those words, okay, to make a good argument. So therefore we can say the solution to the initial value problem, to the initial value problem is we can write that xt which is equals to 2e negative 3t minus 2e 2t. So that is the final answer for that problem. So what you can see that, you know, if you to do this, it doesn't take much time. So it's like maximum it would take like 10 minutes to do all of this. But I'm doing it slowly just to explain everything. But you know, when you want to do that in exam or something, you don't want to, like, we don't explain, like, I mean, we explain, but not like we are not going to take too much time. We just write it fast. Okay, so it won't take too much time. You can see, you can practice and see how long it takes for a problem like that. Okay, good. So that's the first problem. And if you need more, you can look at the first video about that to find more information and what else we did. Okay, good. So let's go to the next topic. So the next topic is what we call the four fundamental equations. So we talk about four fundamental models. So let's talk about that. Four fundamental model equations. Four fundamental model equations. So we talk about four models. And why we did that? Because we know that these models like appear pretty much everywhere in sciences. So it's good to know those four separately. Okay. So the first one, what we did was the exponential growth model. So exponential growth. So that's pretty much everywhere. It's like, you know, bacteria, even like these days COVID, all of them follow the exponential growth model. And then, so the differential equation is dy over dt. We can use the t as the independent variable because the time is it's like kind of makes sense. So k is a constant. We assume k is positive. So, and then we know that the solution of this one is we can write as yt equal a constant times e to the kt. So that's the solution, and you can remember, you can use this. And you know that even we can solve this very easily. This is like a separable differential equations, or we can even use a simple calc 1 technique to solve this one. Okay, it's not a difficult problem. Okay, so now if you look at the solutions for the graph of this one, so what is the graph of this? This is exponential growth. That means you can start at a value and then it's going to grow. So this is what we call the exponential growth model. That's the starting value a, okay, and then it's going to grow. So we assume that k is positive, is a growth. Okay, that's the first case. And then we talk about the what we call exponential decay. So exponential decay. Exponential decay model. So as exponential decay is very similar, dy over dt, and then we assume that k is positive but with a negative sign in front like that. So it's pretty much similar. What's going to happen? There's a negative sign in front, so the e negative kt. So that's what happened. And so if you look at the graph, very similar. But what's going to happen now is it's going to decay. So you can start with a value and go down. So so like that. You can see start with the value a and then go down. So you can see this is exponential decay, and we assume that k is positive again because we put a negative sign in the equation. So that's what we call exponential decay. Especially like if you look at radioactive material, it's going to follow this kind of pattern. There are a lot of other things like even bacteria. If you kind of put like a disinfection there, and those bacteria are going to kill, and then if you look now, if you try to count, so it's going to follow something like that. So these models are everywhere. Like, you know, if you get an injection, what's going to happen? So those are the kind of models for that. So it's very common situation. It's called exponential decay. And then we talk about the next most common one is what we call the simple harmonic motion. So simple harmonic motion. Sometimes we call SHM. Okay, simple harmonic motion. So what is the differential equation? So there's a slight difference now. This can be a second order differential equation. We have like d squared, and then we're going to use a time variable. Let's say time equal. So we can write negative. There's a negative sign, and a k squared y. So remember earlier you had a t. Now this is y. So that's the major difference here. That's the dependent variable comes here. And then we know the solution. So the solution is with sine cosine. So some number, and then we have cosine kt. So k is the square root of that term. So you see, you have to take the square root of that. And then another constant, sine. So one cosine. It doesn't matter which one we write first. So like that. So that is the solution. So it's a sine cosine. You know the sine cosine are periodic functions. So that means if you look at the graph, it has a graph like this. So it's going to be periodic and it's going to fluctuate. It start with some value depending on the initial condition, and it's going to go in a sine curve or cosine curve because it's a mixture of that. So yeah, so that's what happened. So this is what we call a simple harmonic motion. This is everywhere, like all the atoms in the body follow these kind of motions, and if you have a mass and a spring, it's gonna follow these kind of patterns. So this is like kind of very common. So it's called the simple harmonic motion. And then the fourth one, what we normally call the hybrid model. So we have a hybrid model. What's a hybrid model is we have the exponential growth and the exponential decay. You can combine them into one. That's a hybrid model, and you can see the interesting relation. It is simply the same equation we just write above, but with the plus sign. So that's very interesting. What happened? There's no t here. It's the plus sign, the above one, but with the plus sign, we still put the k squared. So what's going to happen? We can write the solution of this one in two different ways. The one way is using the hyperbolic cosine and hyperbolic sine function. So cos kt plus sin kt. We put h to mean that it's a hyperbolic functions. And then if you are not familiar with that, you can look at the video for that. We explain that, and we also talk about some other properties. For example, derivative. One of the major thing is that when you take the derivative, cos becomes sin and sin becomes cos. There are no negative signs. It's one of the major difference between the regular sign and cosine. Also, you can write this solution in different way. I'm going to still use AB, but those are not simple AB, some other constants. But I'm still going to say AB. So A e to the, we can write one of them, let's say KT. Now it's a KT, and then plus B e to the negative KT. That's why we call the hybrid model. This is the exponential growth model, and that's the exponential decay model. So you add the two and you get the hybrid model. So that's the hybrid model for when you have that difference equation, that's hybrid. So those are the four fundamental model equations. And if you look at the graph, so you're gonna get like graphs like this. So I'm gonna put both together. So you can get a graph like that. So because it's a part sine, part e to the kt, part e to the minus kt. So whoever the win gonna get the formula. So it's gonna be like that, or like, you know, it can be like that. Okay, because we know that if you hang a wire, heavy wire, it's gonna go in a equation like that. So it's like in many situations, and yeah, good. Now let's try to see how to solve a problem using these models. So the goal is, if you see one of them, you can directly write the solution. Okay, because these are familiar one. Remember this is very useful for your other courses, so you can directly use the results. So let's look at a problem. So let's solve this problem. So we have, let's say, solve the initial value problem, d squared x over dt squared equal minus 4x, along with x0 equal, let's say, 12, x prime 0 equals 0. Why we need two conditions? Because this is a second order differential equation, so you need two conditions. Now what we can do, we're going to match this equation with one of those four models, and you can see that this is the simple harmonic motion situation. And you can see that in this problem, k squared equal 4. This implies k equal 2 because we consider only the positive value. Now we can write the general solution. So the general solution is, so the general solution is, you can say xt equals, you can directly write it. It is a cos 2t, where 2 is t is the independent variables. You have to be careful. So the independent variable goes there. Okay, and then also this x and this has to be x, otherwise it is not this type of problem. Good. And then so we have plus b sine 2t. So we have that. So that's it's directly come from the four model equations. Now what we can do, we can use the initial conditions, but we can see that when you want to use the initial conditions, there's a prime. So that means let's take the derivative first. So taking derivative, so we can write x prime t equal, so what's the derivative of this one? It's a cosine. So derivative means the negative sign, but there's a 2 here. That means by the chain rule that 2 comes out. So that's going to be negative 2a sine 2t plus. Same thing, sine, when you take the derivative, it's going to be cosine. So it's going to be 2b cosine 2t by the chain rule. Now we can use the initial conditions. So using initial conditions, we have x0, that means plug in 0 for the t. So you're going to get a cosine 0 plus b sine 0, which is equals to 12. This is given. Now we know that cosine 0 equals to 1, sine 0 equals to 0. So because of that, this simply implies that a times 1, that means a, plus 0 equal 12, that means a equal 12. So we find one value. Now using the other condition, we know that x prime 0, which is equals to the second one, so negative 2a, you can actually put the value here. So it is, we already know the value, so I'll put the value here just to make the calculation easier. So 12 sine 0 plus 2b cosine 0, which is equal to 0. So again, we know that the sine 0 equals 0, cosine 0 equals to 1. So that means this says that, so nothing comes from the first term. So this says that 2b equals 0. So this says that b equals 0. That means the b term is going to go away. That means therefore the solution is, therefore the solution to the initial value problem is simply xt equal 12 cosine 2t. So that's the solution of the problem. Good. So let's go to the next topic. So what's the next topic? So what we're going to do, we're going to talk about the classification of differential equations. So number 3, the classification of differential equations. Classification of differential equations. So we talk about various types. So we first start with what we mean by an ordinary differential equation. Ordinary differential equation. So we normally call this ODE. In this one, what we have, one independent variable, variable. So we have one independent variable. So an example would be something like this: dx over dt r plus 3x equal t plus 1. You can see the independent variable is t, and thus there are no more independent variables. So these are ordinary differential equations, ODE. And then the next type is what we call the partial differential equation. So we have partial differential equations, partial differential equation, or we call this is a PDE. That's a shortened form for that, PDE, partial differential equations. So what we have, more than one independent variable. More than one independent variable. So there are more than one independent variable. Sometimes the space and time, those are the two common independent variables. So so such a differential equation have a kind of form like this. So we can write, let's say u is a function of x and y. So then we can write it like this. So if u is a function of x and y, if u is a function of x and y, so that u is a function of x and y. So that's how we write it. So then you can write a differential equation like this. We can say we can use the DABA for that. So DABA u over DABA x plus 3 times DABA u over DABA t equal, we can say, x plus t. So this is a partial differential equation, and you can see that there are two independent variables, space and time. So x and t are independent variables, but that is a different course, and we are not going to focus that in this course. This is only for partial differential. This is only for ordinary differential equations, except in few cases, because we need the idea of partial differential equation in certain situations, and other than that we are not going to focus on that. Okay, that's about that. So there are two independent variables in this. So these are the independent variables. Independent. Okay, so there are two. In the first one you only have one. Okay, and then we talk about what we mean by a order of a differential equation. So that's the next topic we talk about, the order of a differential equation. So order means the highest derivative appear. Highest derivative is what we call the order. So for example, if you look at this differential equation, d squared y over dx squared plus x equal 3. So you can see the highest derivative appear is 2. So we call this is a second order differential equation. We don't say 2 order. So we say this is a second order ODE. Second order ODE. Good. That's the highest derivative appear. The question, why you do that? Because you know that depending on the order, we had to use different techniques. So that's the major point here. So the next important topic is what we mean by linear and non-linear equations. So the next one is number 4, linear and non-linear. So linear versus non-linear. So that means linear means no powers other than one of the dependent variable. So you're going to see no powers other than one. Other than one of the dependent variable. So we don't worry about the independent variable. So there can be only powers of one. So that means there are no products. Okay. So in other words, no products. No products of the dependent variable or its derivatives. So let's talk about two examples. If you say x is the dependent variable, So we can write dx over dt plus t cube x equal t. So you can see that there are no powers of x other than 1. So this is a linear equation. T3, t is the independent variable, that's okay. So this is linear. And if you look at this one, x times dx over dt plus the same thing here, t3x equal t, this is non-linear. So those two equations make a big difference when you try to solve. Linear equations are easy to solve. Linear equations are easy to solve. So that's the fact. Linear equations are easy to solve. Good. So these are linear, non-linear. Good. And then talk about what we mean by the constant coefficient. So number 5, constant coefficient. Constant coefficient. Constant coefficient equations. So that means all the constants are coefficient. All the constants, all the coefficients. Oh, I'm sorry. All the coefficients are constants. Okay, all the coefficients are constants. So for example, 5x double prime minus 3x prime plus x equals 0. So this is a constant coefficient differential equation. You can see that all the coefficients are just numbers. What we normally do is we consider a characteristic equation to solve. Okay, so so use characteristic equation. Use characteristic equation to solve. Which remember which is in lambda. So we write a lambda equation. Good. And there's a characteristic equation for matrices as well. But here we call the characteristic equation for that because that can characterize the differential equation. Okay, that's a constant coefficient. And then let's talk about homogeneous versus non-homogeneous. So the next one, so we have homogeneous versus non-homogeneous. So be careful, the homogeneous and non-homogeneous has a two different meaning in differential equations. And then we can talk about the homogeneous and non-homogeneous again later. So here, what we mean by the homogeneous is whether the differential equation equal to 0 or not. So like it will be easier from an example. So for example, if you have 5x double prime minus 3x prime plus x equals 0, you see that? So you can see that. So you're gonna set the differential equation to 0. That means that side is not a function of the independent variable. So all the dependent variable you can put it to one side, and then you can see that. So we can write this one as a this is what we call a homogeneous equation. So homogeneous equation. So no functions of the independent variable. Okay, so it's a homogeneous equation. Now you can say 5x double prime minus 3x prime plus x equal t. This is non-homogeneous because it's a function of the independent variable. Okay, so if you have a function in the, because you can always pull all the dependent variable terms to one side, and then if you see a function of the independent variable alone, that's going to be non-homogeneous. Okay, you see a function of the independent variable alone. A 0 we just say other than 0. Okay, because 0 is also a function, but other than 0. So this is what we call non-homogeneous because of that t term. So this is non-homogeneous. Good. homogeneous and non-homogeneous. So there's a function of the independent variable alone. Okay, so that means let's write that. So there is a function of the independent variable only. Independent variable only. Okay, so if you see a function of independent variable only, it is what we call non-homogeneous. Good. And then we have what we call autonomous differential equations. So what's autonomous means, if the differential equation does not depend on the independent variable, we call it as an autonomous differential equation. The differential equation does not depend on the independent variable. Okay, if the differential does not depend on the independent variable, we call it as a autonomous differential equations. Let's write this one. So you can say dx over dt plus x squared equal 3. So you can see that this does not depend on the t variable, so this is autonomous one. Okay, so this is autonomous. So if you had like a function of t somewhere, so it is non-autonomous. It's autonomous one. Okay, and then the last topic of this is what we call system of ODEs. System of ODEs. So a system of ODE, so not just one equation, but there are many equations. So like for example, x prime equal 2y plus e to the t, y prime equal, let's say, 3x plus y sine t. So this is what we call a system of ODE. So we discuss all of these types. Good. So that's about that. So I don't discuss any further examples of this one, but if you need more examples, you can look at the corresponding lecture for that. But this is the kind of basic ideas we talk about. Let's go to the next topic. So the next one is what we call the basic integration. So number 4, basic integration. Basic integration. So this is the very simple thing that we did even this one in Calc 1. So there are two types. So let's go with the type 1. So what's the type 1? You have a differential equation which is just on the right side, it is just a function of the independent variable. So this is a function of the independent variable. So this is a function of the independent variable only. Independent variable. So if this is a function of independent variable, things are very easy. Just integrate the two sides. So that means y is simply the derivative of y is simply the integral of the derivative. Okay, we're just gonna integrate with respect to x so that they cancel each other. So that means simply become the integral of fx dx. So it's very simple, just integrate. That's gonna happen if the derivative is a function of the independent variable only. So this is the easiest case. You can simply integrate that. You gotta be careful because sometimes it's not the case. Okay, so let's talk about type 2. So what's the type 2 is, so type 2, we have dy over dx, but it is a function of the dependent variable now. Okay, so if you get the function of the dependent variable, so let's write. So what happened now is a function of the dependent variable. So what we can do in this case, we can flip the equation over. So we can write this one as dx over dy 1 over gy. Now you can see that this came back to the previous case, because you can simply consider y as the dependent variable in this case. So we can see consider y as the independent variable. So that's the whole point. And then just integrate the two sides again with respect to y now. So that means you're going to get x, which is the integral of dx over dy with respect to y, not x, integral of gy dy. So that's what's going to happen in that case. You're going to integrate with respect to y. Okay, those are the first type, what we call the basic integration. So you can just use a table of integrals for that, the common ones, and you can do a lot of problems just using these two equations. So the first case is the derivative is a function of the independent variable. Second one is a derivative of the function of the dependent variable. In the second case, we're going to flip the equation over and integrate. So let's do two examples from those two types. So we have this first example. So let's say solve the initial value problem. Let's say dy over dx equal 3 cosine x, 3 cosine, let's say 2x, minus 8 e to the negative 4x plus 5 along with y0 equal negative 3, something like that. And what you notice? You notice that this is the independent variable. This is the independent variable, and you can see that it's only a function of the independent variable. So that means this is the case 1. That means you can simply integrate the two sides. Okay, so you can see the function of, so this is a function of x. Okay, x is the independent variable. So that means we can integrate. So by integrating, just integrate. Okay, by integrating y equal just the integral. So it is 3 cosine 2x minus 8 e to the negative 4x plus 5 dx. So this is just very basic integrals, and if you forget, so these are the kind of formula that we're going to use here. So if we have e to the kx dx, the answer is simply 1 over k e to the kx plus c. This only works when k is a constant. And the second one, if we have a cosine kx dx, and we know that it is simply 1 over k sine kx, so just divide by k. And the other one, if you have a sine kx, k has to be a constant, so this is simply negative 1 over k cosine kx plus c. So those are the kind of three common ones, and then also we have the power rule that everyone know. And so this is what we're going to use now. So that means in this case k equal 2, so simply divide by 2 is a cosine, that means it's a sine one. So divide by 2, so that means it's going to be 3 halves sine 2x minus, you can see 8, you have to divide by negative 4 e to the negative kx plus 5 is a constant, so it's a 5x plus c. So that's what you get. And you can simplify this a little bit, so you're going to get 3 halves sine 2x. Simplify, you get 2 e to the negative this k actually 2, k actually 4, so you get 4, so e to the 4x plus 5x plus c. Now what we can do is we can use the initial condition. So using the initial condition, y0 equal -3. You can see that -3 equal y0. That means wherever you see the independent variable, plug in 0. So you're going to get 3 halves sine 0, which is 0, plus 2e to the 0, which is 1, plus 0 plus c. So you can see that this is 0 and this is 1. So this tells you that -3 equal 2 plus c. So in other words, c equal -5. So you can plug in that. So that means the solution is simply y equal 3 halves sine 2x plus 2 e to the 4x plus 5x minus 5. So that's the solution. So you can see that it's not difficult. We just use the basic integration technique because the right side is just a function of the independent variable. Now let's look at the other type. So what's the other one? This example. So we have, let's say, solve the IVP, the initial value problem, dy over dx equal y plus 3 along with y1 equal -2, something like that. So if you see an equation like that, now what we can do, you can see this is a function of the dependent variable. So this is a function of the dependent variable. So when you see function of dependent variable, what you do, you're going to flip this over. Also, you can do this problem using the separation of variable. Actually, that's a separation of variable, but you can see as a technique, you can remember like that. So we're going to flip this over. So we can write this on dx over dy equal 1 over y plus 3. Now what we can do? Integrate with respect to y. So integrate with respect to y now. So if you do that, you get x here, and it's simply the integral of 1 over y plus 3 dy. So you can see that's the 1 over y plus 3. 3 is just a constant, so this is a log function. So this simply becomes natural log y plus 3. We are not going to use the substitution here. That's like long time ago. Okay. So we have the solution now. So what we're going to do is we can find the constant, and then so I mean there are two ways to do it. First we can solve for y and then plug in the constant, or we can find the constant and then we can solve. So let's do that. So we know the constant. So what it says that, so using the initial condition. Okay, so there are two ways to do it. Either you can use the condition now and then go for the solve for y, or solve for y and then find the constant. So it work both ways, but be careful what you get. Okay, because sometimes when you try to write the log form with the exponential form, remember you get plus or minus, so you have to be careful with that, whether that is the case. So let's solve for y first. So what we're going to do now is you can write this one as ln y plus 3 equal x minus c. So this says that y plus 3, we have solved many problems like that. So you can see that this is absolute sign. So that means you're going to get the plus or minus here. So we have it's a plus or minus. You can see e to the x minus c. So so now what we can do, we can write this one as e to the like plus or minus e to the minus c, and then e to the x. What I'm going to do, I'm going to call this whole thing just a c. So if you do that, or some other letter if you want, just what we normally call the by abyssal notation, I'm going to call this whole thing just c. It's not the same c, but another one. Okay, like that. So we can write it like that. So in other words, y equal c e x minus 3. Now we're going to use the initial condition. So using the initial condition, we know that for the initial condition, it's a negative 2 when you plug in x equal 1. So let's do that. So that means negative 2, y equal negative 2 equals c e negative 1, negative 3. And then we can, what we need to do is we need to solve for c. So let's do that. To do that, first we're going to move the number to the other side. That means we're going to add 3 to the both sides. So this says that 1 equal c e negative 1. In other words, if you multiply both sides by e, it says that c equal e. So if you plug in c equal e, what's going to happen? Y equal e times e to the x minus 3. Okay. So and then you can combine them because e means e to the 1. So if you combine that, so you're going to get y equal e x plus 1 minus 3. So that is the solution. Yeah, I see that there's a small typo here because we plug in negative 1. It's not negative, it's positive. So that means there's no negative sign. So that means this is going to be e to the negative 1. So that means this is negative 1. So that means the final answer, this is minus 1. Good. So that is the solution of the differential equation. And you can see that that's not that difficult, but there's a process that we need to remember. Good. So let's move on. So let's talk about the next major type. So what is the what we call the separable differential equations? So number 5, a separable differential equation. Separable differential equations. So what's the separable differential equation? So let's look at the differential equation. We have dy over dx, which is a function of x and y. But sometimes what happens, you will be able to separate them into, you will be able to write this fxy function as a product of function of x and y. So if you can write this one as a product of fx and y, we call it is a separable equation. So this is what we call a separable differential equation. If you can do that, we call it a separable differential equation. Separable differential equation, because you can separate them. Okay. And after we do that, what we can do, we can divide both sides by gy. So if you divide, you can write this one as dy over gy equal, on this side we have fx, we're going to multiply, we're going to bring dx to the other side. So we can separate y's and x terms, and then after that what we can do, we're going to separate, integrate them separately. So that is what we call the separable equation formula. Okay, so you're going to integrate them separately. Okay, very simple argument. We're going to first write as a product, and then we're going to move the gy to the other side by dividing, and then integrate the two sides separately. So let's look at some examples. So examples, so let's say solve dy over dx, doesn't look like x, dy over dx equal, let's say y minus 4xy, and then y0 equal, let's say e something. So when you get a problem like that, you're going to check whether you can write this as a product of x and y separately. So that's the first step. So the answer, and you can see that yes, you can write the right hand side. If you pull y out, you can see 1 minus 4x. You can see it's a product of x and y separately. So what we're going to do, we can divide this side by the y function, leave the x function on this side and then integrate with respect to x on that side, integrate with y on this side. So that's the major step. Now what we can do, we can integrate the two sides separately. First one with x, right, left side with y, right side with x. So you're gonna get ln absolute y here. This is just the power rule. So you're gonna get x minus, if you integrate x, you get x squared over 2. So that means you can 2x squared plus c. We are not going to add c1, c2. We only add 1c to one side because you can always simplify. Now we can write this one using the exponential form. So let's do that. So if you write them using the exponential form, I can do it here, then you can see all the work. So if you write the exponential form, so what's going to happen is y equal the same thing. We know that's absolute value, so you get plus or minus, and then you can just put one constant. So it's the same thing here. So it is so what happened is plus or minus, and then e to the x minus 2x squared plus c, and then what we can do, the plus or minus and then e to the c we can combine. So if you combine that, let's write that extra step. So if you combine that plus or minus e and the c, we're gonna combine. So that means I'm gonna call it a. So if you call that a, and then you're gonna get ex minus 2x squared. We have done this a lot. Okay, so that's plus or minus e to the c, you could just call a, and we still have e to the x minus 2x squared. Good. So that's the solution. Now what we can do, we can use the initial condition. So the using the initial condition that y0 equal e, so we're gonna get e equal a, e to the 0, e to the 0 means 1, so that means a, so a equal e, so that means y equal e to the 1, we have e x minus 2x squared. This means that's e to the x minus 2x squared plus 1. So that is the complete solution. It's not difficult. Okay, first we find the general solution. That's the general solution, and then we use the initial condition to find the constant. Good. Let's just do one more example. This is very important topic. So how about this example? So the next example, let's say solve x dx over dt equal 3e to the t minus x, something like that. So let's try to find the general solution of this one. So what is the independent variable? Independent variable is t. You can always switch, flip it, and then change that. So it doesn't matter. At the end, you're gonna get the solution. Okay. So the answer. So what we're gonna do? We're gonna use certain algebra here. So we write dx over dt. We can write this one as 3 e to the t times e to the negative x. So we can do that. Now what we can do, we can see whether we can move x terms to one side, t terms to the other side. Actually, you can see that yes, we can do it. If you multiply both sides by e to the x, you're gonna get x e to the x dx, and then I'm gonna leave 3 here. I leave et here, and then dt I'm gonna move to the other side. So that we can do. So you can see it is a separable equation now. So we can integrate the two sides separately. Right side is okay. How do the left side? For the left side, you have to use the integration by parts. Okay, so we're gonna make the table. So we're gonna pick u equal x. You can use the shortcut. You can use the di method. I'm going to just use this regular method. Okay, just to make sure that. Okay, so dx dv. So if you are trying to use the shortcut method, the di method, make sure that you practice that first. Okay, so DI method, and there's a video and that kind of solve many problems there, so you can practice using that. Okay, and then we take the derivative here, so the du equal dx, integrate, so you get ex, and then what is the integration by parts formula? It is udv is simply equals to uv minus vdu, so that is the integration by parts formula, so we can use that. So by the integration by parts formula, on this side you simply get uv, that means x ex minus vdu. V means ex, du means dx, equal, here 3e to the t plus c, we add only c one side, and then we can finish the integral here, so we get x ex minus ex equal 3et plus c. So the question is, can you solve this for x? X is the dependent variable. Can you? Because of that x term, we cannot. Because there's no way you can pull the x term out. Because when you have sine, cosine, exponential, log, like that, there's no way you can pull the x term out when you have a product like that. It's a nonlinear. Okay, so this makes it nonlinear. So we cannot. So we can leave it like that. So this is the implicit solution. So this is the implicit solution. So implicit solution of x. And if you have initial conditions, what you can do is you can plug in them and then solve for c. But otherwise, you just have to leave it like that because there's no way you can solve this. But that's the implicit solution for the x function. Very good. Okay, so let's talk about the next important type. That is the first order linear differential equations, and we're gonna use the integrating factors method. That's the next major topic. Okay, you always have questions in the exams. Good. So let's talk about that now. So the next topic, this is number 6. So this is first order linear differential equations. You have to remember like that, first order linear. So we use the integrating factor method. Integrating factor method. So let's talk about the let's recall what we did. So we write what we call the standard form. So it has to be of this form. If it is not, you have to bring it to this form before we do anything. And then dy over dx plus pxy equal qx. So that's the kind of format for the first order linear. This is what we call the standard form. Standard form. And then, so if it is not in the standard form, you have to bring it to the standard form first. Okay. So if not, bring it to standard form. That's the first step. Bring it into the standard form. And if you don't do that, your answer is wrong. Okay, so it's very careful with that. You have to bring it to the standard form. Good. So let's talk about the steps. So what are the steps of such a problem? So the first step is, so we assume that it's in the standard form. Okay, that's the standard form. So we assume this is the case. Now what we're gonna do, we're gonna find what we call the integrating factor. Okay, so find the integrating factor I, which is always e to the px dx. P means everything. You're gonna with the sign. So we're gonna calculate that. After that, what we're gonna do, we're gonna multiply. We're gonna multiply the whole equation by that. So we can write I x times the dy dx plus px ix times y on the other side we have qx times I. Now the magic happened. What's the magic? You can see that on the left side, this is automatically the product rule for the product y and I. So we can write the form. That's what we normally call the form. So what the form here is automatically this side becomes the product of y and I. That's automatic. That's the product rule. If you apply the product rule, that's what you get. And on the other side, now we have qx and I. Now what we're going to do, to remove the derivative, we can integrate both sides. So we can integrate. And once we integrate, what's going to happen? You get yi term on this side. This is just the integral qx ix. So you can see this is a function of x. It may or may not be able to integrate. If you cannot, we leave the with the integral sign dx, and we can exaggerate the plus sign. Now what we can do, we need to solve for y, so you divide by I. So that means y is simply, you're going to divide by I term. So you're going to get the bracket. So we have, inside that we have qx ix dx plus c. So those are the steps. So let's try to, don't remember this as a formula. That's because it's much easier to follow the steps and get this quickly. That's exactly the whole point of learning these things. Okay, plugging to equations, anybody can do that. So it'd be better to like kind of follow the steps and get that. Good. So let's do maybe 2 examples from the topic. This is very important. So I'm going to do 2 examples. The first example. So example number 1. So let's say we have dy over dx minus 3y equal e to the 3x sine 4x y 0 equal negative 1/4. So the answer, so you can see that this is a first order linear differential equation in the right form. Okay, so this is first order linear equation. So that means we're gonna use the, you can see that this is not separable equation. You cannot separate x and y. So we can use the integrating factor method. So let's go step by step. So we're gonna find the integrating factor. Integrating factor. So we're gonna say I, which is e to the px dx. So let's plug in here e to the, what is the px? You can see px is with the sign negative 3. That's the p. So it is negative 3 dx. Negative 3 you can pull out. So that means it's going to be e to the negative 3x. We are not going to add the c. Because we are looking for one solution, not all the solutions. Now what we can do, we can multiply. So you can multiply the whole equation by that. So it is e to the negative 3x dy over dx minus, we have 3 e to the negative 3x y equal, what we get on the other side? It is e to the negative 3x e to the 3x sine 4x. You can see it simplifies very well. Okay, so that means if you simplify it properly, it can work very well. So you're going to get sine 4x. Okay, that's the gift you get if you did that right. It simplifies very well. Good. Now we know that this is automatically, this side is, so we can write the form. So this is automatically the derivative of the y and the integrating factor. So that is automatic thing. On the other side we have sine 4x. To remove the derivative, we can integrate. So integrate with respect to x. X is the independent variable, so that's going to cancel out. So you simply get y e to the negative 3x, the integral of sine 4x dx. This is very easy to integrate. K equal 4, so you can divide by that. This is sine, so it's a negative cosine. So this can be negative 1/4 cosine 4x plus c. Don't forget that. Now what we can do, we can multiply both sides by e to the 3x. So if you multiply by e to the 3x both sides, so you're going to get negative 1/4 e to the 3x. When you multiply by e to the 3x, is opposite sign. Okay. So negative 3, you multiply by positive 3. So that they're going to cancel on the left side. On the other side, you multiply by e to the 3x. So you're going to get that times cosine 4x plus c e to the 3x. So that is the solution. That's a general solution. Okay, so this is the general solution. Now what we're going to do, since we know the initial condition, let's plug in that and try to find c. Otherwise, this is the solution. So if I need to find general solution, we're done. Okay, so next step is we're going to use the initial condition to solve it. So using the initial condition, y0 equal negative 1/4, you're going to get negative 1/4, which is simply equals to y0. This is negative 1/4. Wherever you see x, put 0. So e to the 0 cosine 0 plus c e to the 0, which simplifies to negative 1/4, because we know that the cosine is 1, e is 1. This is also 1. So you're going to get negative 1/4 plus c. You can see negative plus 1/4, negative 1/4 get cancelled. So this says that c equals 0. So that means that term is gone. So you simply end up with y equal negative 1/4 e to the 3x cosine 4x as the solution to the initial value problem. Good. So let's try to solve one more of that, because this is very important. So I'm going to do one more. So then as the next example, let's try this. So the example, solve, let's say t dy over dt minus 2y t cube e to the negative 2t. Okay, good. Is this in the standard form? So that's the first question you want to ask. Okay, first question you want to ask whether this is separable. Okay, that's much easier. Actually, that's not the first question. First question is whether this is the basic integration problem. Is this like dy over dt equal a function of the independent variable only, or function of the dependent variable only? And you can see that no, it's none of them. So it's not basic. And then ask whether this is a separable differential equation. Can you separate the x term? Can you separate the y terms and t terms? And you can see that there's a sum, and also there's a multiplication. There's no common term, so this is not separable. And then we're going to go for the linear first order, the integrating factor method. So when you go to integrating factor method, you ask the question, is this in the standard form? And you can see that this is not in the standard form. So what you want to do? You have to bring it to standard form. So how to do that? You're going to divide by t. So because you don't need that term. So that's the only problem. So we're going to divide by that first. So let's do it. So we're going to divide the whole equation by t. So that's the first step to do. Okay, so we can write not in standard form, not in standard form, not in standard form. So divide by that t term. Once you do that, so you're gonna get dy going to get dy over dt minus 2 over ty equal, this becomes t squared e to the negative 2t. Okay, now this is standard form. Everything looks good. Now what are you going to do? Find the integrating factor. So let's do that. So the first thing we did, we divide. Okay, so find the integrating factor. So which is I equal e to the integral of pt, now pt dt. So it is e to the integral of pt, which is negative 2 over t. You have to pick the whole thing. Okay, dt. This is very easy to integrate. We normally do pull the negative t out. This is 1 over t dt. 1 over t means ln. That means e to the negative 2 ln t. We're going to bring this as a power. So that means we can write this one as e to the ln t negative 2. Now from algebra, this part get cancelled. Okay, so you're going to get t e to the negative 2, or in other words 1 over t squared. It doesn't matter which form you write. So that is the integrating factor. Now what we're going to do, we're going to multiply the equation, our standard form equation, using by the integrating factor. So let's do that. So when you do that, so we're going to multiply by 1 over t squared, the whole equation. So you're going to get 1 over t squared dy over dt minus, it's going to be t cubed now, y equal, what happened here? It is 1 over t squared. What you have here? You have t cubed e to the negative 2t. So you can see this get cancels very well. And then you have e to the negative 2t. So then we can write the form. So that this side is automatically become the, so we write the form. So this side automatically become d over dt y times the integrating factor. Other side is e to the negative 2t. We can integrate this now. If you integrate, you get y times 1 over t squared. This is the integral of e to the negative 2t dt. This is a very simple integral. You're going to divide by the constant. So that means it is negative 1/2 e to the negative 2t plus c. Now what we're going to do, we're going to multiply both sides by t squared. Okay, so multiply by t squared to cancel that. So we're going to get y equal, you're simply going to multiply by t squared, so you're going to get negative 1/2 t squared e to the negative 2t plus c t squared. So if you know the initial conditions, we can find c. Okay, so if the initial conditions are given, we can find c. So that's the idea of using the integrating factor method. So you can see that it's not that difficult, but there are certain steps that you need to follow. So here what we did was we multiply by 1 over t squared and we write the form, integrate and multiply again by t squared to isolate y. Good. So next we can talk about what we call the substitution methods. There are 3, so we're going to talk about one by one. So let's talk about the substitution methods. So there are 3 substitution methods, so we're going to do one by one the substitution methods. So we can talk about 3. So let's go with the first one, what we call the direct substitution. Direct substitution. So what's the direct substitution? It will be clear from an example. So what we normally do is let u equal what we call the inside function. Inside function. So we're going to put the inside function as u, and then we can write the differential equation using the new variable and rewrite the differential equation using the new variable. So let's see this in a problem. So how about this one? Let's say solve dy over dx equal y plus 4x minus 3 to the square, maybe something like that. So y0 equal 4. So let's look at this problem, and you can see that if you look at this differential equation, if you try to expand this one, you're going to get a lot of terms, and it will be very difficult to solve because there are y terms, y squared terms, xy products, and a lot of terms. And you can see that none of the method that we discussed doesn't work for that. So what we can do, we can use this substitution technique. So we can substitute for these inside functions. That's the inside function. So that's the starting point. So what we can do, so the answer, we're going to just the basic substitution. We're going to pick, so let's say let u equal the inside function, y plus 4x minus 3. So that's the starting point. We're going to pick that part, inside function. And then just take the derivative. So if you take the derivative, so taking derivative, we can write this one as y prime or dy by dx. So du by dx equal dy by dx on the other side plus 4, because 3 is a constant, negative, so it's going to go away. So that's what you get. And then what you can do is you can solve for dy by dx. So this says that dy by dx equal du by dx minus 4. So we're going to plug in that here. So if you plug in that, what will happen to the differential equation? So dy by dx you can replace by that. So it's going to be du over dx minus 4 equal, we're going to put the inside function as u, so it becomes u squared. So that means, so this says that du over dx is simply u squared plus 4, and you can see that this is a separable equation. This is separable, so we can just use the separation of variable method to continue. So we're going to solve for u first. After you solve for u, then you can use the substitution, to solve for y. Okay, just solve for y. Okay, so that's the idea. So let's finish the argument. So we have so what we have du over dx is equals to u squared plus 4. So we can move the u terms to one side, so we can write this one as du over u squared plus 4. The other side is simply dx. Now what we're going to do, we're going to integrate the two sides. So if you integrate on this side, this is simply going to be tan inverse u, because remember there's a formula. So what the formula says, if you integrate 1 over x squared plus a squared, so this is simply 1 over a tan inverse x over a. So that's the formula says, plus c, and that's what we can use here. So this is one of the formula. It's a direct formula, so we can use that. And also you can find all these formulas in another video. I put all the videos in one formula. in one video, so you can see like kind of all the common formulas. So you can check the Calc2 YouTube list for that. From that you can find it. Good, and I'll also put a link to in the description, so you can find that in the description of this video. Good. Okay, so that's what you get from the left side. From the right side, it is simply x plus c. That's what you get. So this means that if you take tan of both sides, so this says that u equal tan x plus c, and then what is u? U equal, now we're going to substitute back. Okay, so since u equal y plus 4x minus 3, you can put that here. 4x minus 3 equal tan x plus c. Now you can just solve for y. So you can see it's very simple. So y equal, if in the general solution, is 3 minus 4x plus tan x plus c. So that's the general solution. And if in the initial, if you want to solve the initial value problem, so you can use the initial condition. So the initial condition y0 equal 4 gives, so we plug in that, so the 4 equal 3 minus 0 plus tan c. So this says that tan c equal 1. In other words, c equal pi over 4. That's just one value. There are infinitely many values. So this is one solution. Okay? So one solution, c equal pi over 4. That means you can plug in that and you can write one solution as 3 minus 4x plus tan x plus pi over 4. If in the general solution, we know that for tan, you need to add k pi. So that's going to give you like all the possible solutions, because we know that the tan has the period pi, so you're going to add multiples of pi. Okay. Good. So that's the solution. But if you need the complete solution, general solution, like with all the cases, so it's going to be negative 4 pi plus tan. We can do x plus pi over 4 plus k pi, where k is a integer. So that's going to give you like all the cases, because the pi is the period of tangent function. Okay, so yeah, so you can see that the basic substitution method works very well, and then you could solve the problem. Okay? So again, so after you solve for u, what you're going to, so this is where you solve for u. So you see solve for u, and then what you do, you use a substitution to solve for y. Good. So that's the what we call the basic substitution method. So let's talk about what we call the next one is the homogeneous equation. So this is the second meaning of the homogeneous equation. Here homogeneous means you can write the differential equation in as a function of y over x. So that's the idea here. So let's look at that now. So this is number 8, homogeneous equations. Homogeneous differential equations. So what is a homogeneous equation? This is one definition of that. A differential equation that can be written as as dy over dx, a function of y over x. So if you can write the differential equation in this form, we call it is a homogeneous equation. Okay, a differential equation that can be written as dy over dx is called a is called a homogeneous equation. So this is like a one definition. This is like the easy definition. So in this case, what we're going to do, since you can write the differential equation as a function of y over x, we're going to pick that. So the solution method is, so we're going to let v equal y over x. So that is the substitution we're going to pick, the special substitution. And then after that, we can write this equation as y equal v over x. And then what we can do is we can take the derivative. So once you take the derivative, what's going to happen? This is y prime. Just use the product rule. So you get v plus x v prime just by the product rule. So we're going to use this as well. So we also need that. So those two are always the case with the homogeneous equation, no changes. So we can use that. And then the next step is, after we do that, then you can substitute that, and then you get a differential equation in terms of v and x. So solve for v first. So so we can say rewrite the equation in v and x variables, and then solve for v first, and then use y equal vx, so simply multiply by x to solve for y. So that's the kind of argument. So it's not that difficult. Okay, so so let's look at this in a problem. So as the first example, let's say this one. Solve xy dy over dx equal x squared y squared along with y1 equal, let's say, square root 2. So let's try to solve this equation. And you can see that this is not the basic substitution. This is not separable. This is not indicative of factors. So you can use any of those techniques to do this. So what we're going to do, we're going to see this term. So we can divide by that term both sides. So that's the starting point. So the answer, dividing by xy, so we have dy over dx, which is x squared plus y squared over xy. So if we divide x squared, okay, let's show the steps. Xy plus y squared over xy. You can see x get cancelled, so you're gonna get the first one become x over y get cancelled, the second one become y over x. Okay, now you can see that this is a function of y over x, because x over y is 1 over y over x. So that means everything looks good, because the first one you can divide by x in the top and bottom. So you can write this one as 1 over y over x plus the other one is y over x. So that is a function of y over x. Now what we can do, we can use a substitution now. So let v equal y over x. Then we know that y prime equal v plus v prime x. So we're going to substitute. So when we substitute, dy over dx means y prime. So this side become v plus v prime x. The other side is 1 over v plus y over x is v. You can see, interesting part, this get cancelled. So that term going to go away. So you simply have v prime x equal 1 over v. If you write this using derivative notation, dv over dx, x equal 1 over x, you can see this is a separable equation. So this is separable. So what we can do, we can separate the two variables. So if we separate the two variables, we can write this one as v dv on this side, the other side 1 over x dx. Now we can integrate the two sides. So integrate v with respect to v, so it's get v squared over 2. This one 1 over x means ln x plus c. Just add c to one side. So we solve for v. Now what we can do, we can use substitution. So use y equal vx or v equal y over x to write. You can write this one as 1/2 y over x whole thing squared. Here this is ln x plus c. Now we can multiply both sides by 2x squared to isolate y. So this says that y squared equal 2x squared ln x plus c. Now what we can do is we can solve for c. So let's say using y1 equal 1, we have actually not 1, y1 equal square root 2. Square root 2, we can substitute, so this square root 2 squared, that's the y value, x value is 1, and then we have ln 1 plus c, but we know that the ln 1 is 0. So this says that 2 equal 2c, says that c equal 1. So we can plug in that value back here. So it is 2x squared ln x plus 1. And now what we can do is we can take the square root, but be careful, when you take the square root you get plus or minus. Now the question is which one gonna work? But we know that y1 equal square root 2, that means which is positive. So that means you have to pick the positive root here. So it is 2. So we have yeah, so we have the 2 there. So that means actually c equal 1. Yeah, so let's actually forgot so c equal 1. Now what we can do, we can do the square root. So you only get the positive one. So it is x. So this is 2 ln x plus 2 inside and the square root. So we only pick the positive one since y is greater than 0. Y positive, because we know the initial condition says y positive. Because if we had picked the other one, you get negative answer. So that's not going to work. So that means if you are given that. So let's say if you had y1 equal negative square root 2, if this is given, you can see that c is still 1, but you have to pick the negative one in this case, negative solution, because otherwise it does not satisfy the condition, because we know that when you try to solve for y you get plus or minus. Okay, so this is what I'm talking about. When you have y squared equal, let's say 4, y can be either plus or minus 2. So which one? It depends on the rest of the problem. So that means if you are given an initial condition like y1 equals square root 2, you want to make sure that it satisfies the condition. That means you have to pick the negative one in that case. So here only the positive one works. Okay, I hope you understand the argument there. Okay, now let's go to the third type of substitution. So the third type is what we call the Bernoulli equation. So let's talk about that. So Bernoulli's equations, Bernoulli equation. So what's the Bernoulli equation? So this is the extension of the first order linear differential equation. So it is dy over dx plus pxy. So we still have that part, but the other side is different. It is y to the n power. So that's a yn term. So that's the difference. We have the extra term on the other side, yn. So there are special cases to consider. So if you get this one, this is a Bernoulli differential equation with that y to the n term. But there are some special cases that we need to consider. What if n equals 0? So n can be 0. Then you're going to get dy over dx plus pxy equal qx. So that is our famous one. So this is the integrating factor method. Okay, that's the integrating factor method. So not very interesting. I mean, we know how to do that. Okay, it's interesting, but we know how to do it. If n equal 1, what happens? So dy over dx plus pxy equal qxy. So if you get that, we have two options. One option is we can bring this term to the other side. So if you bring this on to the other side, so there are two ways to do this problem. So one way, we can write the differential equation like this. We can bring that term to the other side, and then what happens? Y is common, so you can see this again first order linear. So this is integrating factors. Integrating factors. Now, if we bring this term to the other side, to the left side, so this can be qx minus px y. You can see this is separable. Okay, so this is separable. So that means we can solve these two cases. N equals 0 case is integrating factor. N equals 1 case, you can solve in two different ways, either integrating factor method or you can use the separation of variable method. So what we are interested in this one is we can consider the case where n not equal to any of those numbers. Okay. So that means if n not equal to 0 or 1, we have a new case, okay, new situation. So that's the Bernoulli equation. So we're gonna talk about that. So let's talk about that a little bit more. So if n not equal to 0 or 1, what we're gonna do? We're gonna divide. So dividing by y to the n, we can divide the equation by y to the n term. Divide by y to the n term. If you divide the equation by y to the n term, you're going to get 1 over y to the n dy over dx. And then here you're going to get px. This can be y 1 minus n, because we can divide by y to the n term. We already have one y term, so it's becoming y to the 1 minus n. On the other side, it becomes just qx. Okay, now we're going to do a special substitution. So the substitution is we're going to substitute for this term. That's how we do. We're going to substitute for that whole term. So let v equal y 1 minus n. So that is the substitution you want to remember. Okay. And that's why n cannot be equal to 1, because if n equal 1, this is just 1. So it's not going to work. That's not a variable, just a constant. So take the derivative is going to be 0. Now what we can do, take the derivative. So taking derivatives, we can write this one as v prime. So we can use a chain rule here. It is 1 minus n. Y, you subtract one more, so minus n by and y prime by the chain rule. So this is a chain rule. Good. So that means we can solve for y to the n y prime term. So this says that y to the minus n y prime is simply 1 over 1 minus n times v prime. So that's always the case. Now what we're going to do, we're going to substitute that in the equation. So if you go back and substitute in this form, So you're going to get 1 over 1 minus n v prime, that's the first term, plus px v equal qx. And you can see this again first order linear in v. So this is first order linear, in v. That means we can use integrating factors. Okay, so use integrating factors. Use integrating factors to solve for v, and then use v equal y to the 1 minus n to find y. So that is the argument. Okay, so that's how you solve the Bernoulli equation. So let's look at one example to see how it works. Good. So how about this one? Solve, let's say 2x dy over dx minus y equal 6x squared y cube. This one. So you can see we have this term, and this is Bernoulli. This is a Bernoulli equation. So we divide by that term. And also you can see that there's an unnecessary term here. What's the term we have here is, and you can see, so dividing by, we also going to divide by x also. Actually you can divide by 2 also, but we can leave 2 and you can see how it works. So dividing by x y cube. So you're going to get 2y cube y negative 3 dy over dx minus 1 over x y negative 2 equal, one of the x terms get cancelled, y3 get cancels, so you're going to get c 6x. That's what you get. Now the substitution. So we divide. Now you can see that you get to the form that we want. Now we're gonna substitute for that. So we're gonna say v equal y negative 2. This implies that v prime equal negative 2 y negative 3 y prime. In other words, y negative 3 y prime is negative 1/2 v prime. I mean, that's what happened, so we read it like that. And now we can substitute that. So if we substitute that, so by substituting, substituting 2 times negative 1/2 v prime, substitute for that, and then minus 1/2 v equals 6x. You can see this get cancelled, and then you're going to get negative v prime negative 1 over x v equals 6x. You can multiply by the negative sign, so v prime plus 1 over x v equals 6. You can see this is first order linear in v. That's exactly what we want. First order linear in v. So let's use the integrating factor method. So the integrating factor, I equal e to the px dx. So e to the 1 over x dx, e to the ln x, that means x. So we get that. Now what we can do, we're going to multiply by that both sides. So multiplying by x. So we're going to get x v prime minus plus v equal negative 6x squared. This side is automatically the v and the integrating factor, which was x, equal negative 6x squared. Now integrating. Those steps are just the integrating factor argument. Integrating, we're going to get vx equal, if you integrate this one, it's going to be negative. So you're going to divide by 3, so it is 2x cubed plus c. So that means v equal, if you divide by x, it's negative 2x squared plus c over x. Now what we can do, using v equal y to the negative 2, we're going to substitute that. So we have 1 over y squared, which is y to the negative 2, equal negative 2x squared plus c over x. So what you want to do now is you want to flip it over, but before you flip, you're going to get the common denominator here. You have to do that. So x, so that means you're going to multiply by x, so you can write this in a c minus 2x cubed. Now you're going to flip it over, so that means y squared is x over c minus 2x cubed. Now again, considering cases, you can say y equal, since we don't know, we can write plus or minus x over c minus 2x cubed square root. So those are all the cases, the two cases, and if you know the initial conditions, we can find them. Otherwise, this is the general solution. So this is the general solution. Okay, so that's about that. So that's the basic, that's the substitution method. So we talk about the basic substitution, homogeneous equations, and then the Bernoulli equations. So, and then the last type of first order differential equations, the exact differential equations. So let's talk about that now. So this is the last type we talk about, what we call the exact differential equations. So what we mean by exact differential equation? So we can look at the standard form, which is m a function of xy dx plus n a function of xy dy equals 0. So that is the standard form we're going to consider. Okay, it has to be dx plus dy. But there are other ways to write the same equation. For example, if you divide the equation by dx, you can write this same equation in this form as well. So you can write this one as, for example, dy. Yeah, I'm going to write it down here because I need some space. So we can, by dividing by dx, we can write this one in, for example, dy over dx times nxy plus mxy, just by dividing by dx. But we don't do that because this is really not the right way to do it. We're going to go with the standard form above. So this is what we call the standard form. We do that for a reason, because there are differential equations we're gonna come, like in physics and mathematical physics, come into this form. So that's why we kind of study that. Now let's talk about the theories that we discussed. So what we call, if the dabba m, there's a partial derivative of m with respect to y equal the dabba the partial derivative of n with respect to x. If those two are equal, we call this differential equation a exact equation. Okay, that's the kind of test. The equation is called exact. Is called exact differential equation. This is the kind of test we use. In that case, what happened? There is a function. There is a function. There's a function f x y equal a constant. So there's a function like that, such that the partial derivative with respect to x equal the m function, and the partial derivative with respect to a y equal the n function. So it says that if that is the case, if this condition satisfies this condition, there is a function such that fxy equal constant, c is a constant, that can give you dou by f over dou by x equal m and dou by f over dou by y equal n. Okay, and then if you know that function fxy, what we're going to do, we're going to solve that function. We're going to solve for y. So that's what we do. And then that y is the solution we are looking for. So let's look at a problem. Before we do that, actually, let's talk about the solution method. So what we normally do is we're going to start with one of those equations. There are two equations. So we start with the easy one and then take the integral. Once you take the integral, then you get the function back. So that's the kind of idea. So let's try the steps here. So let's call the solution method. So this is the lengthiest argument that we use in differential equation. Yeah, so let's say you can pick just one of them. So let's say you go with the x function, x derivative. So let's say you pick that one. So you can just reverse the same argument. You can just rewrite the argument using the other one if you want. But let's go with this. And then what you're going to do, since this is a partial derivative with respect to x, we're going to integrate with respect to x. So it's very important. So integrate with respect to x. So if you do that, you get the function back. It's a function of xy. It's the integral of mxy with respect to x. Since it's a partial integral, maybe you had a function only a function of y, because since you are taking the partial derivative with respect to x to find dou by f over dou by x, maybe there was a function of y alone. So we just put that back in. So that's a new term. It's not a constant, it's a function of y. Now what we're going to do, you're going to combine the two. So we're going to differentiate this one. So differentiate with respect to y variable. So if you do that, then you're going to get dou by f over dou by y. That means you're going to integrate whatever the answer you get with respect to y, because it's a function of x and y. We want to integrate with respect to x. So what will happen here? It just becomes this regular derivative because it's a function of y only. We don't need partial derivatives there. Now what we can do, we can solve for gy. But the goal is to find this. That's the only thing we don't know. So the goal is find. Okay, that's the goal. Find this. So now what we can do, we know that this should equals the ny function, because this is the partial derivative with respect to y. This is exactly the nxy function. So we're gonna set it here. We're gonna set that. We're gonna set this equal to this. Now what we're gonna do, solve for g prime y. Okay, or simply solve for g prime y, because we can find it because they match. Then you can find g prime y, and then integrate and find gy. So the next thing is first find g prime y, and then solve for or integrate, and then we can integrate that. First find gy, and or let's try it like that. First find gy and integrate. It's a derivative. Integrate to find gy. Now what we're going to do, we can substitute that in the just the function above. Once you substitute that there, so what we can do, we can substitute the substituting, we have f xy function, so we can substitute here. We know this part, plus now we know gy because we found that above. Okay, now we are not done yet, but we know that the function, what we can do, we can set this equal to a constant, because that's the function we are looking for. We know that there was a function which is fxy which is equal to a constant, so we set that, we put there, and then solve for y if possible. After that, what we can do, solve for y if possible, because sometimes we cannot do that. But if you cannot do it, you get an implicit solution for y. So you get implicit solution for y, because if you cannot solve, it's an implicit solution. So that is the solution method. I know it's a little lengthy, but that's how it works. And then we also talk about a shortcut method. So I'm going to discuss that. So you can use that if you remember. That's not that difficult. It's very easy. So let's talk about the shortcut method. So the shortcut method, so what was that? So I'm going to write that you may also use the shortcut method. So what's the shortcut method? We can start with dabba f over dabba x equal m xy function, and since the partial derivative with respect to x, what we can do, we can integrate this one with respect to x. So integrate with respect to x. Once you do that, you get a function. So what happens when you do that? I need some space here. Once you do that, you get the function fxy. So you get a function. You just integrate with respect to dx. So when you integrate, you can see that you're going to simply consider y is a constant. So you get some expression and do the same thing. So what we do, dabba f over dabba y, which is n xy. What we can do with this, you can integrate with respect to y. So you again get the same function in another form. So here what we did the partial integral with respect to y. Now what we can do, we can write the common terms once, uncommon terms once. So your function f is simply, you write common terms and uncommon terms once. So that's the argument. So after you get that, now what we can do, as before, we're going to set fxy to a constant, and then after we do that, so we set that. After that, what we can do, solve for y if possible. Okay, so that's a shortcut. So you start with dabba f over dabba x, integrate with respect to x. You go with dabba f over dabba y, integrate with respect to y, and then you get two expressions. You write the common terms once, right? The common terms, you can see some common term once and uncommon term once. That's the function fxy. You say this equals 0, solve for y is possible. So let's look at a problem. So this is, so let's say solve. Three ex minus y squared dx plus 3 minus 2xy plus sine y dy equals 0. So if you get a problem like that, the first thing that we do is we check whether this is exact. So this is the m function, this is the n function. So what we're going to do, we're going to check, we're going to do the test here. So the test is we can do da by m over da by y. Remember the m function do with respect to the other one, so da by y. So which is negative 2y. And you can see that that's exactly equals to da by n over da by x. If you respect to x, the constant, the sign term goes away because it's a partial derivative. You get negative 2y. So they are equal. That means it's an exact equation. Okay, that's an exact equation. So that means that means that there is a function. There's a function z f. There's a function z which is simply f x y equals c, such that, so there's a function z which is a function of x y, such that da by f over da by x equal the m function, which is 3ex minus y. Now what we can do, we can integrate this back to x. So integrate with respect to x. So if you do that, you get fxy. If you integrate with respect to x, it is 3ex minus actually it's y minus xy squared plus gy, because we don't know whether there is a function. So I'm going to call this equation number 1. Now what we can do, we can differentiate this one, differentiate with respect to the other variable y. So if you do that, you get da by f over da by y. So if you differentiate with respect to y, this is 0 minus 2xy, because it's a y, so you get 2y. With minus x, you get minus 2xy, and then plus g prime y, because it's a function of y only, so it's just the regular derivative. Now we're going to set this equal to the nxy function, because we know that by the theory there is a nxy function. We can set it, we can set to that. So it is 3 minus 2xy plus sine y. So it's clearly, you can see that this function has to be 3 plus sine y. When you set them equal, g prime y has to be 3 minus sine y, because they are equal to each other. Good. Okay, so we know that. So that means, so this implies that g prime y equals to 3 plus sine y. Now what we can do, we can integrate with respect to y. So integrate with respect to y, and if you do that, you're going to get gy equals to the integral of g prime y dy. That means if you integrate, it's a simple integral with respect to y. So you can see that you're going to get 3y plus, this is sine. So sine means negative cosine y. And we are not adding plus c here. Now by equation 1, since we find y, we can substitute. By equation 1, fxy equal 3ex minus y squared x plus 3y minus cosine y. So that is the gy function. That is gy function. So what we do, we're going to set this equal to c by theory. So that's a constant function fxy that satisfies those conditions. So now what we can see, there's no way you can solve for y. So then the implicit solution is given by 3ex minus y squared x plus 3y minus cosine y equal constant. So that is the implicit solution for y. And you can see that since we have the cosine y term and the y squared term, there's no way you can solve this for y. But if you do not have cosine y term, then you can solve this for y, because you can use the quadratic formula and then you can solve for y. But since you have the cosine y term, we cannot solve. Good. So this is how we solve an exact differential equation. So next we can talk about what if it is not a exact equation. So what we call the almost exact equation. So we're going to solve that next. So next talk about how to solve almost exact equations. So almost exact. So what's going to happen if you look at the standard form of the exact equation, mxy dx plus n xy dy equals 0. So what can happen when you take the partial derivative, the first one with respect to y, it does not equal the partial derivative with of n with respect to x. So that's happened. So in this case, you can see that the equation is not exact. It's not exact. So what we're going to do, we're going to use the integrating factor method. So we're going to use the integrating factor method. So we're going to use integrating factor method. So there are two cases to consider. We have two cases. So so the first one is we're going to calculate my minus nx over n. We calculate that if this is a function of x only. If this is a function of x only, so let's assume that this is a function of x only. It's a function of x only. In that case, we're going to calculate the integrating factor. Is also going to be a function of x, which is e to the, we can integrate that expression my minus nx over n with respect to x. So that's the integrating factor in that case. The other case is nx minus my over m. So this is a function of y only. If this is a function of y only, then you're going to calculate the integrating factor iy, which is e to the nx minus my over m dy now. So how you can remember them? So you can remember them like this. So you can see this is m n n. The other one is n m m. So that's the format of that, m n n or n m m. Good. And then after we find integrating factor, the rest of the problem is exactly the same as what we normally solve a problem in using integrating factor methods. After that, what we can do, then we're going to multiply by the integrating factor. Then we're going to get I times m dx plus I times n dy. So this is the exact equation. So we're going to follow the exact equation argument. This is an exact equation. So we're going to follow the exact equation argument. So let's do just one example just to see how it works. Good. So let's solve this problem. So let's say solve xy dx plus 2x squared plus 3y squared minus 1 dy equals 0. So let's solve that. So what we gonna do, we're gonna pick this as m, we're gonna pick this one as n. Then you can see that dabba m over dabba y, which is x, and dabba n over dabba x, which is 4x, and you can see that they are not equal. So this says that dabba m over dabba y not equal to dabba n over dabba x. So that means not exact. So not exact. So what we're gonna do, we're gonna see which one gonna work. So let's calculate my minus nx over n first. So what do you get? What is my? What is the y derivative with respect to y derivative of m, which is x, and the minus, let's calculate the x derivative of n, which is 4x, divided by n. N means 2x squared plus 3y squared minus 1, which is you can see that this is not only a function of one variable. Okay, so you can see that not a function of one variable. So not a function of one variable. So that means it's not going to work. So let's look at the other one. So nx minus my over m. So if you do that, you're going to get nx, that is 4x, my, that is x, divided by m. Now m is xy. So if you cancel x, so it's going to be 3x over 3 over y. So you can see that this is a function of y only. So the function of y only. So that means we can calculate we can find the indicative factor. So iy is e to the formula nx minus my over m dy. We already calculated that. So it is 3 over y dy. That means 3 ln y. So bring it here. So that means it's going to be y cube. So y cube is the indicating factor. So we're going to multiply by that. So multiply by y cube, the differential equation. So you're going to get x y to the 4th power dx plus you're going to multiply by y cube. So it is 2x squared y cube plus 3y to the 5th power minus y cube dy equal 0. So that's what you get. And you can see that once you do that, it's going to be exact, because that's how we pick the numbers. So now this time we can use a shortcut. Let's use a shortcut to get the answer. So this is exact. So we use a shortcut method. So we use the shortcut method. Okay, so let's use a shortcut method. So if you use the shortcut method, what do you get? we're going to go da by f over da by x, which is the first function. So we're going to integrate this one with respect to x. So if you do that, you get fxy equals to x squared over 2y to the fourth power, because we integrate with respect to x, and we are not going to add the constants. And then go with the other one, da by f over da by y, which is the other function. So it is 2x squared y cube plus 3y to the fifth power minus y cube. We're going to integrate this one with respect to y. If you do that, you get fxy equal 1/2 x squared y4 plus 1/2 y to the sixth minus 1/4 y to the fourth power. Now what we can do, your fxy function is, we're going to first write the common terms, and you can see this is common. So we can write that once. So 1/2 x squared y to the fourth power. And then write the uncommon terms. So 1/2 y to the sixth minus 1/4 y to the fourth. Now what we can do, we set this equal to 0. And you can see that it is not easy to solve this for y. So that means this is the implicit solution. This is the implicit equation, implicit solution, implicit equation for y. So that is how we solve the almost exact equation. And there are, like, cases you cannot really solve because we only consider two cases. Whether my over nx over n is a function of x, or nx minus my over m is a function of y. What if it is not the case? So that means there are some cases that still give you problems. Okay, and then there's a video, what we normally call it all-in-one video. It's already posted. So that's a kind of good one that's going to give you kind of all the methods in one video. So you can look at that. It's in there. I'm going to also put the link to that video, all-in-one review. All-in-one review for first order equations. Okay, so it's going to show you all the formulas there. Good. Now what we're going to do, we're going to discuss the numerical solutions. And you can see that there are a lot of equations that cannot solve. Okay, there are only few equations, just a very small percentage of equations that you can solve. So that means there's a need to solve, we need to find approximate solutions. To find approximate solutions, we're going to use numerical techniques. So let's talk about that. So that is number 12, numerical methods. Numerical methods. When you talk about numerical methods, there are actually we discussed 3 of them. One is the easiest one, the most obvious one, what we call the Euler's method. And then we have improved Euler. Improved Euler's method. And then the very good one, what we call the Runge-Kutta method. Runge-Kutta method. So the Runge-Kutta method is like very good. It's going to give you answers like excellent answers for certain problems. So let's talk about the Euler's method. That's the easiest one. Euler's method. So how it works? So what's the geometric argument for that? So let's say you have a curve. So what's going to happen? you are given a point and the derivative, like the slopes everywhere. So you are given the derivative at each point and a starting point. So that's the only information you have. You can find derivative at any point and also give you the starting point. So the goal is to find an approximation for another point at some point. So that means so this is the actual curve. So what you try to do, you can approximate the value at a certain point. So what we normally do is we're gonna divide this into equal parts and then approximate the value successively. So you're gonna calculate y1, that's y1, and then you calculate y2, and then you calculate y3, like that. So so that's the kind of argument we do. We're gonna approximate one by one. We can look at the tangent line. That's how we do. We can look at the tangent line and then calculate the next one. So actually the first one is not exactly correct. So because when you draw the tangent line, so what happen is, let's extend the tangent line. So this is what you get. So that means your first value is here, right here. That's the first value. So that's the first approximation. So that is y1. Now we can use that value and also use the slope at the point to find the next value. So if you draw the slope at that point, you can see it's going to go like that. So that is y2. Okay? That is y2. So like that, we're going to find that's y2. And then we can draw the slope at that point. So it's going to go right here. That's because they're going to parallel to that. That's the slope. So it's going to give you y3. So that's y3. So that's the approximate value. That's y3. So this is the kind of idea. So you're going to look at the slopes at each point and then use the tangent line to approximate the next point. So that's the kind of idea. So what we normally do is we're going to divide this into equal subintervals, h, like that. And every time calculate the next point. Calculate the next point. So what you are given is simply you are given dy by dx fxy. So that means you know the slope at every point and also you know the starting point. So those are the only things you are given, the slope at every point and the starting point. So and then our formula becomes like this. So your n plus 1 node is simply xn plus the gap, and then your yn plus 1, the next one is simply y current one plus h times xn yn. So that is the scheme for the Euler's method. So this is the Euler's method formula, and this can work. You can start with n equals 0. Once you plug in 0, you get x1, and when you plug in 1, you get x2, 3, like that, depending on how many points you need. Okay, so that's it. So that's the Euler's method. So let's just look at an example and see how it works. So let's look at an example. So let's do this example. Let's say approximate y2 using Euler's method if given the differential equation dy over dx equal, let's say, 3y minus x and y0 equal minus 1 and the gap, the step size 0.5. So this is a kind of problem that you can get. You get a differential equation, initial condition, and a h. So it is always a good idea to kind of try to understand what's going on here. So we have x0, that is starting value, that is 0, and then we have y0, that is the y value. So how many we need to calculate? So you can see that x0 is 0, and then we're gonna go in 0.5 steps. So that means we have 0.5, and then 1, 1.5, and 2. So you calculate at 2. So that means x1, x2, x3, and x4. So knowing x0 and y0, you want to calculate y1, y2, y3, and y4. You calculate 4 more. So let's look at the situation here. So what we have is, so the answer. So what we can do, we're gonna first identify what is the x y function. So you can see it is 3y minus x. That's the xy function. Now we got the scheme. So what's the scheme? Xn plus 1 is xn plus h. So in this case it is xn plus 0.5. So every time you increase by 0.5, and then yn plus 1, which is yn plus h, f xn yn. So let's plug in and simplify. So this is yn plus h is 0.5. The function is 3yn minus xn. So you plug into the function, because that's a function. So you plug in for that. Now what we can do is we can simplify. If you simplify this, what do you get? You're going to get 0.5 times 3 means 1.5 plus 1. So it is 2.5 yn minus 0.5 xn. So that is the formula that we're going to use for each n. So we can start with we have x0, which is 0, and we have y0, which is -1. Now we can start plugging the value. First value is 0. So when you plug in 0, you get x1. So when you plug in 0, you get x1, which is, you add 0.5, so it is 0.5. And y1, the formula says it is 2.5 y0 minus 0.5 x0. Since you know the two values, we can plug in. So it is 2.5, y0 is -1, and then y0 is -1, and then we have 0.5 times x0 is 0. So if you simplify, so you can use a calculator for that, you're gonna get -2.5. So that is the y1 value. So keep doing. So now you plug in n equal 1. If you plug in n equal 1, you get x2, which is 1.0. We have y2 now. So it is 2.5 y1 minus 0.5 x1. Since we know y1 and x1, we can plug. That's coming from the previous step. It's always those two coming from the previous step. So we're going to plug in those two. So you're going to get 2.5 y1 means -2.5 minus 0.5 x1 means 0.5. Always coming from the previous step. So if you use a calculator, you're going to get -6.5. Go to the next one. N equal 2. So this is going to give you x3, which is 1.5. This is going to give you y3 value. According to the formula, it is 2.5 y2 minus 0.5 x2. We know all the values from the previous step. So it is 2.5 -6.5 minus 0.5, and then x2 is 1.0. Now what we can do, we're going to simplify again. So you're going to get -16.75 is a calculator. And then we can put n equal 3, you get x4, that means that's exactly the number we want. y4, that's the value we are looking for. Again, it's the same formula. It is 2.5 y3, we know that, and then 0.5 x3, we also know that. So let's plug in there. So you get 2.5 negative 1675 minus 0.5 and then 1.5. So if you use a calculator, you're gonna get negative 42.625. But this method is not very accurate, so you don't need this many decimal point. We normally leave like just one decimal point. So that means your y2 value, which is the y4th, y2 value means the y4th, is approximately equal to negative 42.6. Okay, so you can see it's not that difficult. So it is always a good idea to get this first, because then you can simply plug in there every time rather than using the original equation every time. So always try to simplify that first and then use that simple equation. This is much easier. Okay, so so this is how you use the Euler's method to find the approximate solution. So next, what we're going to do is we're going to discuss the most correct version, what we call the Runge-Kutta method. So this is very accurate. Even the commercial softwares use that. So I should say that. So this is excellent result. Like a very similar problem. So you have y prime equal fxy. So the slopes are given with a initial condition y x naught equal y naught. So you have a so you know the starting point and you also know the slope. So then the goal is to approximate the actual curve. The same idea. We're gonna split as before, though we're gonna call the gap is h and into find the value at xn. So so the scheme is slightly different now. So what we're gonna do, we're gonna calculate several intermediate values. So we're gonna go for n equals 0, 1, 2, like that, depending on how many you need. As before, we're going to calculate the x naught, which is xn plus 1 equal xn plus h, no change. But before we calculate y, we're going to calculate several other slopes. So we're going to calculate k1 slope, that is the slope at xn yn. Then we're going to calculate k2 slope, that is the slope halfway in between. So you're going to go xn, you go h over 2, comma, yn plus h over 2 times k1, and then k3 slope, which is f, again at the halfway point, comma, yn plus h over 2 k2 now. So we have k1 goes there, and then k2 goes there, and then we have k4. So what is k4? Which is f xn plus h yn plus h times k3. So we're going to calculate those extra slopes, and after you calculate the slopes, then your yn plus 1, the next approximation value is given by yn plus h divided by 6 times k1 plus 2k2 plus 2k3 plus k4. So that is the Runge-Kutta scheme. Is very similar. You know x naught, y naught. So you can calculate x1, y1, x2, y2, x3, y3, like that. So this is what we normally call the fourth order Runge-Kutta. Fourth order Runge-Kutta method. So normally called RK method. Runge-Kutta method. This normally used in what we call ODE 45 algorithm in MATLAB and other softwares use an improved use an improved version use an improved version of this. Okay, so that means it's very accurate. The solutions are very accurate, and we solve several problems in the homework. And you can look at that. Also, we have solved several problems in the video as well. So if you need more information, you can find them. Good. So this is the Runge-Kutta method, and I'm not going to solve a problem from this one because it's very lengthy. Because you know that there are many things you need to calculate before we calculate the next one. Okay, so this is how we gonna solve a. This is the next good numerical method to solve a first order differential equation. So next, let's talk about what we call the directional fields. Directional fields. Some also call this slope field. Slope field. So what's the directional field? So what we're gonna do? So when we have a differential equation, so let's say you are given a differential equation dy over dx equal fxy. So what we can do is at each point in the domain, draw an arrow indicating the direction of the tangent line, indicating the direction of the tangent line, the direction of the tangent line. So that's what we call the directional field or the slope. The direction of the tangent line means the slope. So we can do a look at a problem. So let's say draw the directional field of let's say dy over dx equal 2x minus y. So if you get a problem like that, what we're gonna do, we're gonna draw like a typical grid, with enough points. So let's do that. So this is a grid with enough number of points. So normally like this will be given. So let's divide this into 3 parts. So what we're going to do, let's say this is 0, and then 1, 2, 3, and then -1, -2, -3, like that. So this is 1, 2, and then -1, -2. So what we do is, so this is the x direction, and this is the y direction. So we're gonna at each point you can evaluate the slope and draw a small line. And we know if there's a positive slope, so the arrow goes like that. This is for positive slopes. If you have a negative slopes, that's the arrow goes down. It's a 0 slope, is horizontal. So we can use those 3 facts. So let's evaluate at 0. So at 0, you can see that if you plug in 0 to the differential equation, you get dy over dx is 0. So that means at 0, slope is 0, so you draw a line like that, the 0 slope. And then also you notice that there's a special line. For example, if you look at this line, so you can say the line, on the line, if you set this equal to 0, so you're going to get y equal 2x. On the line y equal 2x, the slope is 0. The slope is 0. Slope is 0. So that means, what is this line? So that means at x equal 1, y equal 2. So that means this is the line. So the line passing through these points. So on this line, the slope is 0. So that means if you pick any point on that line, you know that the slope has to be 0. So that's one thing. So we know that on that line, slope is 0. And also let's calculate few other values. So for example, at this point, if you look at this point, you can see that it is x equal 1, y equals 0. So the slope is 2. So it's a line with slope 2. And at that point, you can see slope is 4. So it's more steeper. And here slope is 6. So it's much more steeper like that. And if you go to the other side, you can see at -1, slope is -2 and -4 and -6. So it's much more steeper. And then if you go along the y-axis, you can see that x coordinate is 0, y coordinates increases, but with the negative sign, it's going down. So for example, at this point, the slope is -1. So it's going to go like that. The slope is -1. And if you go up, it's -2. So it's much more steeper. And here, at -1, it is 1, and this is a 2. And we can also draw a few more. So for example, if you add 1, 1, so you're going to get slope 2 minus 1, so it's 1. So slope is exactly 1 here. And then if you go further, it's the same y coordinate, but x coordinate increases, so you're going to get more steeper, like that. And then here what happened, x is -1, that means -2, and then y is 1. So at this point, what's going to happen is, let's calculate what you get. So you can see the x equal -1, that means it's -2 and 1, so -3, so it's -3. And when you go up, it gets more steeper because y is you subtract y, that means it gets more steeper. And at -2, it's going to be -4, and so it gets more steeper. You go the same thing, when you go this way, it's going to get much more steeper. And what about this point? So this point, you can see x is 1, so it's 2, and then -1, so it's 3, because y is negative, so it's 3, so it's more steeper. The same thing, much more steeper when you go that way. So go down, that means it's gonna get more steeper, like that. So we only left these. So let's calculate what happened at this point. So which is -1, that means -2, and then we have y equal -1. With the negative, it become positive, so it become -1. And then when you go, it's gonna get much more negative, like that. So those are a few values. Okay, so we still have just a few more. So at this point, what's gonna happen is it is -2, that means -4, and with -2 it's become. So what happened here? So you can see when you go down, you subtract negative values, that means it's gonna get less steeper, so like that. Yeah, because the negative sign, so it's get less steeper when you go down. So that means this has to be less steeper than that. Good. So when you go down, it's get less steeper because the negative y sign. Okay, so that's the directional field. for this one. And good. So now what we can do is we can draw a typical curve. Like for example, if you want to draw a curve that passes through one negative 1 1, so that means the point, this point, that's the negative 1 point. So what's gonna happen? It's gonna follow the arrows. So if you follow the arrows, what's gonna happen? It's gonna go like that, go like this, and I think it's gonna go like that, and get 0, and then turn, and gonna go uh, like this. So this is a typical curve that passes through the point 1 1. So what we're gonna do is simply follow the uh, arrows. So like that. So good. Okay, so that's what we can do with directional fields. And then what else we had? We talk about existence and uniqueness theorem. So let's talk about that a little. So we have the existence and the uniqueness theorem. Number 14. Existence and the uniqueness. Existence and the uniqueness. So let's look at the differential equation dy over dx equal fxy along with yx naught equal y naught. So let's say, so there's a region, so there's a point x naught, y naught. So we know that point. Now the question is whether there is a unique solution that passes through that point. Actually, that depend on certain conditions of the function. So for example, if the function f is continuous and its y derivative, y partial derivative continuous, so the answer to that question is yes, there's a unique solution. So let's write that as a result. But in general, uh, a solution may or may not exist. May or may not exist. But under certain conditions, the answer is yes. So let's write the theorem. So this is what we normally call the Picard's existence and uniqueness theorem. So Picard's existence and uniqueness theorem. So what it says that for the initial value problem, dy over dx equal fxy along with yx naught equal y naught, there is a unique solution. There is a unique solution. This unique solution. Just unique solution near x naught y naught if the function fxy and its partial derivative with respect to y are continuous near x naught y naught. So we check what happened near x naught y naught is if the two functions fxy and the da by f over da by y, the partial derivative with respect to y continuous, then there is a unique solution around that. So that means if you can extend that interval, along that interval there is a solution. So it can be the whole region, because this interval can be the whole domain. So that's the existence and uniqueness theorem. So we only check whether these two functions are continuous near that point. So let's just do one example just to see how we can apply that. So for example, something like this. For the IVP, for the initial value problem, dy over dx equal x over y along with y1 equal to, so that means you can see your region is, so say 0, so it's 1 and 2, so there's a point somewhere. So we're going to check what's going to happen near that point in that box. You can see there's a box defined. Yeah, good. So we can check whether there's a solution in that small box. This box can be everything, but we just guarantee in that small one. Okay. So then we can see that there is a unique solution. There's a unique solution. Y equal yx, so it's a function of x. That's what it means. Near, you can say near the point, 1, 2, since the function fxy, which is x over y, and f over y, if you take the partial derivative with respect to y, you're going to get negative x over y squared. That's what you get. And you can see that though both functions are continuous, there are no problems with that near that region, but you cannot include 0. If you include 0, we get the division by 0 situation, but here no, because we only consider near 1, 2 points, so everything, all the functions are continuous. So since the two functions are continuous near the point 1, 2. But there are problems near 1, 0. If we have 1, 0, because at that point the y doesn't exist anymore. Okay, so we can see, but near 1, 0, the solution does not exist. Since y over f over y discontinuous, y and fxy equal y over x discontinuous at 1, 0. So that means there are no solutions over that point. There's no slope at that point. Okay, so and then we need to talk about the autonomous differential equations. The autonomous differential equations. Autonomous differential equations. So you can say a differential equation is called autonomous if it does not depend on the independent variable. If it does not depend on the independent variable. For example, dx over dt equal minus x x minus 1 squared is autonomous, because you can see that it does not change over time because there's no t term, so it's just fixed. Okay, so this represents the what we normally call the stable solutions, stable situations, because it doesn't change. Differential equation doesn't change; it can stay there. Uh, so you can see that. So the knot, so you can see does not change, does not change, does not change as does not change as time. That means in this case t changes. Okay? That's very important. And then we define what we call critical points for that. So critical points. So critical point means the places where the derivative is 0. Okay? So if dx over dt equals 0 at x equal x naught is called a critical point. It's called a critical point. And then after that, what we did was we check whether the critical points are stable, unstable, half stable. So we may check whether the critical points are stable. We may check whether the critical points are stable or not. Okay. So let's do that in a problem. So we can do something like this. So the example, find the critical points and find the critical points and classify them as stable, half stable, or unstable. Yeah, so there are three types: stable, half stable, or unstable. For the differential equation dx over dt equal negative x squared x plus 1 x minus 2, something like that. So what we can do, we're gonna first find the critical points. So for critical points, what we can do, we can say dx over dt, which is negative x squared x plus 1 x minus 2 equals 0. This implies that from each factor, the first factor say 0, and then we have negative 1 and 2. So negative 1 coming from here, negative 1 coming from here, and the 2 come from there. So those are the three critical points. Now what we're going to do, we're going to draw the phase portrait. So it's a vertical line, and we're going to put those numbers in the order. So we're going to go with negative 2 first, and then we have 0, and then we have 2. So those are the 3 points that we have in that order. Now what we're going to do, we're going to pick points in those intervals. So we're going to pick a point which is greater than 2, we're going to pick a point between 0 and 2, and then pick a point between negative 1 and 2, negative 1 and 0, and then pick a point which is less than negative 1. Now what we're going to do, we're going to check the sign of the slope. So we can check the sign of the slope. So you can see that you just plug in a just point in those region to the equation, and you can see that it is if you pick a point like let's say 3, so it's negative, and if you plug in 3 it is positive, and if you plug in 3 it is 4 is positive, if you plug in 3 it's positive. So that means this says that so negative, positive, 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 so it's negative. That means dx over dt is negative, that means it's going to go down, so we're going to put the arrow going down. Do the same thing. Now we're going to pick a value between 0 and 2, so like for example 1. So if you plug in 1, you can see it's negative, positive, this is automatic. And then if you plug in 1, you can get x plus 1 means 2, so it's positive. And if you plug in 1, this is negative, so that means it's going to give a negative, negative, a positive sign, so that means dx over dt positive, so that means it's going to increase. So we're going to draw a line like that, arrow like that. Now we're going to pick a value between 0 and negative 1, like a negative 0.5. So if you do that, it's negative, positive, automatic. And if you pick a value between as like a 0.5, and then you can see this is positive, and then this is negative. So that means positive. So that means dx over dt, this is the slope, which is positive. So that means it's going to go up. So that means the arrow going up. Now for the last one, we can pick like something like negative 2. So if you pick negative 2, it's a negative, positive. If you pick negative 2, it's going to be negative, this is negative. So there are 3 negative signs, that means negative. So that means dx over dt negative, so it's going to go down. So we're going to put a down arrow. So now you can see that the two arrows converge in the first one. So that means this is a stable point. At this point it is stable, that means both sides going to converge to that. And at 0 you can see that one goes in, one goes out, so it is a half stable. And then the last one you can see that going out, so it is unstable. So we can say that for those critical points. So that's the classification. And the last thing what we can do, let's say you start with a point, like at the beginning you start with a point. So let's say so the question is, if x0, the starting value is let's say negative 0.5, so what's going to happen in the long run? So find the limit, t goes to infinity xt. So what's going to happen, you can see that when time goes on, it's going to go up. So that means it's going to converge to 0, but even though the arrow, all the arrows, the next arrow is also going up, it never go to 2 because it's never pass a critical point. That's a very important fact. Never cross a critical point. So never cross a critical point. Okay, so this is all about first order differential equation and related topics, and then we can talk about second order differential equations. So this is the final exam review of part 2. In this we are going to talk about introduction to second order linear ordinary differential equations. In that we can talk about what we mean by general solution and the linear independence, including Wronskian test. Then we can talk about the reduction of order method. That means we can reduce a second order differential equation to a first order differential equation if you know one solution. And then we talk about constant coefficient second order differential equation. Then we talk about one of the very special case, what we call the Cauchy-Euler differential equation. Then we talk about the higher order constant coefficient differential equations and how to solve them using what we call the characteristic equation method. And then we talk about non-homogeneous equations. Under that we going to talk about undetermined coefficient method and the variation of parameters method. So let's start with the second order linear ordinary differential equations. So this is number 16 according to our list. So this is second order linear, ordinary differential equations. So let y be the dependent variable, and x be the independent variable. It's always a good idea to check what is the independent variable, because sometimes we get confused and write the wrong one and everything is wrong after that. So if you look at a general second order linear differential equation, you can write that in this form. So you can write that as ax, that's the coefficient function of the first, the highest term, and then we have bx, that is another coefficient function of the second one, and then plus cxy equal dx, because x is the independent variable. So you can write it like that. That is the general second order linear differential equation. Now what we're going to do, we're going to divide by the ax term just to make it easy and to bring it to the standard form. So we can divide by ax. So dividing by ax, we can write this equation as y double prime plus bx over ax, later we call that px, and then y prime plus cx over ax y equal dx over ax. So we can write like that. Now what we can do, we can call this bx over ax px, and this is qx, and this is fx. So with that, we can write the standard form. So we have the standard form y double prime plus px y prime plus qx y equal fx. So this is what you get, and this is what we normally call the standard form. So if because we know that ax is not zero, completely zero, so therefore we can always do that. It can be zero. What we can do, we can remove those points. So what we normally call the singular points, so we remove them. Now what we know, this is a second order differential equation, so there should be so this is second order ODE. So that means in theory there should be two solutions. So there are two solutions. Why? Because this is second order. So there are two solutions. So let's talk about the special case. First we're going to consider the case where fx is 0. That's the easy one. So let's talk about that. So that's what you call the homogeneous second order equation. Homogeneous second order differential equation. Homogeneous second order differential equation. So what is that? That is means if fx function is identically 0, then the differential equation is homogeneous. You just say homo, that's mean homogeneous. Okay, that's in short sometimes. Good. Now we have this very important result, what we call the superposition principle. So what is so this is what we call the superposition principle. So let's say superposition. So what it says that if y1x and y2x, if y1x and y2x are two solutions, of the homogeneous equation, if the homogeneous equation y double prime plus px y prime plus qx equals 0, then y equal c1 y1 plus c2 y2 is also a solution, is also a solution for any c1 and c2. So that's very interesting result. So what it says that if you know that y1 and y2 are solutions, then for any c1 and c2, y equals c1 y1 plus c2 y2 is also a solution. Okay, so this is a very interesting result, and let's prove this one. So I'm going to prove this one. So we are not going to prove many in a review, but this is like one of the very interesting result, and you need to know this one. So I'm going to prove this one. So what we normally do is we can write the differential equation of L operator. So let's say define L, that's the operator. So that means the second derivative, that means you need d squared dx squared plus this one we can say px d over dx plus qx. So we can define this operator. So and then what's going to happen is what we call a differential operator. We define this differential operator, and then we know that this differential operator is a linear operator. So linear operator means if you have a sum, you can write as 2, and if there's a constant, you can pull it out. That's what we call a differential linear operator. So this is a linear operator. Okay, so let's try it. This is a linear operator. This is a linear operator. Now what we can do, we're gonna act on that. So we know that y1 and y2 are solutions. That means if you operate on L, so that means Ly1 and Ly2 are 0, because that's because y1 and y2 are solutions. So what we can do, we're gonna operate on that. So let's write it like this. Yeah, I'm gonna write this extra one. So this operator is linear. That is, there are two results. The first one, L y1 plus y2 equal L y1 plus L y2. That means if you have sum, you can break it like that. That's the first condition of a linear operator. The second condition is if there's a constant and y1, you can pull the constant out. So that's the second operator. So that's what we mean by a linear operator. Linear operator. So now let's use that fact. So what we can do, we can consider Ly. We can consider Ly. So then considering Ly, what is y? Y means c1 y1 plus c2 y2. Now we know that the L is a linear operator, so we're going to break it. So we can write this on L c1 y1 plus L c2 y2 using the first property. This is from the first property. Now we get the second property. What's second property? Second property says you can put the c out. So L y1 plus L y2. Sometimes we just write it like that without even bracket. This comes from the second property. But what we know now, we know that since y1 is a solution, this has to be 0. Since y2 is a solution, this has to be 0. So 0 plus 0, that means the whole thing is 0. This says that Ly equals 0. That means, so this implies that y is also a solution. So this implies that, so therefore y is also a solution. So that's the proof. So very simple proof using linear operators. So that's what we call the superposition principle. So let's start to go to the linear independence. Linear independence. So what's the linear independence means? Let's go with the definition. So this is an actual definition. So if c1 y1 function of y1 is a function of x plus C2 y2 equals 0, 0 for any x, implies that this can implies that C1 and C2 are 0. That means there's only the trivial solution. If it implies that, we call y1 and y2 are linearly independent. This because we are only considering 2 solutions, that's why we have 2, but we can just extend this one for 3 solutions, 4 solutions, like that. We just write for 2. We are linearly independent. If the functions are not linearly independent, if the functions are not linearly independent, if the functions, shortcut fun, if the functions are not linearly independent, if the functions are not linearly independent, they are linearly dependent. We call linearly dependent. So what normally happens is we start with general set. If there's a linearly dependent one, we can remove one of the dependent one. Now we consider the new set. See whether this is linearly independent or dependent. If it's dependent, again we remove one linearly dependent one. We keep doing it, and at one point what's going to happen, you get vectors, these are called vectors actually, they're going to be linearly independent. So we can do that like reduction method. We can always try to remove a dependent one. Then we end up with a set which is linearly independent. That's the kind of criteria. So let's try to do like one example just to see how things gonna work. Show that y1x equal x, that's the first function, and the second function y2x is, let's say, cosine x, linearly independent. So what we can do, we can use a definition. So the answer, so let's say suppose we have c1x plus c2 cosine x equals 0 for any x. Now what we can do, because this should be true for any x, so we can just pick any value we like. So we can say x equals 0. Substitute x equals 0. So if we substitute x equals 0, what will happen? We will get c1 times 0 plus c2 times cosine 0 equals 0. It should be true for any x. So we put x equal 0. So this is 1. So this says that c2 equals 0. So now we prove that c2 equals 0. Now what we can do? So that means this implies that solving a math problem is a logical argument. So that's why we write it like that. So what we can, so c2 equals 0. So we only have c1x equals 0. Now what we can do? Just put any non-zero value. So now let x equal 1. Just pick anything other than 0. So this says that c1 equals 0. So what happened now? So if you start with c1x plus c2x equals 0, if you start with this, so we start with that, that's the definition. Proving the linear independent by definition, we assume that, and then this implies that c1 and c2 has to be 0. So that means by the definition, the two functions are linearly independent. Okay. So we can say thus c1 equals c2 equals 0. Okay. Therefore, by the definition, by the definition, y1 x and y2 x which is cosine x, are linearly independent. Okay, so that's the proof. It's a very short proof, but just substitute proper values and we try to prove that C1 equals C2 equals 0. So that's how we prove like something linearly independent. Now, so this can be lengthy sometimes. So we have instead the what we call the Wronskian test. So let's talk about that. Wronskian test for linear independence. Wronskian test for linear independence. What it says that we're going to calculate the Wronskian. So what's the Wronskian of two functions, y1, y2? So it defined as a 2 by 2 matrix, 2 by 2 determinant. It is y1, y2, y1 prime, y2 prime. That's for 2 by 2. So what it says that if this is not equal to 0 for some, not all, for some, all is good, but we don't need that. For some x naught, some x value, then y1 and y2 are linearly independent. We prove that where this is coming from. So you can look at the knot to find out where this is coming from. Good. So let's use this idea to prove this result just to see how it works. So that y1 equal sine 3x and y2 equal cosine 3x are linearly independent. That's short form for linear independence. So let's do the same thing. So we're going to go with the Wronskian y1, y2, which is according to the definition y1, y2, y1 prime, y2 prime. Let's substitute. This is sine 3x. The derivative of sine means cosine. 3 comes out by the chain rule, so it's a 3 cosine 3x. This is cosine 3x. By the chain rule, it is negative 3 sine 3x. Now what we're going to find the determinant. This is a 2 by 2 determinant. We multiply the main diagonal and subtract the product of that diagonal. So if you multiply the main diagonal, you get negative 3 sine squared 3x minus you multiply the other diagonal, so you get 3 cosine squared 3x. Now what happened, you can pull the negative 3 out, so you get sine squared 3x plus cosine squared 3x. We know that by the Pythagorean identity this is 1. You simply end up with negative 3. This is automatically not equal to 0 for any x. Why for any x? There's no x. That means independent. That is, you can say for any x. Therefore, those two functions are linearly independent. So therefore, y1x, which is sine 3x, and y2x, which is cosine 3x, are linearly independent. You can see that it's very simple. Just need to use the definition, the definition of the Wronskian, and then find the 2 by 2 determinant. If you forget what the 2 by 2 determinant is, if you have a, b, c, d, the determinant we use the vertical bars is AD minus BC. That's the 2 by 2 determinant. Okay, so now we have there are like kind of common sets which are linearly independent. So I'm going to give you that set because it's good to remember that, not just for this class but in general. So let's talk about that. So it's a result. The following sets and their subsets. Following sets. So if you pick any subset, still work. Following sets following sets and their subset. You can pick any subset and their subsets. You can just put any number of elements. That's what it means. Following sets and their subsets are linearly independent. So this is like kind of good set to remember. So I'm going to give like about 7 of them here, but there are more. So the first one is this set 1x, x squared, x cubed, like that. This set is linearly independent. And if you pick any subset, for example, 1, 2, those are linearly independent. Let's say you put 1 x squared, x3, those are linearly independent. That's why I say any subset. You can, this whole set is linearly independent, and even if you pick any subset of that, still linearly independent. Because if you make it small, it's always independent. Problem comes when you add more. The second one is 1. I just add 1 to all of them. Ex, then you square this, that means e2x, square this, e3x, not the square, you multiply by another x, so like that. So this set is linearly independent. 1, ex, e2x, e3x, like that. Actually, you can just go with any general one. So for example, let's write that. So I'm going to add one more. So it's a new one. E alpha, like alpha is any non-zero number. E2 alpha, E3 alpha, like that. So this set is linearly independent. Number 4. How about this one? 1 x. This is a very useful one. We're going to use this a lot. E alpha x. And then we're going to multiply the two. So x e alpha x. And then x squared e alpha x. This set is also independent. You can just multiply by x every time. So this set is linearly independent, and any subset of this is also linearly independent. That means x. No, for example, you can start with e alpha x, x e alpha x. That's a like kind of common one. So we need this later when we talk about repeated roots. So e alpha x, and then when you multiply by x, it's going to be linearly independent. When you multiply another one, linearly independent. This is like useful, very useful. Let's go number 5. This one, e alpha 1x, e alpha 2x, like that. E alpha 3x, those alphas are different. So alpha 1 does not equal alpha 2 and not equal to any of the other ones. So actually this only says alpha 2, alpha 3, but it's also it's not equal to alpha 1 as well. So if you want to write it like that, you have to write it like that actually. So that's the idea. So all the alphas are different. And then we have 6th one, 1 sine x, cosine x, and then we have sine 2x, and then we have cosine 2x, like that. So this is very useful in Fourier transform, and that's the Fourier transform basis actually. And then we have number 7. We can square or multiply. We have 1, and then we have sine x, cosine x, and then we can square them. So sine squared x, cosine squared x, and even you can have any product of the previous ones. For example, you can have sine x, cosine x. These are all linearly independent, and any subset of this is linearly independent. And as the 8th one, I'm going to write this one, x sine x, and then x sine x, like that. X squared sine x, you get the idea. Okay? Like that. So those are all those sets are linearly independent, and it's good to remember. Okay, then we have this major result. So let's write this as a theorem, what we normally call the existence theorem. So we can say if y1x and y2x are two solutions, are two linearly independent solutions, This is very important. It has to be linearly independent. If it's not linearly independent, this result is not true. Okay. So if y1x and y2x are two linearly independent solutions, of the homogeneous equation, y double prime plus px y prime plus qxy equals 0, the general solution, that means any solution you can write in this form. The general solution is given by y equal c1 y1 plus c2 y2, where c1 and c2 are any constants. Okay, these are any constants. So for any constant c1 and c2, the general solution is given in this form. For that, y1 and y2 has to be linearly independent. So that means any solution you can write in this form: c1 y1 plus c2 y2. That's like really powerful result. Okay, so that's about the major things. And then so let's talk about the non-homogeneous case. So that's as we talk, that topic we can talk about later, but we're gonna put it here so that it does like everything together. So none, this is all for homogeneous, but now let's talk about the non-homogeneous equation. So the non-homogeneous equation. So what's a non-homogeneous equation? We have y double prime plus px y prime plus qxy equal fx. So where fx is not identical, it can be 0 for some values, but not identical 0. So the question is how to solve it. So that's the question. How to solve. So what we can do, we can split the problem into two parts. Okay, so let's talk about that. So what we can do, so again, how to solve. So what we can do, we can split the problem in two parts. We're going to do y double prime plus px y prime plus qx equals 0. We're going to get this part, and that's what we call the complementary problem. And then we're going to talk about the whole equation again, y prime plus qxy equal fx, the whole equation. What we're going to do from the first one, the homogeneous equation, we're going to find the general solution. So find the general solution of the homogeneous equation. Find the general solution. We know that this general solution you can write as, we're going to call this is the complementary solution. We're going to call YC. We know that the general solution of this one has the form C1 Y1 plus C2 Y2 for two solutions. So this one is what we normally call the complementary solution. That's why I put a C here. Complementary solution. And then from the other one, we find one solution. Find a particular solution. Find a particular solution, just one. Here we find a general solution. Here we find only one solution. So this solution, what we normally write as YP, because YP, that's the one solution, the particular solution. So this one is what we call the particular solution. And then the general solution of the non-homogeneous equation. So the general solution of the non-homogeneous Non-homogeneous equation is given by y is the sum of the two, yc plus yp, which is c1 y1 plus c2 y2 equal yp. And we know that how many conditions, how many unknown we need, how many c's we need, because this is a second order differential equation. That means we need two, and you can see that those are those two unknown. So this is the general solution with two unknown, and then we can find those c1 c2 using the initial conditions. Okay. So that's the form of the general solution of the second order non-homogeneous equation. Okay. To find yp, we're going to use the two methods. So let's talk about that. To find yp, we use two methods. The first one is the undetermined coefficient method. That we discuss later in the discussion, and then we also use the variation of parameters method. The problem is if you use the undetermined coefficient method, there are only three cases that we can do. There are only three cases. We can talk about those three later. But we can use the variation of parameters. In that case, the only problem is you might get an integral that you cannot do, then you're going to get stuck again. But otherwise, you can use that. Again, to find C1, C2, we use the initial conditions. Okay, that we normally do at the end. To find C1 and C2, use initial conditions. So we use the initial conditions at the end. So remember that. It's kind of joke, but that's how you remember. Initial conditions you use at the ends. Okay, so that's about that. And then we have this existence theorem for second non-homogeneous equations. So let's write that. So it's a theorem, existence and uniqueness theorem. So what it says that if P, Q, and F are continuous, on some interval, containing A, then y double prime plus px y prime plus qx y equal fx has a unique solution. That's very important. Has a unique solution satisfying ya equal b and y prime a equal b1 on that interval I. So what it says that if that's the a, so on this interval, this is the interval I. So on that interval, it says that there's a unique solution, because where is that interval coming from? Because that's where those three functions are continuous. So on that interval, there's a unique solution. So it's a very interesting result. Okay, so let's just do one last example from what we discussed so far. So two solutions of x double prime minus x prime minus 12x are given by 12x equals 0. equals 0 are given by x1 equal 2e negative 3t and x2 equal negative 5e4t, so that they are linearly independent, so that they are linearly independent. We can use a Wronskian test for that. y1, y2, not y1, y2, this is x1, x2. So we have x1 and x2. So it's x1, x2, x1 prime, x2 prime. So if you plug in 2e negative 3t, if you take the derivative, negative 6e negative 3t, and then we have negative 5e4t, so negative 20e4t. Let's take the determinant again, multiply this first and subtract that. So what do you get? If you multiply that one, you're going to get negative 4t e negative 3t times e to the 4t, and when you multiply the other one, you get positive, and again minus, because of it's AD minus BC, so you're going to get 30 e to the negative 3t times e to the 4t. When you multiply, you get negative 70 e to the t, which is not equal to 0 for any t. We only need one t, but so for any t it doesn't equal 0. So therefore x1, which is 2e negative 3t, and x2, which is negative 5e4t, are linearly independent. Good. So that's the proof. Very simple. So that's the about basics about the second order differential equations. Now let's move on to the reduction of order method. So in this we can talk about the reduction of order method. That's number 17. A reduction of order method. Reduction of order method. So what's going to happen? You start with a higher order differential equation, and you're going to bring one level down. So that means second order differential equation. You can write as a first order differential equation. That's the idea. That's like a reduction of order. Order go down. So how it works? One solution is given. Find the other solution. So that's the kind of idea. Find the other one given. So how it works? So let y1, which is not equal to 0, be a solution. Okay, that one we know. Okay, we know this. So we know this one. Now what we can do, we can assume a solution. So we can assume a second solution. Of the form y equal, that's the second solution, let's call it y2 equal the y1 solution times u. So u is unknown. That's the one we need to find. The unknown function. We're going to find that unknown function. So the goal is to find this. Okay, that's the starting point. We're going to assume a solution of the form y1 times u. Goal is to find u. Okay, goal is to find u. So the goal is to find u. Because after find u, then we know the second solution. Okay, but how we do it? We can start taking derivatives and then plug into the equation and then solve. So that's how we do it. So we can start with taking derivatives. So we have this one, and then we can take the find u. So what we can do, take derivatives. Take derivatives and substitute into our formula. So what is that? So differential equation is y double prime plus px y prime plus qx. So we're gonna qx y equals 0. So we're gonna plug in here. So we can take derivatives and plug in here. So let's see how it works now. So we have y2 equal y1u. So take derivatives. So that means y2 prime by the product rule. This can be y1 prime u plus u prime y1. That's what you get from the product rule. Now let's take the derivative again. So if you take the second derivative, y2 double prime, now we have 2, so you get 4 terms. So we can take the derivative. So this is y1 double prime u plus y1 prime u prime. From the other one, u double prime y1 plus u prime y1. Now you can see that you can combine these two and write one equation. So you can write this one as y1 double prime u plus 2 u prime y1 prime, and then we have u double prime y1. Good. Now what we can do, we can substitute this. Okay, because we know that this is a solution, since y2 is a solution of y prime px y double prime plus px y prime plus qx equals 0. We can substitute here, so we're going to get 0 equal we have y2 double prime plus px y2 prime plus qx y2. So let's plug in for each term. So what is y2 double prime? That is y1 double prime u plus 2 u prime y1 prime plus u double prime y1. That's the first one. It's coming from here. Now px times u2 prime. u2 prime means u1 y1 prime u plus u prime y1. It's coming from here. Now the other one, which is qx times y2, which is y1u. But we know that this whole thing equals 0. Now what we're going to do, we're going to kind of collect the terms in a different way, so that we can use the fact that y1 equals 0. y1 is a solution. So what we're trying to do, we can isolate the u terms. We're gonna go with the u double prime terms first. So what are the u double prime terms? U double prime, we have y1 u double prime. That means this term. Then we're going to go with the y prime terms. What are the y prime terms? Let's collect all the y prime terms. We have 2 y1 prime plus, that's that term. And then we have the other y prime. So this is another y prime term. So let's collect those two together. So we have px y1. So those two have a y prime term plus u prime terms. And then let's go with the u terms. What are the u terms? There's a u term here, there's a u term here, there's the other u term. Let's combine all of them and take u out as a factor. So you're going to get y1 double prime plus, from the second one, px y1 prime plus qx y1. That's what you get from the u terms, and then take u out. But we know that y1 is a solution. That's we know. That means this has to be 0 because y1 is a solution. So that means that term going to go away. So you simply end up with this expression. Y1 u double prime plus 2 times y1 prime plus p y1 u prime. That's what you have. So that means that has to be equal to 0 because that's equal to 0. That's how. So that's the whole argument. That's what we're gonna do. You're gonna assume a solution, take derivatives, and plug in, and you can see that there's a special term that's gonna go away because y1 is a solution, and then you simply end up with a new expression. So what we have now? So this is the interesting part. So we only have this one. So we have y1 u double prime plus 2 y1 prime plus px y1 times u prime equals 0. So that is the equation we end up with. Now the goal is to solve this for u. Solve for u. But you can see that there u prime is there, not u prime. So what we can do, we're going to make a reduction of order here. So what we're going to do, this is the whole point. So we're going to say let v equal u prime. If you say v equal u prime, since there's no u term here, then we have v prime equal u double prime. So what happened? Then we can rewrite the above equation in this form. So we can write the equation like this. We can say y1 v prime plus 2 y1 prime px y1 u prime means v equals 0. Now you can see that this is a first order linear equation. First order linear equation. So first we can divide by this term. Okay. If you divide by that term, because that we know that that's not equal to 0. So v prime plus, if you divide by that, you get what do you get? You get 2 y1 prime over y1 plus px, just px here, times v equals 0. So this is first order linear in v. This is first order linear in v. Now we can solve this. We can use the integrating factor method or some other techniques to solve this one, because this can even be because you can factor this. This can be separable. So depending on what is y1 looks like. So that means so the next step is solve for v first, and then solve for u, because after you solve for v, then we can use the fact that v equal u prime, you integrate one more, then you're gonna get solved for u. So that's the idea. Okay, so let's do the actual calculation in a problem, because what happened when you do a real problem, there are a lot of simplification going on, so it won't be this lengthy when you do the actual problem. So let's do a problem. So, and also I'm going to give you the formula for that, so you can use that formula in the exam. But this is just a method if you want to do something later. Okay, good. So let's do this one. So it is given that y1 equal x squared is a solution of x squared y double prime minus 3xy prime plus 4y equals 0. So we don't know how to solve this equation, but somehow you can use a trial and error argument or something. We know that this is a solution. The goal is to, what is the other solution? Find the other solution. Okay, so find the second solution, because there should be two solutions because it's the second order. Find the second solution. So that's the goal. Okay, so we can use the reduction forward argument. Okay, because we know that that's solution. So let's see the argument and completely solve this problem. Good. So the answer, assume a solution of the form y2 equals x squared u, because we know that's, so we don't write y1 x squared u. Now what we do, we take derivatives. Okay, so taking derivatives, we have y prime equal, use the product rule, so it is 2xu plus x squared u prime. We have second derivative in the equation, so that means we need the second derivative as well here. So if you do the second derivative, you get 2u plus 2xu prime from the first term. From the second term, you get 2xu prime plus x squared u double prime. So you can combine this, and you can write this one as 2u plus 4xu prime plus x squared u double prime. We combine these two. Okay, now since so actually this is y2, since y2 is a solution, so we can substitute that to the equation. Since y2 is solution, we can substitute the equation, so we're going to get x squared y2 double prime minus 3x y2 prime plus 4 y2 equal x squared times, let's substitute y2 prime, it is 2u plus 4x u prime plus x squared u double prime. This is simply coming from here, minus 3x y prime. Y prime means 3xu plus x squared u prime plus 4 y2. Y2 means x squared u, which is equal to 0, because that's the assumption. Because we assume there is a solution. Now let's see how it's going to simplify. You can see there are a lot of simplification going on here. There's a type also. This is not 3, this is 2. You can see that there are a lot of cancellations going on. Let's look at the x squared u term. So there's x squared u term here. This is x squared u term. And then we also x squared u term here. And you can see that those three get cancelled. So those three get cancelled out. because we have 2, 4 and -6, it's gone. So that means you only end up with just a few other terms. So you have so you're gonna get so what are you gonna get? You're gonna get there's x cubed term here. So this is an x cubed term because that's with x cubed term. There's another x cubed term here, so you're gonna combine those two x cubed term, and there's x fourth term. So this is x fourth term because there's x squared. So that means you have x cubed term and x fourth term. So this is gonna give you that x fourth u double prime plus x cube u prime equals 0. So that's what you get. Everything else get cancelled. Now what we can do is we can divide this by x fourth. So if you divide by x fourth, so we can divide by that term. So that this can be u double prime plus 1 over x u prime equals 0. Now what we can do, we can use a substitution. So we can say let v equal u prime. So let v equal u prime. Then we have v prime equal u double prime. So we can plug in. So our equation simply becomes v prime plus 1 over x v equals 0. So you can solve this problem using separable method or the integrating factors method. So you can use any method. So it depends on the problem. Sometimes you can do that, sometimes you can't do. But most of the time, yeah, so it's always like in this problem, you can use both of the techniques. So we can use the integrating factors for this one. It's kind of straightforward. So let's do that and finish the problem. So we have integrating factor I, which is the integral of p x dx. So it's integral of px. Px is 1 over x dx. So we have e ln x, and then e ln x cancel out. So you get x. So that's what you get. Now, from the theory, from the theory of integrating factors, we know that this side is simply the derivative. So you're going to get d over dx. The v times the integrating factor equal on the other side is 0. So integrating, integrating we have vx equal a constant, I'm going to call c1. So this says that v equal c1 over x. Now we're going to substitute for v, but v means u prime. So this says that u prime equal c1 over x. To get u, we can integrate. So u equal the integral of u prime, calc 1, so integral of c1 out, 1 over x dx. That means c1 ln x plus c2. But what you can do, you can ignore c2 because we are looking for one solution. We can even say c1 equal 1. So set c1 equal 1 and c2 equals 0 because we are looking just one solution here. So that means you're going to get u equal ln x. So x actually here you can say absolute value because we did not restrict only to positive x. So x can be positive or negative. So you can have ln x absolute value. So okay, so that means this is second solution. So then the second solution y2 equal x squared u, which is x squared ln x. So that's how you find the second solution using the reduction of order method. So it's not that difficult. What we did was we assume a solution of the form y1 u, substitute that. There's a nice simplification. You can see that there's there are a lot of simplifications, a lot of terms get cancelled out, and then you get a simple equation that you can solve using the separation of variable or integrating factors method. So now I'm going to give you the reduction of order formula. So you can directly use this formula if you get a problem like that. So the theorem, the reduction of order method. reduction of order formula. So let's say if y1x not equal to 0 is a solution of y double prime px y prime plus qx y equals 0. Remember, it has to be of this form. If it is not of this form, you have to bring it to this form. Okay, we need to isolate the px term. So sometimes you have something in front, so you have to divide by that first. Okay, so it's very important. It's a solution of this. Then another solution, another linearly independent. So this automatically linearly independent. Another linearly independent. Another linearly independent solution is given by y2x equal y1x integral of e to the negative px dx. That's why you need to know what the px, and divided by y1x whole thing squared, secant square y1 dx. So that is the formula. That's a reduction of order formula, and you can directly use that. So let's use that in a problem and see how the whole calculation works. So this is a problem of that type. So if it is given that y1 equal x is a solution of x squared y double prime minus x y prime plus y equals 0, find the general solution. So so that's going to find the general solution. That means it's a second order differential equation. That means there's another solution. So we're going to find the other solution using the integrating factor method. So the problem is, when you look at this one, this is not of the standard form. There's x squared term, so we have to divide by that. So we have x squared y double prime minus x y prime plus y equals 0. So what we can do, we can divide by x squared to bring it to standard form. Okay, so the standard form is, if you divide by that, you're going to get y double prime minus 1 over x y prime plus 1 over x squared y equal 0. So you can see where px is negative 1 over x. That's the px term. Okay, so you have to isolate the px term. Good. So then we can use the formula to find the second solution. The second solution is given by the formula. It is y2 equal y1 times e to the minus px dx over y1 squared dx. So let's plug in here. We have everything we know. So y1 is x, the integral of e to the minus px is a negative 1 over x dx over x squared dx. This you can simplify a little bit. So you get e to the 1 over x dx over x squared, and you can see that you cannot bring the x squared out because as you're still integrating inside. So from that you can see this is x. The top is simply e to the ln x over x squared dx. And then we know that when you have ELNX, ELNX, ELN cancel out, so you get x. So this is x times x over x squared dx. So this is simply 1 over x dx. 1 over x means ln x, so we're going to say x ln x. We are not going to add the c here. The reason is we are looking for one solution. Okay, so that's that. Now the next step is we need to show that these two are linearly independent. Okay, to show that they are linearly independent. Actually, if you remember the theory, it says that these are another linear independent solution. So either you say that linear independent solution by the theorem, or you can just prove this. This is not that difficult. Yeah, so that solution is automatically linearly independent. The solution that we get, we can prove that using this formula. But it's also not that difficult to show that. So let's plug in here and see what happens. This is x. Derivative of x is 1. We have x ln x. Derivative of that is use the product rule. So you get ln x plus x times 1 over x, even in this case. So let's simplify. When you simplify, what happens? You're going to multiply. So what do you get here? You get x 1 x ln x ln x plus 1. That's what you get. So we can multiply through. When you multiply through, what do you get? You get x ln x plus x minus x ln x. That's what you get. You can see these two get cancelled. So you get x, which is not equal to 0 in general. Wait, x can be anything other than 0. So that means, yes, not equal to 0. So they are linearly independent. So y1 equal x and y2 equal x ln x are linearly independent. Good. Therefore, the general solution is, because in the theory we know that those two solutions has to be linearly independent to find the general solution, otherwise it's not going to be. So therefore the general solution is given by y equal c1 y1 plus c2 y2 equal c1 x plus c2 x ln x. So that's the general solution. So that's how the reduction of order method works. So it's very interesting and not that bad. Okay, so if you have a problem like that, you can directly use the reduction of order formula. Okay, let's move on to the most important topic. So what's the most important topic? The constant coefficient differential equations. So number 18 is the most important one. The constant coefficient second order constant coefficient second order differential equation. Good. So this kind of equation has this form. So it has the form a constant times y double prime, another constant time y prime, another constant time y equals 0, equal to the homogeneous equation, and then we know that a, b, and c are constants. That's the case we trying to understand. So that is the case, very special case. Good. Now what we can do, how to solve this one? what we did, we assume a solution of the form y equal e to the lambda. So that's how the solution work. So assume a solution of the form y equal e to the lambda, and then what we can do, we can take the derivatives of that and plug in. We assume a solution of the form, and then we can take the derivatives. Okay, so take derivatives, so we're going to get y prime, which is lambda is a constant, so it's a lambda e lambda, and then we can take another derivative, double prime, so we can take lambda squared e to the lambda. Okay, so we know how to take derivatives like that. Oh, actually, it's not e to the it's lambda t, it's not just lambda. So e to the lambda is a constant, it's not a function, it's just a function, it's a constant for e to the e lambda t. And then also here, so t and t. Okay, good. Yeah, so we assume a solution of the form and take the derivatives. So y equal e to the lambda t. Now we're going to substitute this in the equation. So let's do that. Substitute. So if you substitute, you're going to get a lambda squared e to the lambda t, that's the first one, plus the second term b, a lambda e to the lambda t, that's for y prime, because this is y double prime, this is y prime, plus c e lambda t equals 0, this is y. So we're going to substitute for 3. Now you can see that e lambda t is common, so you can take it out as a factor. So if you take as a factor, you're going to get a lambda squared plus b lambda plus c equals 0 for any t. But we know that e to the lambda t never becomes 0, since e lambda t not equal to 0, the only option that this can be 0 is a lambda squared plus b lambda plus c equals 0. This is what we call the characteristic equation of the differential equation, because this has to be satisfied if e lambda t is a solution. Okay, so this is what we call the characteristic equation. Characteristic equation. Good, and you can directly write this equation. So what happens when there's a derivative? It's a second derivative, you get lambda squared. It's a first derivative, you get lambda 1. There's no derivative, you get lambda 0, that means constant. So you can directly write, you don't want to show this work here. You can directly write the characteristic equation if you have a problem like that. Okay, then let's write this important theorem. So what it says that, okay, so the theorem. So consider the differential equation a y double prime plus by prime plus cy equals 0, where a, b, c constant with, okay, so yeah, and then the characteristic equation, then the characteristic equation we call Char equation. Characteristic equation is simply a lambda squared plus b lambda plus c equals 0. So you simply replace the derivative terms by lambda powers. So see what happens. Is there a connection? Y double prime lambda squared, y1 prime lambda 1 power. There are no derivatives or no lambda powers. It's lambda 0 powers. Okay. Now we can write the general solution for this one in these 3 forms. So let's write them separately. So the general solution has the form and let's say and the general solution. And the general solution has the form, let's try it one by one. So there are three cases to consider because this is a quadratic equation. So it can be, so there can be two real roots, distinct real roots, equal real roots, or complex roots. So we have three cases. So if b squared minus 4ac positive, then what happened? The lambda 1 and lambda 2 are real distinct roots. So the general solution has this form: y equal c1 e lambda 1x plus c2 e lambda 2x in that case. The second case, if b squared minus 4ac equals 0, then what happened? Lambda 1 equals lambda 2. Then what happened? This is a real repeated situation, real and repeated, real repeated. So the solution has the form c1 plus c2x times one of those terms, lambda 1x, or you can expand it and write it like that: c1 e lambda 1x plus c2x e lambda 1x. You can write it like that. It doesn't matter which form. Okay. And the third case, if the b squared minus 4ac negative, now what happened? Your lambda can be written as alpha plus or minus a beta I, complex conjugate. This is what we call the complex conjugate situation. Complex conjugate. So in that case, what will happen? Your y has the form c1 e alpha x cosine beta x plus c2 e alpha x sine beta x. So that's what happened in that case. We have a cosine and a sine term. So those are the three cases that we want to remember. So again, what happened in the first case? You get real distinct, real repeated, and then complex conjugate. And you can directly use the result. So let's see this in a problem or two. So let's look at this problem. Find the general solution of let's say a 2y double prime minus y prime plus 3y equals 0. So if you get a problem like that, the first thing is we look at the characteristic equation. So the characteristic equation is simply 2 lambda squared minus lambda plus 3 equals 0. This is very easy to find factors. So what are the factors? 2 times 6, so you have 6. You're going to write this as a product with the when you add the 2, you get negative 1. So that means it has to be negative 3 and 2. So that means your factors are 2 lambda and lambda. Now to find the number, so you know that 2. So how to get this number? You simply divide that 2 by this 2. So that means it is plus 1. And for the other number, you divide negative 3 with 1. So that means negative 3. So those are the two numbers you get. And if you don't know how to do that, then you can look at the factoring polynomial video, and I explain all different type of polynomials in there: quadratic, cubic, quintic, quartic, all of them. So that's a video that you can watch. Okay, good. So then we have the two roots. So then you can see. So then you're gonna set them equal 0. So you're gonna get lambda equal -1 and lambda equal 3/2. You set them equal to 0 and get the two values. If you want, I can write that step as well. So what we normally do is after that, so you're going to set them equal. So then we have 2 lambda minus 3 equals 0, or lambda plus 1 equals 0. So this says that if you bring this to the other side, 3, and divide by 2, this says that lambda equal 3/2, or lambda equal -1. So it's not an and. We don't know whether we need both. Good. So those are two solutions of lambda. So the general solution is given by y equal, according to theory, it is C1 e lambda 1 t plus C2 e lambda 2t. So let's plug in the two values. So it is e C1. I normally put the smaller one first. It's a -1, so negative t, plus C2 e, the larger one, 3/2 t. So that is the general solution of the differential equation. Very simple. So let's look at one from the other type. And here I pick the independent variable as x, as t. So it's just up to you. Be careful when you use that. Here you can pick x or t because I did not say anything. Okay. Good. Let's do the next example. So problem number B. So we have 4x double prime minus 4x prime plus x equals 0. And you can definitely cannot pick x as the independent variable now because that is the dependent variable. Okay, so the characteristic equation is 4 lambda squared minus 4 lambda plus 1 equals 0. How to factor this? You can see that this is 2 lambda squared minus 2 times 2 lambda plus 1 squared. So this is a complete factorization problem because we know that we have formula. If you have a squared minus 2ab plus b squared, this is simply a minus b whole thing squared. That's exactly what we have here. So that means this is simply 2 lambda minus 1 whole thing squared. Yeah, you can see this again in the factor polynomial video. Good. So we have that. Now what we can do, we can set this equal to 0. So we have 2 lambda minus 1 equals 0. This says that lambda equal 1/2. Why? Bring 1 to the other side, divide by 2. And then also is repeats because, or you can say with multiplicity 2. With multiplicity 2 because it's a repeat, you can see it's square. Good. Now so we're gonna get the solution, so the general solution. So then the general solution is y equals C1 plus C2. Here variable, your independent variable has to be t because you can pick x there. So t times e to the lambda 1 t because it's a repetition. So that means C1 plus C2 e, nope, C2 t e to the 1/2 t. So that's the solution. C1, C2 constants. So let's do a last one from the other type, the complex type. So let's say y double prime minus y prime plus y equals 0. Again, the characteristic equation is lambda squared minus lambda plus 1 equals 0. You can see that you can find factors of this one, so you have to use the formula, quadratic formula, so which is lambda negative b plus or minus b squared minus 4ac square root over 2a. So let's plug in here. So you get 1 plus or minus 1 minus 4ac. So that's what you get over 2a means 2. So which is 1 plus or minus negative 3 square root over t. You need complex numbers for that. So that's going to be square root 3i. So this says that, so we have lambda equal 1 plus or minus square root 3i over 2. If you separate this, you can write this one as 1/2 plus or minus square root 3i over square root 3 over 2i. So you can see that that is the alpha value and that is the beta value. So the general solution is, general solution is given by y. Let's say x is the independent variable, e alpha x times c1 cos beta x plus c2 sin beta x. So that is the format. So we're going to plug in here. So it is e 1/2 x times c1 cos square root 3 over 2 x plus c2 sine square root 3 over 2x. So that is the general solution with c1, c2 unknown. And now what we can do is we can completely solve a problem with initial conditions as well, and to see how it works as the last problem of this type. So let's do that. So solve the initial value problem x double prime plus x prime plus 3x equals 0 with x0 equals 0 and x prime 0 equal 22. And later we're going to solve this exact same problem using the Laplace transform method, and you can see how it works. Okay, but right now we're going to use the constant coefficient differential equation technique, because that's much easier. So let's do that. Okay, so the answer, we can look at the characteristic equation, so which is lambda squared plus lambda plus 3 equals 0. And then you can see it's impossible to find the factors, so we're going to go with lambda equal formula, negative b plus or minus b squared minus 4, a is 1, so c over 2. So we can simplify this in negative 1 plus or minus negative 11. So negative 11 square root over 2. If you split this, you can write this as negative 1/2 plus or minus square root 11 over 2i. So so that's the alpha value. This is the beta value. So we have the alpha value and the beta value. So the general solution, so the general solution you can write as xt, which is c1 e to the alpha value t. So let's say it's a function of t, independent variable is t, and then we have cosine beta, which is square root 11 over 2t plus c2 e to the negative half t sine square root 11 over 2t. So that is the general solution. You get general solution in 3 lines. Now only thing what we have to do is to find C1, C2 using the initial conditions. So let's do that. So we can use the initial conditions. So using the initial condition, first x0 equal 0, we have 0 equal x to the 0. That means plug in 0 wherever you see t. So c1 e to the 0 cosine 0 plus c2 e to the 0 sine 0. So this says that this is equal to 0. This is equals to 1. This is, we know that this is 1. Sorry, this is 1, and this also 1. So that means you simply end up with, what do you get? C1. So this says that C1 equals 0. So that means your solution kind of simplified because you don't need the C1 term. So that means you have, so thus we can write xt like this. It is simply c2 e to the negative 1/2 t sine square root 13 over 2t. So before you take the derivative, it's a good idea to do this because then you have only one term. Otherwise, like, it will be difficult. So now what we can do is we can take the derivative. So taking derivatives, taking a derivative. So we can use a product rule here. So we have x prime t equal, so take the derivative of the first term. So you get 1/2 negative 1/2 c2 e to the negative 1/2 t, no change to this term, plus, now you take the derivative of the other term. So that means sine. So by the chain rule, square root 2, square 11 over 2 comes out. We have c2 e to the negative 1/2 t, sine become cosine square root 11 over 2t. That's what you get. Now we'll apply the condition. So x prime 0 equal 22 gives 22 equal negative 1/2 c2 e to the 0 sine 0 plus square root 11 over 2 c2 e to the 0 cosine 0. That means, as before, this is gone, this is 1, so you're gonna get, what do you get? You're gonna get square root 11 over 2 c2. So that's gonna give you the c2 value. So this says that c2 equal 44 over square root 11. In other words, 4 square root 11. Okay, that's c2 value. So therefore we have the solution now. We have xt, which is 4 square root 11 e to the negative 1/2 t sine square root 11 over 2t. Yeah, so that's the solution. So let's talk about something more about this one. You can see that in this problem, this is a periodic function. We have sine term, that means a periodic function, but you can see the amplitude. That's the amplitude, that's what we call envelope. That's going to decrease because that's an e negative term. So that's going to decrease. So that means if you look at the graph of this one, this is very interesting. So, so if you graph this function, this is how it looks like. So we have what we call this envelope curve, e to the negative 1/2 t, that's envelope. So that's gonna decrease. So it's gonna go like that. And then it's a sign that means plus minus. So what we normally do is we're gonna reflect it like that. So what's gonna happen now? we're gonna graph the sine function inside, because when you have t equals 0, it's a 0. So that means you can start 0 at 0 and just the sine graph between these two envelope. That's exactly what happened in this kind of situations. So this is simply, this curve is simply 4 square root 11 e to the negative 1/2 t. That's that curve. This is exactly the opposite of that. This is the negative 4 square root 11 e to the negative 1/2 t. So these kind of situations are like kind of common, like, you know, if you have like a bob hang like that and put like a sudden force, like impulse, then it's gonna go in a, like a motion like this. It's gonna go to this corner and to that corner. So what's gonna happen, because of the air resistance, the this gonna slow down. So that means if you look at the graph of this one, if you graph it, this is exactly what you get. It's gonna start here, it's gonna get a sudden jump because the impulse, and then it's gonna slow down and gonna go and stop like that. So that's the situation. So this is the solution you get using differential equations. So that's a kind of nice idea. Okay, so that's about the constant coefficient differential equations and how to solve it. There are 3 cases, and we talk about those 3 cases. In the next, we're going to talk about another special case, what we call the Cauchy-Euler differential equation. So in this, let's learn how to solve the Cauchy-Euler differential equation. So this is number 19, Cauchy-Euler a differential equation. Some people call it Euler-Cauchy, same things, CE equation. So a Cauchy-Euler equation has this form. So it is a x squared y double prime plus b x y prime plus c y equals 0. So that's the format. It's also second order homogeneous differential equation and also linear equation, because x is the independent variable. So x is the independent variable. So that means this is still linear. So how to solve it? We can assume a solution of the form. Assume a solution of the form. Assume a solution of the form y equal x to the lambda power, and then what we try and do, we're gonna take the derivative and plug in there and solve for lambda. That's how we do. And solve for lambda. So that's the kind of idea. So once you do that, what's gonna happen? Because we're looking for 2 solutions. So let's say if they are lambda 1, which is not equal to lambda 2, then the solution is simply y equal c1 x lambda 1 plus c2 x lambda 2. So that's the kind of idea. So let's look at a problem and see how it works. So example, solve x double prime x squared y double prime minus 3x y prime minus 5y equals 0 for x positive. So let's say x positive. So how it works? So we can assume a solution. So assume a solution of the form y equal x lambda. Then what happens? We take the derivative, so y prime, which is if you take the derivative, so lambda x lambda minus 1 just by the power rule, and then y double prime, we take one more, so it is lambda minus 1 x to the lambda minus 2. Now what we can do, we can substitute that. Okay, so we substitute that. Substitute. So once you substitute, what happens? You have x squared and then y prime, y double prime, which is lambda, lambda minus 1, x lambda minus 2 minus 3x, lambda prime term, y prime term, which is x, no, lambda x lambda minus 1, and then minus 5 y term. So those are the three terms. So again, so this is the y double prime term, this is y prime term, and this is the y term. So those are three terms, and you can see that you can simplify this. You get x to the lambda in each term, so we can take it out. So you're gonna get lambda times lambda minus 1 minus 3 lambda minus 5 x to the lambda equals 0. But we know that x to the lambda is never 0 because x not equal to 0. So that means only thing should happen is the whatever inside the bracket has to be 0. But you can see if you simplify that, you're going to get lambda squared. You get minus lambda minus 4 lambda minus 5 equal to 0. That's what you get. So this is very easy to solve. So we're going to look at the factors. So what are the factors? You can see lambda minus 5 and lambda plus 1 are the factors. So this can give you lambda equal minus 1 and 5. So the general solution, so the general solution is y equal c1 x to the lambda 1 x, lambda 1 not x, lambda 1 plus c2 x to the lambda 2. So we're going to plug in that. So the c1 x to the minus 1 plus c2 x to the 5. If you rewrite it, we bring x down. So you can write this one as c1 over x plus c2 x to the 5. This is 4x positive. Good. So that's a solution. So it's not that difficult. So we solve for, we assume a solution of x to the lambda, take derivatives and plug in, solve for lambda. So let's discuss another method. What we're trying to do here is we're going to transform the problem to another domain, another variable. So another method. So we can transform the problem. So let's say for x positive, what we're going to do, we're going to let x equal e to the t. So we're going to transform the problem to the t variable. Now what's going to happen, you can show that. So I'm going to skip that, the how it works. You can look at the video, general video for that. So then what happens, once you do that, you can transform the variable x to t variable. Okay, so what happened now in variable t, the differential equation becomes a y double prime t plus b minus a y prime, again the variable t, plus c y t equals 0. You can see that this is a constant coefficient differential equation, and we know how to solve this. So that's the idea. So we transform the Euler-Cauchy equation to a constant coefficient differential equation by this special transformation. So this is for x positive. If we x negative, we can say x equal negative e to the t. The interesting thing is you get the exact same equation even in that case. Very interesting. So now this is constant coefficient. So this is a constant coefficient. This is a constant coefficient equation, and we know how to solve that. So we can look at the characteristic equation: a lambda squared plus b minus a lambda plus c equals 0. That's what you get. So that's the characteristic equation for the Cauchy-Euler under the new transformation. Now, if you know these values, then we know the solutions, because in the t variable, what you want to do is you can transform the variable back. So so this is the characteristic equation, and you can see this is quadratic in lambda. So this is quadratic in lambda. Again, this is quadratic in lambda. That means there are two solutions. Okay, so let's talk about the separate cases, and also you can see how the transformation works. So we can talk about that. So let's go one by one. If b minus a squared minus 4ac, that's the discriminant for this. If it is positive, there are two solutions. So these have two solutions. So if you call them R1, R2, R1 and R2, those are two numbers you get. So this is real distinct situation. So your solution y equal, in the t variable, it is C1 e R1t plus C2 e R2t. Now what we're going to do, we're going to transform this to x, but we know this transformation in the equivalent transformation. So what we have x equal e to the t, if and only if t is simply ln x. So that's the transformation that we can use, because the exponential you can write as a log like that. So t is ln x. So let's use that. That means e to the t is simply x. So if you replace that, then this simply you can write this one as c1 e to the t is x, so it's become x to the r1. Same thing, e to the t is x, so this becomes c2 x to the r2. So that's the idea. And why? This is algebra, because if you have e r1 t, you can write as e to the t r1. That means x r1. So that's what happened. Just basic algebra. So you get the solution in x. Okay, so that means you solve the new characteristic equation. This is the characteristic equation for the Cauchy-Euler equation, and then after you get that, those values, whatever the values, simply gonna go here r1 and as r1 r2. So very simple, but you have a new characteristic equation. That's the only thing you remember. That's the first case. And the second case, if b minus a squared minus 4ac equals 0, what's going to happen? You're going to get 2 equal. So you're going to get r1 equal r2, a real repeated. In this case, we know how the solution in the t variable, it has to be c1 plus c2t e to the r1t. Now again the same argument, c1 plus c2. What is t? T equal ln x. So now put the ln x here. And then e, this is again as before, x to the, this simply become x to the r1 as before. That's the second case. And the third case, if b minus a squared minus 4ac negative, then we have as before, r is complex, so alpha plus or minus I beta. Then we can write so as a complex conjugate situation. So we can write the solution in the new t variable. So in the t variable, the solution looks like e alpha t c1 cosine beta t plus c2 sine beta t. But what you want to do is you want to write this one using the new variable. So with the new variable, you're going to get e t is x, so it's x to the alpha as before. C1 cosine, no change, beta t is ln x. So x is positive, so you don't need the absolute sign here. Plus the same thing, C2 sine beta ln x. So that's the those are three solutions. So what do you want to do? Once you get the Cauchy-Euler equation, look at the new characteristic equation, find the values, the lambda values, lambda 1, lambda 2. We just call it R because just to remember the difference. And then after you get that, you simply get the three solutions. Okay, so that's the first solution. Just put the new values there, and the new values in the last equation, which is a little long. Good. So those are three cases. So this is for x positive, but we can show that. So I'm going to write that just for your knowledge and for the future, for the exam. We can say in k. So we can see it can be shown that. Let's write it. It can be shown that. It can be shown that for x equal negative e to the t, that's the other case. That means x is negative. We get the exact same characteristic equation. We get the same characteristic equation. That's very interesting. We get the same characteristic equation. So the general solution, for x not equal to 0. So what you want to do, we want to consider the positive case and the negative case. So instead of x, we put absolute value. So that means the three cases are if b minus a squared minus 4ac positive, then the solution is y, c1, not just x, the absolute x, because it can be positive or negative, r1, because we don't know whether those are integers, so be careful, and then c2 x r2, so it has the both positive and negative case. Only thing is you include the absolute sign. And the next one is if b minus a squared minus 4ac exactly equal to 0. In that case, y equal c1 plus c2 ln absolute value of x times absolute value of x r1. That's the common r1 solution. The third case is if b minus a minus 4ac negative. In that case, what happened? We have alpha beta. So that means your solution is simply, I don't think I have enough space here. Yeah, let's write it. So it is x to the alpha times c1 cosine beta ln x plus c2 sine beta ln x. So that's the general case for any x other than 0. So let's just solve one equation, one problem to see how it works. So say solve x double prime x squared y double prime minus 2 x y prime minus 4y equals 0 for positive x. So the answer, the characteristic equation is, so in this case a equal 1. So we can see and write them. A equal 1, b equal negative 2, c equal -4. So the characteristic equation is simply lambda squared plus minus b minus 1 lambda minus 4 equals 0. So this says that lambda is squared minus 3 lambda minus 4 equals 0. So the you get -4 and 1. So this says that lambda equal -1 and 4. So real distinct, real distinct. So that means the general solution y equals c1 x -1 plus c2 x 4, or if you divide c1 over x plus c2 x to the 4th power. So that is the complete solution. So you can see it's not that difficult, but you have a new characteristic equation. So it is not lambda squared, a lambda squared plus b lambda plus c. It is a lambda squared b minus a lambda plus c. Okay, good. So that's about the characteristic Cauchy-Euler equations. So let's move on to the higher order differential equations. We just talk about the basics of that, and then we're going to move on to the non-homogeneous equation and undetermined coefficient method. So let's talk about a little bit about the higher order differential equation. So this is topic 20, higher order constant coefficient differential equation. So it's very important. We do the constant coefficient only in this one. So those equations have this form: a y n power b y, not the power, derivative n minus first derivative, like that. We have a first derivative and a constant not a constant term, dy term is equal to 0. It's a homogeneous. So we can look at the homogeneous case. Good. Same idea. We can assume a solution of the form. Assume a solution of the form y equal e lambda t. Then we get the characteristic equation as before. So the characteristic equation is a lambda n power b lambda n minus first power, like that. So you get c lambda plus d equals 0. So that's the characteristic equation. Now what we're going to do, we're going to factor this, get the numbers, and plug. So we're going to factor this. Okay, so we're going to factor this. So there are a few cases. So let's go case by case. So we have cases. So the first one is if all lambdas are real and distinct. That's the most common case. So what's happened? Just an extension of what we learned. So the C1 E lambda 1, if you use the x as the independent variable like that, C2 E lambda 2x, like that, Cn E lambda nx. So that's what happened in the distinct case. So let's look at the repeated case. Very similar. So the case 2, let's say if lambda 1 repeats m times. Lambda 1 repeats m times and the rest are distinct. the others are distinct. If that is the case, then what happened? Why? So this is just extension of what we have, because when we have 2, we have C1 plus C2x. So if you have m, you're going to go m minus 1. Okay, that's the idea. So that means C1, C2x, like that. We continue that. And then we have Cm, m term has the power m minus 1. And then we have, this is similar, so L lambda 1x plus the rest we know. I just put some numbers, so let's say d e to the next lambda value, just repeat, and then the last lambda value, lambda n x, like that. Okay, so the interesting part is here, how we can write that term. You can see if it is a m repeats, you're going to see m minus 1. If it is 2, you're going to see x. So like that. Okay, and then the last case is the complex case. So let's say if coefficients are real, so it's very important. Coefficients are real. If the coefficients are real, then we have complex conjugate roots. Then we have complex conjugates always. Complex conjugate roots. If the coefficients are real, the solution has to be complex conjugate. That's like theory we prove in algebra. Complex conjugate, let's say complex conjugate pairs. Let's write that. Complex conjugate pairs. So let's say lambda equal alpha plus or minus I beta. The whole thing, because we go with pairs, okay? Repeats m times. This thing can repeat m times, and others are distinct. Others are distinct. So in that case, what's going to happen? Y is simply C1 plus the same thing, C2x, like that. So we have Cm x m minus 1. That's the coefficient of E alpha x cosine beta x, plus a similar term for sine. So we have d1 plus d2x, like that, dm x m minus 1 E alpha x sine beta x, and then plus the other terms, all the non-equals. But see the format. So we have 2 there. So that means we already have 2m off, okay, because there are 2m many terms, and then the rest is n minus 2m many terms are there, and that's going to follow the other pattern. Okay, so that's the idea. And then let's talk about the linear independence. Linear independence is very similar. So we can write the Wronskian. So for example, if we have 3 functions, so we can extend that to many, but let's just for 3. So we have the Wronskian, so it's going to be y1, y2, y3. Take the first derivative. So this is 3. Take the first derivative and take the second derivative. So that's a Wronskian. And then if this is not equal to 0 in general, for some x0, the functions are, then this implies that y1, y2, and y3 are linearly independent. Okay, so that's the kind of idea. So very similar. So as an exercise, you can try this. You can see the detail in the actual lecture. So for example, show that 1 sin x cosine x, these three functions are linearly independent. And we already know that this is one of the common linear independent set. We discussed that earlier. So just prove it. And you can see that this is very easy because 1 is there. Once you take the first derivative is 0, second derivative is also 0. So that means the determinant of the 3 by 3 matrix is very easy. If you write the cofactor expansion, you only need 1 times 2 by 2. So it's just one term. So it's very easy. Okay, so you can try that. Let's do like a regular problem. So how about this one? Find the general solution of 2y triple prime plus y double prime plus y equals 0. Something like that. So it's a third order differential equation. Now what we can do, same argument. We can look at the characteristic equation. So the answer, we can look at the characteristic equation. It's going to be 2 lambda cube plus lambda squared plus 1 equals 0. So this is what we get. So it's a cubic equation, and you can see that there are no 4 terms. That means grouping doesn't work for this problem. What we can do, we can use the factor theorem for that. Okay, so so let f lambda equal to lambda cube lambda squared plus, and if you are not familiar with how to find factors of the things like that, please look at the factor theorem video, and there I explain like many different type of problems, like in a quadratic, cubic, quartic, like order 4, and a quintic order 5, and even like order 8, 9, 10, like larger ones also. We basically use the factor theorem and then the lone division or the synthetic division. Normally we go for the synthetic division. We first use the factor theorem and then use the synthetic division. That's how we normally do it. So let's see how it works here. After we get that, now we can notice that and then let's say note that what we're going to do is we're going to try these values. We're going to try lambda equals 0, plus or minus 1, and plus or minus 2. We're going to try those values until you get a quadratic. That means you only need to find one value, because after that you can divide, then you can get the quadratic. So use the quadratic formula or factor. So we just need one value to find. So note that if negative 1, if you plug in the negative 1, what can happen? 2 negative 1 cube negative 1 cube plus negative 1 squared plus 1, how much you get? You get negative 2 plus 1 plus 1, which is 0. What does that mean? By the factor theorem, this means that, lambda plus 1 by plus 1, because it is minus 1, because the minus, we plug in the minus 1. So this is a factor theorem. So lambda plus 1 is a factor, or in other words, negative 1 is a 0. So now what we can do, we can use synthetic division to find the other one. So use synthetic division to find the other factor, So let's see how it works. In the synthetic division, we only use the coefficients. So the coefficients are 2 of the original polynomial, and then x cubed as a 2, and then 1. There's no lambda term, so that means you will put a 0 there, and then 1. So those are the coefficients. So we check negative 1, whether negative 1 is no. What we are doing is we want to get the quotient when you divide by lambda plus 1. So what we put here is the 0 corresponding 0, and you can see the lambda plus 1 means the 0 is -1. So that's the 0. So that's the one we're gonna use there. What we normally do is it's a very simple one. We copy that number first and then multiply and add. We're gonna multiply -1 with 2, so you get -2, put it there and add, so you get -1. Then multiply again with -1 and -1, so you get 1 and add, so you get there. Just add, multiply, add, and then -1 with 1, so you get -1, add, you get 0. That means good. That means it's completely divided. If you get a 0, that means it's completely divided. So that's the quotient. So we have the other factor right here. 2, -1, 1. Those are the coefficients. So that means the other factor is 2 lambda squared. Why? There are 3 terms. Minus lambda plus 1. So we get that. So that's the other factor. Now what we can do, so we're going to set that equal to 0 because we're looking for that. So we use, you can see whether you can factor, you can see that it's not easy to find factor. So we can use the quadratic formula. So let's use the quadratic formula. So we have 2 lambda squared minus lambda plus 1 equals 0. Lambda equal -1 is plus or minus 1 minus 4ac square root over 2a, that means 4. So let's simplify. You get plus 1 plus or minus, you get 1 minus 8, so that means -7 square root over 4. Using complex numbers, we can write this in as 1 over 4 plus or minus square root 7 over 4i. So that is the alpha, that is the beta. So we have alpha and beta. Now we can, it's a complex, so it's a complex conjugate. So complex conjugate means we can use the complex form. So the 3 roots are, so we can say thus, the 3 roots are lambda, one is -1 and the other one is 1/4 plus or minus square root 7 over 4i. And as before, the alpha and beta. So we write general solution. So the general solution, we can write, which is y equal c1 e to the -t plus. Let's write the form first. So what is the form actually? Because there's a one real and then complex. So that is c. We can write this one as c2 e to the alpha t cosine beta t plus c3 e to the alpha t sine beta t, and if you plug in that here, you're going to get c1 e to the minus t plus c2 e to the what's the alpha? 1/4. So 1/4 t cosine square root 7 over 4 t plus c3 e to the 1/4 t sine square root 7 over 4 t. So that is the solution of the third order differential equation. So we use quadratic equation, C in 3 division, factor theorem. So it's a nice problem. Okay, so this is the end of homogeneous equation. Now let's discuss how to solve the non-homogeneous equation. So let's talk about the next very important type. So this is the how to solve a non-homogeneous equation. So this is topic 21, solving non-homogeneous equation. Solving a non-homogeneous equations. So we can start with a problem like this: a y squared plus b y prime plus cy equal fx. This is again a constant coefficient situation. So with a constant coefficient. How we do, like when you get a problem like that, we're gonna split the problem. We're gonna consider the homogeneous part and the non-homogeneous part separately, like this. So from the homogeneous one, we find the general solution. So find the general solution, what we normally call the complementary solution. So this has the format YC as a complementary solution, C1 Y1 plus C2 Y2, C1 Y1 C2 Y2. So that's the general solution. And for the other one, we find one solution. So find a particular solution. Find a particular solution. We're going to call this YP. So just one solution. Just one solution. So we don't need many, only one solution. Now what we can do, after we know the particular, this is what we call the complementary solution. So this is called the complementary solution. And this is the particular solution. And then we can have the general solution. So the general solution is general solution to the non-homogeneous is given by y equal, we just add the two, yc plus yp. So you're going to get c1 y1 plus c2 y2 plus that one solution that we found. So this is what we do. We just need one solution and we add that to the general solution. Now the argument is, you know that the non-homogeneous equation is a second order differential equation. That means if you find the general solution, you need two constants. You can see these are the two constants. So everything looks good. So because second order, you need two unknown, two arbitrary constants. We have two arbitrary constants, C1 and C2. Okay, but YP is only one solution called the particular solution. Now, how to do this in reality? So what we do is we're going to use two techniques for that. We use two methods. To find YP, because we already know how to find YC. So the two methods are, first one is what we call the undetermined coefficient method. Undetermined coefficient method. And we also use the variation of parameters. Variation of parameters method. So the problem with the undetermined coefficient is you can only solve three type of problems. So problem with like a exponential function like that, and then sine cosine, and then the polynomials. So polynomial. Those are the only three types that you can solve using the undetermined coefficient method. So if you get something like secant, you cannot do using this method. Like natural log, you can do using this method. So there's a problem. So we need new technique. That's what we call the variation of parameters method. if you have something like that. Okay, so let's first talk about the undetermined coefficient method. This is a very powerful technique. So let's talk about that first. Undetermined coefficient method. Undetermined coefficient. So this is like simple idea. We kind of guess the solution and plug in and try to find those undetermined coefficients. So again, work for 3 cases only. Work for 3 cases only. That's the major problem. So we have a y double prime plus b y prime plus cy equal, let's say, fx. X is the independent variable. So it can be exponential function. That means if we have like 5 e to the 3x, we can handle that. Then we have the sine and cosine functions. For example, if we have 3 cosine 2x minus 4 sine x, we can do that. And you can see that this is 2, this is 1. That's okay. You can still do it. And the third case is the polynomials. So like 2x cubed minus x plus 1. We can also do that one. So those are 3 types that we can do: exponential, sine, cos, and polynomials. So what we normally do is the first step is guess the particular solution. Guess the form of yp. So that's what we do. We're gonna guess. We guess the form of yp. But there are certain criteria for that. So let's talk about that. We have so guess form of yp. So we're gonna follow this table. The first type, if we have a number times e to the beta x, beta is another number. So your yp, just a form of yp, gonna be a e to the beta x. The goal is to find b. Find a. Goal is to find a. That's the first type. The second type, there are 3 cases. It can be a something times cosine beta x, something times sine beta x, or let's say something times cosine beta x and another thing times another number times sine beta x. So here you see that the beta. So in this case, all these 3 has only one form. All these 3, if you see any of them, it's going to be simply a cosine beta x plus b sine beta x. Even if we have only one, like just cosine sine, we still need to have 2. The reason is when you take the derivative, it's going to change sine to cosine. So that's why we need to add both. So that's the second type. The third type is a polynomial type. So it is like nth degree polynomial. Nth degree polynomial. So you're gonna guess the form as say nth degree. So it's a n x n, and then a n minus 1 x n minus 1. Write all the terms until a constant. So write all the terms. Okay, all terms. You cannot miss anything. Okay, even though the actual function fx doesn't have that, we have to write all of them here. So write all terms. It's very important. Good. So that's the kind of idea. So let's talk about some special cases. So there are some special situations. For example, if beta the number beta is a root. It's a root of the characteristic equation of YC, the complementary solution, then YP has to be A. You have to add extra x in front, so that's very important, because if you do not add extra x in front, if beta is a solution, what will happen? A beta x is a solution, so it just disappears, it becomes 0, so you don't get anything. So that means you have to add a extra x, okay, to get a independent solution. To get an independent solution, so it's very important. You need that extra x there to get a independent solution. That happens when beta is a root. And then if beta is a repeated root, if let's say beta is a repeated root of the characteristic equation, then you need to have another x. So that means it has to be a, not just one x, you have one more x, so a x squared, a beta x. So that's what happens if it's a repeated root. You need to add one more to get an independent solution. And then the next one is, how about you're going to see a combination of the 2 or 3. So let's talk about that. So the next one is, if there's a combination, if there is a combination, if there's a combination of them, right, YP for each and combine, right, YP for each and combine. So for example, let's look at some examples. So let's say your fx looks like this, 3x minus 2e 4x, like that. So what we can do, you can see that there are two. There's a polynomial and an exponential function. What we can do, we're going to have both in here. So because of the first degree polynomial, you need a term like ax plus b is a first degree polynomial. That's for 3x. Plus, because of the exponential one, you have c e 4x. So we're going to write for each and combine like that. So you just write one expression combining both. So that's the idea. It's very simple. The next one is, how about we're going to see product and like all of them. For example, x e to the 4x plus sine 3x. So if you get something like that, now the yp looks like this. So we have x, that means a polynomial. So we write ax plus b for that. And then we have e to the 4x. But for e to the 4x, the general term looks like c e 4x. But there is something here, because a and b already contain c as a factor. So that means we are not going to write that c here. So we don't write that. We don't include that there because c already contained in a and b. So if you add a c, that's extra unknown. So that's going to make it difficult. So we are not going to write that. So we're going to remove that. That means without that, we can write like this. Just ax plus b e to the 4x, like that. So that argument always there. If it is already inside as a product, we don't need that extra one. So that's the first two. So it's going to take care of x and the e to the 4x. Now sine. The sine means in one term, but we know that you need to have sine and cosine both. So that means it's a c sine 3x plus d cosine 3x, because if you see one of them, you need to write both. Okay, so this automatically comes everything. Good. So that's the kind of idea. And then also, let's say you also have an extra term like minus cosine x. So that means this also going to introduce another 2. So that means if you have that, then what's going to happen? It is e. Again, sine, cosine, it doesn't matter. So write cosine, and also the sine version, f sine. So always go as pairs. Okay, so it's very important. Good. So that means so this is go with that, and this one go with that. So that's the idea. Okay, so I hope it's clear. Now what happened? The other one that we just discussed before. So let's say if you have a differential equation like this, let's say you have y double prime minus y prime minus 2 equal 3e2x. So if you look at this problem, so if you want to write the form for yp, let's look at it's always a good idea to look at the characteristic equation first. If you look at the characteristic equation, it is lambda squared minus lambda minus 2 equals 0. The factors are lambda minus 2 and lambda plus 1. So this says that lambda equal 2 and minus 1. You notice that these exactly match with that. So in that case, what's going to happen? Your yp has to include an extra x. So it is a x e to x. The reason is lambda already appear in the characteristic equation, because if you just have a e2x, it's not going to work. The reason is it's a solution. Since the solution, once you plug into the left side, it just gets 0. So you get 0 equal something non-zero. That's not possible. You can have 0 equal to non-zero. So because of that, to avoid that, we introduce that extra x to get an independent solution. Okay, so to get an independent solution, because we discussed that, because if you multiply by x, it's going to create a new independent solution. Okay, so that's the idea. So what we can do now is let's talk about the steps to solve a problem like that. So these are the steps to solve a problem using undetermined coefficient method. So steps. So the first step is always going to be find yc. The reason is then it's going to tell you whether the lambda is appeared in the characteristic equation. So we find yc first, at least the lambda values. That's the first step. The second step is guessing y. So you're going to guess. So guess yp. You guess yp. That's the second step. Third step, you can take derivatives. Take enough derivatives. What does that mean? If it's a second order differential equation, you need 2 derivatives. If it's a third order differential equation, you need 3 derivatives, like that. That's why I say enough. Okay, sufficient number of derivatives. Okay, so it's clear. And then what we're going to substitute into the equation. So substitute into the differential equation, the non-homogeneous one, and then we can equate the coefficient of linearly independent terms. So number 5, equate coefficients of linearly independent terms. Linearly independent terms. We're going to equate the coefficient of linearly independent terms, and then terms to find unknown coefficients. That's why we find unknown coefficient. find unknown coefficients, the undetermined coefficients. And then after we find that, write the general solution. Write the general solution in the form y equal yc plus yp. We can write that, and then last step is we can use initial conditions to find the c's appeared in yc. Okay, use initial conditions. That's the last step. Use initial conditions at the end to find C1 and C2. So that's we do at the end. So that's the last step. Initial one we use at the end. So okay, so those are the kind of steps to solve a problem using the undetermined coefficient method. So let's just do one example to cover all those things. Okay, let's do one example. Okay, so let's do this one. So example, solve the initial value problem y double prime minus y prime minus 2y equal, let's say, 6 plus 8 times e to the negative 2t minus 4 cosine 2t with y0 equals 0, y prime 0 equal 2. So this is a complete second order initial value problem, and with a complicated non-homogeneous term. Let's go step by step. The first step is find the characteristic equation. Okay, so the characteristic equation of the homogeneous equation y double prime minus y prime minus 2y equals 0 is simply lambda squared minus lambda minus 2 equals 0. The next step is factor. It's very easy to factor. So you're going to get lambda minus 2, lambda plus 1. This is going to give you the lambda values. Lambda equal minus 1 and 2. So we're going to the yc. So the yc equal c1 e to the negative t plus c2 e to the 2t. Okay. Now you can see that 2 and that one is different. So that means you don't need that extra t for this one. So we can write the yp. That's why we need that first to see whether that's the right form. So write yp. So yp is, let's go term by term. 6 is a constant. That means you can add a for that. And then that's the polynomial part. And then we have 8e, the exponential term. So that is b e negative 2t. And then we have sine cosine. So it's a cosine. So we're going to go c cosine 2t, and also you need to have the sine term. So that's the rule. Okay, good. Whether you have 2 or 1, you still need to add 2. The next step is take derivatives. So number 3, derivatives. So you can take derivatives. So we're going to get yp prime. So it's a 0. So you get the exponential function. When you have exponential function, when you take the derivative, that constant comes out, that we know. So that means it's going to be negative 2b e to the negative 2t. So that's what you get. From that, the constant comes out. And then this is a cosine. Cosine means when you take the derivative, it's going to be a negative sign. Also 2 comes out, so it is negative 2c sine 2t. This is a sine become cosine. 2 also comes out, so 2d cosine 2t. So that's what you can take the first derivative. Now take one more derivative because the equation is second order. So yp double prime. Another negative root comes out, so it becomes 4b e to the negative 2t. Sine become cosine, 2 comes out, so the negative 4c cosine 2t. Cosine becomes sine, so negative 4d sine 2t. So that's what you get. So we get all the derivatives now and yp. So we can substitute that into the equation. So let's do that. Step 4, substitute. Substitute into the equation. So let's do that. So y prime. So y double prime. So y double y. So we're going to put the y double prime term first. So if you want, you can repeat the equation here. So it is y double prime minus 2y equal ft. That's the function we have. So let's put that. So y double prime terms first. So it is 4b e to the negative 2t my negative 4c cosine 2t minus 4d sine 2t. So that is the y prime term. Now we're going to go with the first derivative term. It's a minus. You're going to get negative 2b e to the negative 2t negative 2c sine 2t plus 2d cosine 2t, and then the y term, which is negative 2 times the y term, which is a, that's the longest term, 2e negative 2t plus c cosine 2t plus d sine 2t, which is equals to the ft, which is 6 plus 8 minus 2t minus 4 cosine 2t. Good. So that's the expression we get. Now what we can do, we can equate the coefficients of linearly independent terms. So what are the linearly independent terms you can see here? We have a constant, which is a linearly independent term, and then we have exponential function, which is linearly independent. We have sine, which is linearly independent. We have cosine, which is also linearly independent. So those are the 4 terms that we have here, which are linearly independent. So step 5, equate coefficients of linearly independent terms. So we start with the first term. We will start with the constant term. So we start with the constant term. What are the constant terms we have? You're going to see a is a constant, and that's the only term we have. And then other side 6. So we're going to equate those two. So we have negative 2a equals 6. This directly going to give a. A has to be negative 3. So we all know the a value. Same thing. Let's go to exponential function next. So e to the negative 2t. So you equate the coefficient of that. That's also linear independent term. So let's start with that. So you can see we have that e to the negative 2t, and then we have this one, and we have that one, and on the other side we have this. So those are the 4 terms that we have. So 3 on this side, 3 on the other side. So we have 4b, and then we have negative negative positives 2b, and then we have negative 2b, good, and then equal on the other side we have 8. So how this simplifies, you can see this and that get cancels, so you will get 4b equal 8. In other words, b equal 2. So we already know a, we already know b. Now the only thing that we need to do is find the coefficient of sine and cosine. So let's go with one of them. So let's go with cosine 2t. They are also linear independent. So if you go with that, we have cosine term here, we have cosine term there, and then this. Those are the 4 terms. So let's go with one by one. So the first one is negative 4c. The next one is negative 2d. The next one is negative 2c. Those are all the terms on the left side equal the right side negative 4. See whether you can simplify this a little. So you can see negative 4c, negative 6c, so negative 6c minus 2d equal negative 4. What we can do is we can divide this sum by negative 2. If we divide this sum by negative 2, you're going to get equation 3c plus d equal 2. So I'm going to call this equation number 1. Now what we can do, we're going to create a similar equation for sine 2t and solve the 2. So let's see what you're going to get for sine. For sine, we have sine 2t. We're going to get negative 4d and then plus 2c minus 2d equals 0. With there's no sine term on the side. This simplifies to negative 6d plus 2c equals 0. And if you divide this by, okay, I'm going to write it here. So this is going to give you negative 6d plus 2c equals 0. If you divide by 2, you're going to get c minus 3d equals 0. I'm going to call this equation number 2. Now what we're trying to do, we can simply get rid of d term by, so I'm going to multiply the first equation by 3 and add to the second equation. When you do that, you're going to get 9c plus c minus plus 3d minus 3d, which is equal to 6, and you can see this gets cancelled out. So you will get the value of c. So 10c equals 6. It says that c equals 6 over 10, in other words 3 over 5. And then we can use the second equation. So d is 1/3 of that. So this says that d equals 1/3 of c, which is 1/5. So we find the two values. Now we can write the general solution. So thus the yp, or the general solution, yp is negative 3 plus 2 e to the negative 2t plus 3/5 cosine 2t plus 1/5 sine 2t. So we get all the terms. Now what we can do, we can write the general solution. So number 6, the general solution. So the general solution is y equal yc plus yp. So you can substitute is c1 e to the minus t plus c2 e to the 2t and then minus 3, let's add them, plus 2e minus 2t plus 3/5 cosine 2t plus 1/5 sine 2t. So in the exam, like, you know, you're not going to get a question like this long, but here I'm telling you, like, you can manage all of them together, but you will get like 1 or 2 terms, not like a lot like that. Okay, now the last step is, now we can use the initial condition to find c1 and c2. So you can see that the only thing that we don't know is c1 and c2. To find that, we can use the initial conditions. So initial conditions we use at the end. That's what you remember. So the step 7, using the initial conditions, we have y0, so 0, which is y0, that means you plug in 0 for all the t's, so you're going to get, so what are you going to get? So let's write a separate equation for that. Yeah, I'm gonna write it like that. So it's much easier like that. Using initial condition y0 equals 0, we have 0 equals c1 plus c2 minus 3 plus 2e0 plus 3/5 cosine 0 plus 1/5 sine 0. Now we know that sine 0 is 0, cosine 0 is 1, e0 is also 1, so this is going to give you an equation. So what equation you're going to get? You're going to get 0 equals c1 plus c2. C2 we have, what do we have? We have minus 3, and also we have minus 3, and we have 2 here, so it's a minus 1 plus 3/5, that means minus 2/5. That's what you get. So I'm going to call this equation number 3 because we already have 1 and 2. Now the same thing, let's try to use the other conditions. So we get one result here. Now first we take in derivatives, first. We're gonna get y prime t equals to negative c1 e to the negative t plus 2c2 e to the 2t minus 0 minus 4e negative 2t minus 6/5 sine 2t plus 2/5 cosine 2t. And now what we're going to do, we're going to use the condition using y prime 0 equal to, we're going to get this equals to negative c1 plus 2c2 minus 4, and then negative 6/5 sine is 0, so that's gone, plus 2/5 cosine 0. Okay, so if you plug in the values, because again this is 0 and this is 1, you're gonna get, if you move negative to the other side, 6 equal negative c1 plus 2c2 plus 2/5. I'm going to call this equation number 4. Now what we can do, we can add them. Once you add them, this is going to cancel out, you get c2. So let's do that. And also, you see this is negative, this is positive, they cancel out also. So that's interesting. So by 1 plus 2, we have 6 equal 3c2. In other words, c2 equal 2. And then you can use one of those equations. So let's say c1, if you use the first equation, c1 equal negative c2 plus 2/5, and we can plug in, so it's negative 2 plus 2/5 equal negative 8/5. So we get the solution. So therefore we have the solution y as negative 8/5 e to the negative t plus 2e to t minus 3 plus 2e negative 2t, and then 3/5 cosine 2t plus 1/5 sine 2t. You can see that none of the terms are 0. That's very interesting. Okay, so that's the solution. So it's just like a writing few terms, but otherwise it's not that difficult. But you want to make sure that you kind of follow the pattern, guess the proper YP term, and then after you get the general solution, so you can see the most lengthiest part was to find C1, C2. Otherwise, the problem was not that difficult. The finding C1, C2 takes time because of a lot of terms. But if I say find a general solution, it won't be a very difficult problem. Okay? Yeah. Let's expect something like that. Good. So the next topic is the variation of parameters, and that's the last one we're going to talk about in this this part of the review. In the next one, we're going to talk about the series solution, Laplace transform, and the system of equations. So the only thing we're going to discuss in this one is the variation of parameters, but that's the easy one because you are allowed to use the formula. So I'm going to discuss the formula and the technique. So let's talk about that. So let's talk about the last topic, the variation of parameters method. So this is 22, the variation of parameters. Variation of parameters method. We know that the undetermined coefficient method only works for 3 cases. So the problem is, what if you have something else? So we can use variation of parameters in those cases. So this is a little bit more powerful than the undetermined coefficient problem. So why we use this one? We use this one to find yp, the particular solution of y double prime plus px y prime plus qxy equal fx. So it's the same problem, but it has to be in this form. So we write that standard form. Okay, if it is not in the standard form, you have to bring it to standard form first. So these are the steps. So let's go with the steps. So the first one, find two linearly independent solutions. Find two linearly independent solutions of the homogeneous equation y double prime plus px y prime plus qxy. So we have to solve this first. So it can be constant coefficient or maybe Cauchy-Euler. So that's the first thing. And then also the px and qx may be, no, need not, maybe constants. Maybe constants. Okay, so that's the first step. You find two solutions. So let them be linearly independent. And let them be y1 and y2. So let's call those two solutions y1 and y2. Those are the solutions of the complementary equation, the homogeneous equation. Now what we're going to do, we're going to guess the solution. So guess, so it's the extension of the reduction order. Guess yp of the form, guess yp of the form yp equal u1 y1 plus u2 y2. So for the non-homogeneous, we have one other term. If you have the homogeneous, it's only u1 y1. But when you have non-homogeneous, we add one more term. So the goal is to find this u1 and u2. So that's the goal. How to find this u1 and u2. So we do a very similar thing. We take the derivatives and plug in to the equation and get two equations to solve for u1 and u2. So you can see where u1 and u2 are unknown functions. Where u1 and u2 are unknown functions. So we need to find those two. Okay, so the goal is to find u1 and u2. So what's going to happen when you plug in? You're going to get. So I will skip the other part. So we're going to end up with these two equations. So we're going to solve the two equations. Solve the two equations. Solve the two equations. Solve the two equations to find u1 and u2. What two equations? These two. It is u1 prime y1 plus u2 prime y2 equals 0. That's one equation. The other equation is u1 prime y1 prime as well plus u2 prime y2 prime equal the function fx. So we can solve these two equations. That's always the case. You're going to end up with these two equations. So the goal is to solve these two equations and find u1 and u2, and then after you find u1 and u2, you're going to plug in there, you get yp. So that's how you find the solution. So let's use this method to solve a problem like that you cannot do using the undetermined coefficient method. So let's see this problem. So example, find the general solution of y double prime plus y equal tan x. So if you have this equation, you cannot do you cannot solve this using undetermined coefficient because tan doesn't work. So the problem, so what we try to do is just try to find the two solutions, two linearly independent solutions of the homogeneous equation. So that we can do very easily. The characteristic equation of y double prime plus y equals 0 is lambda squared plus 1 equals 0. So lambda equal plus or minus I, which you can write as 0 plus or minus I. So thus, using the constant coefficient argument, you don't get the exponential term, you only get the sine cosine terms. So that means yc has the form c1 cosine x plus c2 sine x. Now what we can do, we're going to pick these two functions as y1 and y2. The order doesn't matter. So let y1 equal cosine x and y2 equal sine x. So let's pick those two functions. Now what we can do is, now we're gonna so suppose or assume yp of the form u1 y1 plus u2 y2. In this case it is u1 cosine x plus u2 sine x. Now we can take derivatives. Then from the equations, the two equations, we're going to get u1 prime cosine x plus u2 prime sine x equals 0 as the first equation. The second equation says u1 prime, take the derivative. So once you take the derivative of cosine, it is negative sine, so it is negative sine x plus u2 prime cosine x. We take the derivative, which is equals to whatever on the other side, so in this case tan x. So those are the two equations that we need to solve, 1 and 2. Now we're gonna think of how to solve. We're gonna use the elimination type of argument. You can see you can eliminate u1 term easily. What we can do, we're gonna multiply by the missing term and add them, it's gonna go away. So that's the kind of idea. So let's do that. So simply by, we're gonna multiply the first equation by sine, the second equation by cosine, because those are the missing term. you can multiply these two and add them, so you're going to go away. So by 1 times sine x plus 2 times cosine x. If you do that, when you add them, this is going to go away. On the other side, what will happen? You're going to get u2 prime sine squared x plus u2 prime cosine squared x equal, so the bottom one you multiply by cosine, so it is tan x times cosine x, which is, what is it? Tan means sine, cosine, so sine x, so which is equal to sine x. If you simplify, and here what's going to happen, you can see this is 1, so you're going to get simply u2 prime, this is sine squared x plus cosine squared x, which is equal to sine x, but this is 1, so this implies u2 prime equal sine x. That's all you get. Now what you can do, you take the integral, you get u2. So if you integrate, so u2 is simply the integral of u2 prime dx. So that means you just integrate that, so that is sine x dx, that means negative cosine x, so that is u2. Now by 1 you have u1 prime cosine x plus u2 prime sine x. So if you plug in, you're going to get u1 prime cosine x plus sine x, that's the derivative of negative cosine, times sine x, which is equals to 0, that's how it says. Now if you look at the last equation, the last part, which says that u1 prime is sine squared, so negative sine squared divided by cosine x, that's how you get. Now what we can do, we have to think of how to integrate this one. So what we can do is, we can write the top as cosine squared x minus 1 over cosine x, is you can split as cosine x minus 1 over cosine means secant x. So that means it's very easy to integrate. So u1 is the integral of u1 prime dx. So let's integrate the two separately. So cosine x dx minus the secant x dx, and we know the cosine means the sine x, that's the easy part, and then so we have minus, we know that the secant means natural log secant tan, secant x plus tan x, that's the formula from calc 2. We are going to add c, so calc 2, okay, so that's a formula. You know the secant, integral of secant is ln secant tan, that's a formula. Okay, so now we have that, so that means we can write the solution now. So the yp is simply u1 y1 plus u2 y2, which is equals to cosine x times sine x minus ln secant x plus tan x plus u2. U2 means negative cosine, so it is sine x times negative cosine. Now you can see that this and that get cancelled, so you only get the last term. So that means the yp is negative cosine x ln secant x plus tan x. So the general solution, is y equal yc plus yp, c1 cosine x plus c2 sine x minus cosine x ln secant x plus tan x. Okay. So that is the general solution which has two constants c1 and c2. Good. So that's the kind of idea how to use the variation of parameters method. You're going to write the two equations for u1 and u2, and this use the elimination method to remove one of them and solve for one, and then use one of those equations again to solve for the other one. The variation of parameters also has a formula, so let's discuss that, and you are allowed to use that in an exam. So let's talk about the variation of parameters formula. So formula for variation of parameters. Variation of parameters method. So let's talk about that. Again, the same idea. Let's say two linearly independent solutions, two independent solutions of y double prime plus px y prime plus qx y equals 0 are, let's say, y1 and y2. That's always the first step. We find two linearly independent solutions of the standard equation, and then the particular solution is given by a particular solution of y double prime plus px y prime plus qxy equal fx is given by p equal, it is simply u2 y2 y1 fx over the Wronskian y1 y2, order matters, minus y1 y2 fx over the same Wronskian y1 y2 dx. So you can remember this formula and use when there is a variation of parameters type of problem, because there are a lot of problems that you can use the undetermined coefficient method, but this works. Only problem is whether this integral can be done, because sometimes what happen, this is not going to work. Okay, sometimes it's even difficult. So this is simply the Wronskian. Now you know that why the solution has to be linearly independent, otherwise the Wronskian can be 0. So we want to make sure that it's not equal to 0 because we divide by that. Okay, let's just do one example from that just to see how it works, and then that is the end of the review too. So let's do this problem. So let's say use the variation of parameters method, to find the general solution of this equation, y double prime minus 2y prime plus y equal ex over x to the fourth. You can see that this one you cannot do using the undetermined coefficient method. See the format, because there's something in the denominator, so then you cannot do it. But when you take the derivatives, you're going to powers get more and more and more. So it's not going to work. Okay, so let's use the variation of parameters. So the answer, so first we can look at the characteristic equation, the homogeneous equation. So the characteristic equation of the homogeneous equation is lambda squared minus 2 lambda plus 1 equals 0. The zeros are you can see it is a lambda minus 1 squared, so that means lambda equal 1 1. That's a repeated solution. So thus the YC is C1 plus C2 XEX, or in other words C1EX plus C2 XEX. So that means those two are the Y1 and Y2, the two solutions, Y1, Y2. So take or pick or select Y1 equal EX and Y2 equal XEX as two independent solutions. Independent solutions. Now the Wronskian W Y1 Y2, so Y1 first, Y1 Y2 Y1 prime Y2 prime. So if you plug in, you get EX XEX, that means EX plus XEX. If you multiply through, you get EX times EX plus XEX minus XEX times EX. So you can see this and that get cancelled out. So you get e to the 2x, which is not equal to 0. Perfect. Okay, so that's the Wronskian. Now the solution. So the particular solution is by the formula, it is Yp equal Y2 Y1 fx over the Wronskian Y1 Y2 in that order minus Y1 Y2 fx over W Y1 Y2 in that order. So same thing, no change, with a negative sign in between. So let's plug in. So if you plug in, you're gonna get XEX EX, that's Y1, and then we have EX over x to the 4th power over Wronskian, which is e to the 2x dx minus Y1, that is EX. We have XEX, again EX over x to the 4th over e to the 2x dx, and you can see there are a lot of cancellation going on. This cancels with that, the same thing happens on the other side. So you simply end up getting XEX, the integral of 1 over x to the 4th dx minus EX times the integral of 1 over x to the cube. So these are very easy to integrate. So if you integrate them, you get XEX times x to the negative 3 over negative 3 negative EX times x to the negative 2 over negative 2. If you simplify, you get, what do you get? Negative EX over 3x squared plus ex over 2x squared. If you add them, you get ex over 6x squared. Okay, that's the YP. Now what you do, you write the general solution. So the general solution, y equal the sum of the two, yc plus yp. Yc is what? Which is c1 ex plus c2 xex plus ex over 6x squared. So that is the general solution using the formula. So it's not long, but you need to simplify the integral. This is the end of the review 2. So next we can talk about review. In review 3 we can talk about the series solution, at least 2 examples, and the Laplace transform and the eigenvectors method. This is the part 3 of the final exam review of the differential equation class. In this review, we're going to talk about 3 topics. The first one is the series solution method. We will discuss 2 problems, first order and second order. And then we're going to go to Laplace transform method. So we will go with the definition, and then how to solve a differential equation and the convolution, and the Heaviside function or the Cauchy functions, and then the Dirac delta functions. And then finally we're going to talk about the solving a system of ODE. So we will go through the 3 techniques, the elimination method, and then the Laplace transform method, and the eigenvectors method. So let's start with the series solution method. So it is number 23, the series solution method. Series solution method. So this is a kind of a last resort type of situation, because there are a lot of differential equations you cannot find closed form solutions. So in that case, what we're going to do, we're going to assume a series solution. We assume there's a solution given as a power series, and then we try to find the coefficients of that. And once you know the coefficients, you pretty much know the solution. So that's the kind of idea. So we normally deal with second order differential equation in this course mainly. So we have a equation like this. So ax, let's say y double prime plus bx y prime plus cx y equals 0. So let's say it's a homogeneous equation. So what we're going to do, we're going to assume, so the first step, we're going to assume a solution of the form, y equal sigma n going from 0 to infinity cnxn. So we assume that the solution can be written in this form, and then after we do that, we're going to assumption, and then we can take the derivatives of this one. So we're going to take derivatives. So depending on the differential equation, if it's a first order, you need 1 derivative. If it's a second order, you can need 2 derivatives. So take derivatives. That's the second step, and plug in. So we take the derivatives and plug into the equation, and plug in to the equation. So we can take the derivatives of the series and then plug into the equations. So we have 2 steps. So take the derivative and plug into the equation. Third one is, after you plug into the equation, we try to find a relation between the coefficients. So we can try to find the relation among the coefficients. Okay, so find a relation among coefficients. Okay, find a relation we can say between coefficients. So it will be clear what we mean by that, because sometimes you can express like what we try to do, we can try to find a solution for Cn plus 1 or Cn in terms of other coefficients. Okay, that's a relation. We find a relation between the coefficients, and then what we can do, we can evaluate few coefficients. So after that, we can do find C naught. We can probably have it. So then we're going to find the rest. So we can calculate few, and if possible, that we don't know, if possible, we can say if possible find a formula for Cn or Cn plus 1. Normally Cn plus 1. So we try to find a formula, but that sometimes is impossible. Like, I mean, you can, but it's going to be like very complicated. After that, what we're going to do, we're going to plug in them and then write the solution. And then after we do that, then we can write the solution. Write y, which is sigma n going from 0 to infinity. We're going to plug in here. So Cn xn. So like, so if you look at the expanded versions like that, so we can just plug in for the coefficients, because that's what we found earlier. So we're gonna plug in here. So that's the kind of point. So we do that, and sometimes we can see a pattern and find a closed form solution, but that's not always the case. So find a closed form solution. Again, if possible. So that's not always guaranteed. Okay, these are the kind of steps to do a problem. So let's look at a problem and see how it's gonna work. So we can start with the first order equation. So let's say, so example, find a series solution. Find a series solution. Find a series solution of. Find a series solution of y prime plus 3y equals 0. So we're going to try to kind of find a solution for that. Y prime plus 3y equals 0. Again, we're just going to follow the steps. So the steps are, I'm going to assume y equal a series solution. So y is given as a series. So that's the assumption. We assume that. Now what we can do then, we can take the derivatives. So you can see that when you take the derivatives, the first term is a constant. So when you take the derivative, what will happen? The first term disappear because it's a constant. So that means we can start with y prime, which actually start with n equal 1, because the constant term goes away. So we just take the derivative. So if you take the derivative xn, that means n Cn x, you subtract 1. So that's the derivative. And you can see that the important thing, start with 1, because the constant term disappear. So if you take one more derivative, it's going to start with n equal 2, because now the first term is a constant. So if you take the second derivative, it's going to go away. So that's something we need to remember. Okay, good. Now what we can do, substitute. So we can substitute. So once we substitute, what will happen is y prime plus 3y equals 0. So that means you're going to get y prime. That means n equal 1 to infinity n Cn xn minus 1 plus 3 times y. Y means n going from 0 to infinity Cn xn, which is equal to 0 on the other side. Okay, so we plug in. So that step is over. We plug in. We take the derivatives and then plug in. Now what we're going to do, you can see that we check what terms we're going to get. So for example, let's plug in the first value in the index. So you can see for the first series, the first value is n equals 0. So you plug n equals 0, first value is n equal 1. If you plug n equal 1, you get x to the 1 minus 1 means x to the 0. So you get x to the zeroth power in the first one. Second one, you can see the index value is n equals 0. When you plug in n equals 0, you get x 0. So that means that's a good one. That means you get the exact same number in both. But if you do not get the exact same number, we need to write the uncommon terms first. We can write the uncommon terms and then start writing the common terms. So that's we're going to see in the next example. But here you can see everything start with x here, so everything looks great. Now what we can do, we're going to use the seesaw method. Remember the seesaw method? So we're going to use the seesaw method to reindex. I'm going to write it here. So next what we do, use the seesaw method. So seesaw method to reindex. So what's the seesaw method? It's a method that I introduced, so you can find them in other books. Okay, so you can look at the video about seesaw method. It's there. So what we can do, it's very simple, because you can see in the second sum it is xn. We try to get the xn in the other one as well. How to get xn? You can see to get xn you have to increase the index by 1. So you can increase this one by 1. What we do, we increase inside, decrease outside. That's what we call the seesaw, because it's one goes up, the other goes down. So that's the kind of idea. So it's like a seesaw. So this side goes up, then this side goes down, so that this stays the same. You see that the middle never change, but one goes up, one goes down. So that's the kind of idea here. When one goes up, the other goes down. So that's what we call the seesaw method. So it's very simple. It's going to make the calculation much easier. So if you use that, so outside you can increase by decrease by 1. That means your sigma going to start with 0, because you go down by 1. And inside you can increase everything by 1. That means n become n plus 1, n becomes cn plus 1, x is n minus 1. If you add 1, it becomes xn. Perfect. And then here I'm going to bring the 3 inside. So this is 3cnxn. Now you can see that both have the exact same index, exact same power xn, and exact same index. That means you can combine. So we'll combine them into 1. So we can write this one as sigma n going from 0 to infinity, n plus 1 cn plus 1. I'm not going to write the xn term, leave it. And then from the other one you get 3 cn. Now we can write the common xn outside. So now what this says? This says that the whole series equal to 0. The only way this can happen is this term has to be 0, because there's no other way that the whole series is 0. So that means this implies that this term, the coefficient, is 0. And that's exactly what we need. So let's write that. So we're going to get that n plus 1 cn plus 1 plus 3cn equals 0 for the indexing value. Index values are starting with, you can see 0, 1, 2, like that. So it's always coming from the sigma. Whatever the value, you're going to put it there. Now we can solve for cn plus 1. So cn plus 1 is, if you move to the other side, is negative 3 over n plus 1 times cn. So that is the relation. That is actually the relationship between the coefficients. Okay, so you find a relation. Again, this is only valid for n going from 1 to 3, like that. It's only valid for those. Now what we can do, just calculate few values. Okay, so we can start with this first value, n equals 0. So if n equals 0, you're going to get c1. Let's plug in, just plug in n equals 0. So you're going to get negative 3 1, so it's negative 3 c naught. That's what you get. Now we're going to plug in n equal 1. If you plug in n equal 1, you're going to get c2 is become minus. If you plug n equal 1, you get 3 halves c1. But we already know what is c1. So let's plug in the c1 value. When you plug in the c1 value, what happen is you get negative 3. You multiply by another negative 3. That means negative 3 squared. We leave it like that. And in the bottom, you get 2 c naught. So that's what you get for the second coefficient. And then go with n equal 3. So keep writing and until you see a pattern. So if you apply n equal 3, what happens is still negative 3. If you plug in 3, this become so if when you plug in 1, you get 2. When you plug in, oh, actually, I missed the value. This n equals 2. If n equal 2, then you get that, and then this become 3, C2. Now we know C2, so we can find the C2 value here. So when you plug the C2 value, because C2 comes from the previous step, you can see you get another negative 3. So I'm going to write it like that over 3 times 2 here, C0. So, and then you can see that what happened every time you're going to multiply by the same index like that, you just divide by that. So that term comes extra, that's gonna you add it to the previous one. So that's what you see. So that means if you want to keep going like that, so at the nth step, what's gonna happen? You're gonna get C n. So let's say in minus 1 step. If you go in minus 1 step, you're gonna get Cn equal minus 3 over n. Here it is Cn minus 1. That you can simplify, you can substitute. So what will happen when you substitute like that? You're going to see that it is negative 3. So you can see that when you have 1, it is negative 3, only one of them. When you have 2, there are 2. When you have 3, 3. So that means in this case, you're going to get n of n. In the bottom, you can see that also that number exactly matches the bottom number. So that means in the bottom, you're going to get n times n minus 1 times like that. That's simply the factorial. So times C0. So if you go back, what you have gain is negative. So if you go back and you can fill this now because you see the pattern now. So it is negative 3 squared factorial 2 C0. This become negative 3 cube over factorial 3. Now this is negative 3 to the n over factorial n C0. So that's what you get. So that is the general coefficient. Now what we're going to do, we're going to plug in that in the equation. So we found the coefficient. So let's plug in. So therefore, or then you can see y, which is sigma n going from 0 to infinity, Cn xn. So if you plug in for Cn, you're going to get it is negative 3 to the nth power over factorial n, and then I can write the C0 outside, so xn, I'm going to write the C0 outside. But that's kind of make it simple. So it is equal C0. I write C0 outside, is common. So what is going on here? So you can see this is simply C0 times n going from 0 to infinity. You can write this one as negative 3x to the nth power if you combine. If you now, what is this? So you can see this is simply the Taylor series of e to the negative 3x. So this is simply C0 e to the negative 3x as expected, because we know that this differential equation is one of the 4 fundamental equations. We already know the solution. It is C0 e to the kx. In this case, k is negative 3. That's exactly. So we exactly get that. So if you forgot what I'm writing here, we know this formula. So e to the x is sigma n going from 0 to infinity xn over factorial n. And you can see that's exactly what we have here. Here x is negative 3x. So that means you get negative 3x like that. So this is the solution of the differential equation, and you can see that's not that difficult. After you find the relation, try to evaluate few and see whether you can find a pattern. And if you can find a pattern, you can nicely simplify like that. So yeah, so that's about that. So I'm going to do one more example from a little like a higher, like second order differential equation. So let's do a little complicated one just to see what we can do. But in the exam, the question is going to be reasonable. So you will get a reasonable question. But here I'm going to do like question just to see what's going to happen. Okay, so this is like a 3-term differential equation, 3-term. Good. So let's do that. So the next example, again, find a series solution. Find a series solution of, find a series solution of x minus 1 y double prime minus x y prime plus y equals 0. So that is the differential equation we're going to solve. The same idea, but this is second order. So it doesn't really matter. So but only thing is we need to take two derivatives. So the answer. So we're going to say assume a solution of the form, assume a solution of the form y equal sigma n going from 0 to infinity Cn xn. This step is always the same. Now we take the derivative. As we discussed, once you take the derivative, you can see you can start with n equal 1 because the first term goes away. So you get n Cn xn minus 1. Take one more derivative. So you're going to get the new first term going to go away because that's a constant. So you're going to start with n equal 2. And then you have one more. So it's n minus 1 Cn, no change, x to the n minus 2 now. Okay, so there are two things to focus on, this and that, here this and that. Good, so those are the derivatives. Now what we can do, we can plug it. So substitute into the equation. So substitute into the equation. So if you substitute, what we get? We have x minus 1 as a term, and then y double prime, so that means the sigma n going from 2 to infinity n minus 1 Cn x n minus 2, then minus x, the first derivative, which can start with n going from 1 to infinity, 1 to infinity n Cn x n minus 1 plus y, which is sigma n going from 0 to infinity Cn xn. So we write that. So the next step is we try to bring this inside before we change the index. Okay, we're going to multiply through. So let's multiply through. If you multiply through, what will happen? You can see there's an x term. Once you multiply by x term, inside it's going to be x to the n minus 1. And then there's a minus 1 in front. The minus 1 multiplied by the, so we can start with that. So that means the first term going to be now. That's the highest one, so we're going to go with that. So it is minus sign go inside n minus 1 Cn x n minus 2, because I multiply by the minus 1. And then let's start multiply with x. When you multiply with x, you get it's still n going from 2 to infinity, no changes with the index. n minus 1 Cn x. When you multiply by x, it's become n minus 1 now. Okay, because you multiply by x term. And then from the next one, we can bring the x inside. So if you bring the x inside, it's going to be sigma n going from 1 to infinity n Cn x n. Why? Because you multiply by extra x. So n minus 1 become n. And then the last term, what's the last term? Sigma n going from 0 to infinity Cn xn equal 0. So to get now, so we substitute and bring the x outside x term inside. That's the next one. Now what we're gonna do, we're gonna see what are the starting terms. So that's what we check. So let's check the starting term. If you apply n equal 2, the starting term is x to the 0. If you apply n equal 2, starting term is x to the 1. Okay, so that's slightly different. Again, in the next one, if you apply n equal 1, starting term is x to the 1. The last one, x to the 0. So that means there are uncommon terms, because in the first one, the last one, there's x0 term that is uncommon because the other two series does not have that term. So what we can do, we can write the uncommon terms first. So let's try the two uncommon terms. There's a one uncommon. After that, if you start with the next index, that means n equal 3, you can see that you get x1. In the last one also, if you start with n equal 1, you get x to the 1. And everything have x1, 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 x1 on all four. So that means they have common index. So we only write the uncommon index. So uncommon terms. What are the uncommon terms? You get uncommon term on the first one when you apply n equal 2. So that means it is negative 2, 2 minus 1, c2, x to the 0. So that is the uncommon term. From the last one, for the last term, you also get uncommon term when you apply n equals 0. So we write that. And then what we can do, we're going to write the rest of the terms using the proper index. So in the first one, now you can see that n equal 2 we already plug in. So we plug n equal 3 now. Okay, because the first one we already wrote. So minus n minus 1, cn, x, n minus 2. No change, just the index, just the index. The next term, no change, because it's only for the uncommon term. So no changes here. Yeah, there's a lot of writing. I don't know whether even enough space here. And then I'm going to write here negative. No change because still it is a common term. So we can write n, cn, x to the n. From the last one, it has to start with n equal not 0 but 1 because we already wrote the first term there. So that is what we do next. So we change the indexes only for those uncommon terms. Now what we're going to do, we're going to use the seesaw method now. We're going to reindex now. We're going to reindex and see whether we can bring everything into one common index. That's very easy to do. So let's look at the terms now. You can see we need to bring it to xn if possible. So how to do that? We're going to bring this one up by 1, this one down by 1. So then it's going to be xn, power xn. Here you can see you want to bring this one up by 2. So this one down by 2. And then everything else in xn, so fine. So we only need to change the index of 2, just 2 series. So let's do that. So we're going to get, after we reindex, so we're going to get, so we're going to start with the first one, and then only the first two, and then we have the other two. We can combine them also because you can see the last two you can actually combine them into one. So let's do that. So we're gonna get so we have this now. So we have negative 2 c2 plus c0. We have that, and then we're going to use the seesaw method for reindexing. We're going to bring it down by 1, down by 2, so it's become n equal 1 because we had n equal 3 before, it became 1. Infinity, no change. Now inside you can increase everything by 2, so you add 2. Outside you subtract 2, inside you add 2. Because n become n plus 2, n minus 1 become n plus 1, n become n plus 2, x n minus 1 become xn plus, let's go to the next term. In the next term, we need to bring it down by 1. So it's become n going from 1 to infinity. So you add 1, become n plus 1. And then we have n minus 1 that become n. This is c become n plus 1. And then we have xn minus 1 that become xn. And what we can do with the last two, we can actually combine them into one because you can see they are the same, so we can combine them. So we have so if you want we can just leave it because just to keep the argument. So we have n going from 1 to infinity, n cn xn, and the last term is n going from 0 to not 0, it's again 1 to infinity. So 1 to infinity, we have cn xn equals 0. Now what you notice? You notice that everything has the exact same index, n1, 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 n1. Also everything has the exact same power. So what does that mean? You can combine them. So we can combine them. So let's combine them. So once you combine, you're going to get negative 2C2 plus C0. Now let's combine. Let's write the common index outside. So the common index is n going from 1 to infinity. That's the common index. And let's put those terms together. From the first one, you're going to get negative n plus 2, n plus 1, Cn plus 2. That's the first one. And from the second one, you're going to get plus n plus 1, Cn plus 1. And if you combine the next two, you can see one has a negative NCN, the other one has Cn. So you can see, you can write this one as, if you order the plus sign, it is 1 minus n Cn. You can write it like that. Because one has a negative NCN, the other one has a Cn, so we can write like that, and then write the xn power outside, which is whole thing equals to 0. Now again, if this whole thing equals 0, what we're going to do, we're going to equate the coefficients of each term, each linearly independent term. So you can see that that implies that the first thing implies that is this has to be 0. Other thing is that this term has to be 0. So that's what you get. So let's put those two together. Let's set them equal to 0. So if you set the first one equal to 0, so you're gonna get, you can solve for C2. You can see that the C2 equal 1/2 C0. That's what you get. If you set this equal to 0 and solve for C2, you get that. And from the second one, if you solve for Cn plus 2, so I'm going to solve it here. So if you solve for Cn plus 2, just set this equal to 0 and solve for Cn plus 2. So you're going to get simply n plus 2 equal, you can see n plus 1 term get cancelled from the first two terms. So you get n over n plus 2 Cn plus 1 minus, and then you're going to get n minus 1. I put the minus 1 outside, it's easy. And then we have here, we have n plus 1 over n plus 2. So n plus 1, n plus 2, Cn. So that's what you get, okay? And this is valid for n going from, what is the index value? 1. So starting with 1. So 1, 2, 3. You can see that's the exact same indexing value here. See, that's the starting. Okay, so that's a relation. So that means we know the relation. Though what we can do is we can calculate few. We can start plugging the values and then try to calculate few of the terms. So let's do that. Okay, so after that, after you get the relation, we can start calculating values. So we can start with the first indexing value, n equal 1. If you plug n equal 1, you're going to get C3. So let's plug in. So if I n equal 1, what will happen is a 1, and then over n plus 2, that means 3. Cn plus 1, that means C2 minus. If you apply n equal 1, what will happen? N minus 1 becomes 0. So you get 0 times C1. 0 times C1. That means C1 disappear. 0 times. Okay, so that's what you get. So in other words, now what we're going to do, we're going to substitute C2, because C2 we already know from the previous step. See, C2 equal 1/2 C0. So let's plug in there. Since plug in there, you get 1 over 3, 1 over 2 C0. In other words, you're going to see that later it is factorial 3 C0. Factorial 3 means what? What is factorial 3? Factorial 3 means 3 times 2 times 1. So you're going to see that going to appear here. Okay, but if you don't see it, that's okay. When you write few more terms, you're going to see that. Now let's try to calculate the next term. So we're going to calculate n equal 2. So by n equal 2, this becomes C4. So let's plug n equal 2 in the equation. It's a 2 over, nope, it's a 2 over. So it is 2 over, so when you plug in 2, it becomes 4. C3, actually I don't want to write that large. So it is 2 over, man. So it is 2 over 4 C3, and then minus, if n equal 2, that means for 1 over, what do you get here? When you apply n equal 2 to the equation, you're going to get 3 times 4, so 4 times 3 C2. So that's what you get. Now what we're going to do, we're going to plug into C2 and C3, both of them. So let's plug in. So if you plug in, what do you get? From the first one, you get 2 over 4 C3. What is C3? It is factorial 3 C0 minus 1 over 4 times 3, plug into C2. C2 is 1/2 C0. Now you can see that they have the exact same denominator. That means they have the exact same factorial 4. And then in the top, it is 2 minus 1. 2 minus 1 means 1. So that means it nicely simplifies to factorial 4 C0. That's interesting. Do the same thing. N equal 3. Let's choose one more. Then you can see it's clear. So you're going to get 3 over 5 C4 minus 1 over, if I n equal 3, so it's going to be 5 times 4 C3. So let's plug in here. So you get 3 fifth. C4 means factorial 4 C0 minus 5 4 C3. C3 means factorial 3 C0. The same argument, you can see the denominator is simply factorial 5 now. And the top is 2 minus 1 again. So that means is that right? Yeah, actually there are some typos here. So it is not 2, this is 3, and also this is not 1 anymore. So this is 3, so 3 over 5, and then here it is, you plug n equal 3, this becomes 2. You have 2 divided by 5/4, because n minus 1. And you can see now it's again simplifies very well, same denominator. The top is 3 minus 2, that means 1. So it's going to be 1 over factorial 5 C0. So that means you can guess what's going to happen with for Cn. Cn has to be 1 over n factorial C0. So in general, so that's why. So once you write few terms, you're going to see a pattern. Okay. So try to find the pattern. You just write few terms until you see a pattern. Or if it's a difficult problem, what's going to happen? The problem will ask you to write just the first 5 terms, or like 4 terms, 5 terms, like that, if it's a difficult one. But if it is like this problem, very nice, you can solve them. You can simply go forward and find them. Okay, so it depends on the problem. It's a difficult one, just like few terms is enough. Okay, so let's now, you can see in general. Okay, in general, you can write Cn, which is 1 over factorial n C0, which is valid n going from, so what's the starting value? We can start with n equal 3, so right? Yeah, because we apply n equal 1, but we start with C3, so that means starting with 3, so 3, 4, 5, like that. But we also know that, and we know that C2 is 1/2 C0. See, fortunately, that also the exact same format. So that means we can simply write this one as Cn is factorial 5, factorial n C0 for n going from 2, starting with 2. Not just 3, because it has the exact same format. You see, this is the exact same format. Good. So that means now we know the general form. So let's plug in. Okay. So we can substitute that in the equation. So substitute. So when you substitute, is y, which is C. So let's write the formula. So this is the sigma notation. So we're gonna plug in that. So n going from 0 to infinity, Cn xn, so which is C0 plus C1x plus C2x squared, like that. So let's plug in here. So when you plug in, what do you get? So you're going to get, we like C0, we leave. C1 we don't get from here, so we can leave that. And then starting with C2, we have a formula. So it is 1 over factorial 2x squared, 1 over factorial 3x cubed, like that. Actually, and also we forget the C naught term, so let's write that. So I'm gonna, yeah, you can put that top. So this is C naught. There's a C naught term everywhere. We C naught times. Okay, so you can see. So that is the case. Now what I'm gonna do? You may or may not see a pattern here. The only thing missing here is the C naught term for the x to the first power. So what we're gonna do is we can write like this now. We can write this one as I'm gonna add and subtract that term. So so what we can do, I'm gonna add and subtract. So we can write C1 minus C naught x. That's the first term, x1 term, and from the rest I'm gonna add here the C naught coming here. That's that C naught term. So I'm gonna write the rest. So here we can add the C naught term. So this is a C naught x term. That's the one I add. So this is subtract. I add. So add and subtract. Now write the rest. Just write the rest. So what's the rest? C naught over 2 factorial x squared, C naught over 3 factorial x cubed, like that. And you can see from the rest. So this C1, C naught, it's just a constant. I'm going to say it's a big C1 plus. What's going to happen here? Here we have this C naught term. So you can pull the C naught out. So if you pull the C naught out, it's just like just a term. So what do you get? You get 1 plus x plus 2 factorial x squared plus 3 factorial x cubed plus like that. This is simply the e to the x. So that means you're gonna get this C1 is not the C1. This C1 is simply equal to C1 minus C0. So it's just a number. That number I call C1, the big C1. So we're gonna get C1x plus C0 e to the x. So that is the solution of the differential equation. It's very well simplified, and sometimes this happen, you can do that, but not always. So this is the kind of thing, but in a final exam, this may not be possible unless it is like a short problem. The first problem is okay, but you will get a manageable problem. But this is like pretty long, a little long, unless you can do it really fast. But in exam we don't expect that because you have a lot of things to do. So, but what I'm going to show you how it works. Okay, this is how it works. Sometimes it works very well. So you will get something manageable. Okay, not like this long. So you can look at the problem that you get for exam 1, things like that. Okay, good. So that is the power series method, and you can like do any problem like that. So it's not difficult, but you can see it's like a simple thing. So next we're gonna do is we're gonna talk about Laplace transform method. So let's talk about the Laplace transform method. So it's number 24, the Laplace transform method. Laplace transform method. So this is again a very powerful technique. You can do a lot of problems using this technique, because we know that we get stuck when you try to find the solution with undetermined coefficient method, because there are only three problems that we can do, 3 type of problems that we can do. And then also if you try to do the variation parameters, you get an integral that may be impossible to get the closed form solution. Then we have this new technique, what we call the Laplace transform method. So let's try to look at the definition of Laplace transform. So the definition, let's say you have a function. So for a piecewise continuous and exponential order function, for a piecewise continuous and exponential order. That means it's gonna grow slower than, and an exponential function. That's exponential order functions, or at least at the level of at most at the level of exponential function, linear exponential function. So that's what we call exponential order. It doesn't grow faster than that. So piecewise continuous and exponential order function. Exponential order. Okay, so that means it's slower than e to a k t function, slower than that. Maximum is like that. Exponential order function f. The Laplace transform is defined to be the Laplace transform is defined to be, we can use this notation, curly L, f equal, it is from 0 to infinity e to the minus st ft dt. So you get you integrate with respect to t and the limits going from 0 to infinity. We write this one as fs because once you integrate you get the function of s, so we write it like that. So we use uppercase f for that. So that is the definition of a Laplace transform. Okay, just an improper integral. You learn improper integrals in Calc 2, so we use those ideas. Okay, so let's use the definition to find a Laplace transform. It's just a simple function. So let's say example, find the Laplace transform of, let's say, 2t minus 3. Just use the definition to see how it works. So the Laplace transform of 2t minus 3 is, by the definition, 0 to infinity 2t minus 3 times e to the minus st dt. You can see this is a good candidate for integration by parts. So let's do that. So I'm going to use a regular technique. You can use the DI method, no problem. So if you use a regular technique, u has to be 2t minus 3. dv is negative e to the negative st dt. We take the derivative of this one, so du equal 2 dt. We take the integral of this one as a parameter, is act as a constant. So it is e to the minus st divided by minus s, because you divide by the constant term. That's how you integrate a exponential function. That's a constant, you divide by that. Okay, so we have that. Let's plug in here. So if you plug in, you're gonna get so it's a uv minus vdu. So uv, so it is 2t minus 3, that's a u. V is e to the minus st over minus s, in limit going from infinity to 0. And then so uv minus vdu, minus, but there's a minus sign there, so it's become plus. There's a 2, I'm going to write the 2 outside. So so vdu, so you can see the first product is the top row, that's the integral is the top row, the other one is the bottom row, you can see. So that's the bottom row we get, now we are going to writing. So it's 0 to infinity, the bottom row. So let's try the bottom row, I need some space here. So so let's try the bottom row. What's the bottom row? It is it's with a minus sign, so it becomes plus 2. So we multiply this, so I write s outside, so you only have negative st dt. That's the bottom row. Top row is the integral, bottom row is the second integral here. That's how you remember the integration by parts. Okay, now you can see, let's plug in here. So if you plug in infinity, now there are some problems, because you see that one goes to infinity, one goes to 0, one goes to infinity, because the polynomial goes to infinity, e to the minus st goes to 0. So that means indeterminate situation, so you have to use the L'Hopital's rule. But there is a small result that you can remember. When you try to compare with the exponential function always win. So that means whatever happened to the exponential function, everything happened, the whole thing, the same thing happened to everything. So in this case, exponential part goes to 0. That means the product has to go to 0. So that's the result. when you have an exponential function and a polynomial, exponential function wins. Okay, so the whatever happened to the exponential function, the same thing happened in the product. So that means when you plug in infinity, it's 0. Okay, so you get 0 when you plug in infinity. Now when you plug in 0, because this is the we're going to plug in for t, so when you plug in 0 for t, so you're going to get so t term is gone, so e to the zeros is gone, is 1. So you have 3 over s, but there are 2 negative sign, and also there's a negative sign coming from the, when you subtract, there's another negative sign, that means there are 3 negative signs, so you get negative 3 over s when you plug in 0. Okay, now the next one. Next one, what we can do, you need to integrate that. So if you integrate, what will happen? So you have plus 2 over s. When you integrate, you're going to get one more negative sign. So that means it's going to be 1 over negative s e to the negative st, the limit infinity and 0. The same argument. When you plug in infinity, it is gone. When you plug in 0 for t, so it's 1. With the negative sign, it's become plus. So that means you end up getting 2 over s squared minus 3 over s. So that's what you get when you finish the integral, and you can see that's not that difficult. So this is just use the definition to get this one. Okay, so what's going to happen, we are not going to do that like every time when you get this one we use the table. So let's look at the few common values that you want to remember, and in the exam you will get the table. Okay, so you get a table that you used before. So these are the common ones. So table of Laplace transforms, this you need to remember. I mean, it can help you. Table of Laplace transforms. So so let's write the function and the Laplace transform. So start with 1. Laplace transform 1 is 1 over s. That's very easy to find using the definition. Laplace transform t is 1 over s squared. Those you kind of need to remember. And then we have t to the nth power, which is factorial n divided by s to the n plus 1. And then we have sine omega t, omega is a constant, which is omega divided by s squared plus omega squared. And then we have cosine omega t, which is s divided by s squared plus omega squared. And then we have the et function, e to the minus at. So if you have e to the minus at, it is 1 over s plus a. See the sign change. And then we have the Heaviside function ut minus a, which has e to the minus as over s. Actually, you have to be careful. We dividing the whole thing by s. Okay, so it is e minus a, divide the whole thing by s, not just the minus a's part. And then we have the first shifting theorem. It is e minus at et ft. So if you get et ft, the answer is you just get the Laplace transform of the function. You replace s by s plus a. So again, opposite sign. Okay, opposite sign. So it's a good thing to remember. But in the Heaviside function, the same sign. And then the second shifting theorem, which is u t minus a f t minus a, which is simply e minus as fs. So this is what we call the first shifting theorem, and this is what we call the second shifting. So these are useful when you try to find the Laplace transform and the inverse Laplace transform. So these are the kind of thing that you can remember, because it's not that difficult. If you remember them, it's easy to find those inverse and Laplace transforms. Okay, so And then there are some facts about these linear transforms. The Laplace transforms. One of the big fact is linear. This is a linear operator. Okay, it's a linear operator. What does that mean? If we have a sum like that, if you try to find the Laplace transform of the sum, it is simply the first one plus or minus, it doesn't matter, whatever. The same sign goes here, and then g. So that is the first condition. The second condition is if there is a constant, you can simply pull the constant out. So those two properties gonna make life easier because it just act like as we expected. So let's try to kind of do two problems from that. So let's do this one. Find the Laplace transform of find LF4. The first one is, let's say, if t equal to t minus e to the negative 2t plus sine 3t. So let's try to find the Laplace transform. So LF is it's a 2 times Laplace transform of t is 1 over s squared minus, this is the eat function here, a equal 2, so that means 1 over s plus 2, and this is sine. We know the table is omega over s squared plus omega squared, so it's a 3 over s squared plus omega squared means 9. So that's the answer. I mean, you cannot do much with this, so we leave it like that. Let's do another one. How about this one? Let's say you have ft equal e to the negative 2t sine 3t. So if you have something like that, that's the eat function. So according to that, your answer is, what we can do, we first find the Laplace transform of the major function, the sine 3t. So we can do that first. It is 3 over s squared plus 9. And then what we're going to do, we're going to shift s to s, because we have that's the number, so that means plus 2. Okay, so when you have so remember the format, there's a negative sign here, but we're going to go with the plus sign. So that means it's going to be, you simply replace s with s plus 2. So if you do that, you end up getting 3 over s plus 2. You replace s with s plus 2 squared plus 9. If you want, you can simplify the bottom. That's not a must. If you do that, if you expand and add 1, add 9, you get s squared plus 4s plus 13. So that's what you get. So that's the Laplace transform of that. Okay, so it's not that difficult, but this is how it works. Okay, now let's talk about the inverse Laplace transform. So we're going to define the inverse Laplace transform kind of in a like a interesting way. So inverse Laplace transform. So how we define inverse Laplace transform? We're going to say if the Laplace transform of a function is fs, if and only if, let's go backward and forward. If you take the inverse of fs is the ft, so that's the kind of idea. So you can transform backward. So I mean, that's how we define the inverse transform. That means if you know the Laplace transform, you can simplify the inverse Laplace transform. So let's do like 2 examples just to see how it works. So find the inverse Laplace transform. Let's start with this one. So the first one, inverse Laplace transform of 3 over s plus 2 minus 1 over s minus 1 squared. How we do this? It's already factored. Otherwise, we have to find partial fractions, but it's already given. So this is the linearity. So it is, you're going to take 3 out. So it's L inverse 1 over S plus 2. And here you can take the minus sign out. It is L inverse 1 over S minus 1 square. Okay. Now let's see how we can do it. So the first one is easy. It is 1 over S plus A. That's one of the formula in the table. So that means this is simply 3e to the minus 2t, opposite sign. Okay. That's S 1 over S plus A. Minus, how about the second one? When you want to do the second one, you first need to figure out, it's a shifting version. That's a shifted version. You want to figure out what is the base function here. The base function is 1 over S squared. If the base function is 1 over S squared, we know that 1 over S squared is corresponding to t. So we write t because that's 1 over S squared, because that's the base function. Here the base function is 1 over S squared, you see? And then you shift it. Then the shifting part comes. That means the e term comes. So in this case, the shifting part is e, but it is minus 1. So that means it is plus 1. So it's a plus 1 t. So that's what you get. Okay, so it's simple. So you need to figure out what is the base function. The base function is 1 over S squared. 1 over S squared is corresponding to t. And then you do the shifting. That means you multiply by e to the t. So that's the eat function example. Okay, so what I use here is, I'm going to write it here. So what I use here is, we know that if you have e to the minus at ft, it is simply f s plus a. So that's the one we use. Good. So let's do one more example. How about this one? Let's say L inverse 3 plus 2s over s squared plus 4. So if you get something like that, what we can do, it's not directly something that we know. So what we can do, we can split this. We can split this into 2 fractions. So what are the 2 fractions? You can see that I'm going to take 3 out. L inverse. First one, I'm going to write s squared. So what is missing here? We know that this is very close to the sign, but if the sign, the square root of 4 is missing, that means 2 is missing. So what we do, we multiply and divide by 2. So that's what we do. We're going to multiply and divide. So we're going to multiply here by 2 and then divide here by 2. So that's the first one we do. Plus, because the linear, so things are easy, you take the 2 out. So we write L inverse s over s squared plus 4. So now we know all the both. So the first one is simply 3 have sine 2t. Second one is 2 cosine 2t. So it's very simple. Okay. So but we have to break it into 2, split, and then you can see it's right there. It's simply coming from the table. The next major method is the partial fraction method. So let's discuss that now. So the partial fractions method. Partial fractions method. So if you don't know much about that, there's a video that I did for my Calc 2 class. There, like I explained, like a vast a majority of questions, like in different types. So you can look at that, and there are like shortcuts, a lot of shortcuts to find the coefficients, and I discussed that there. So maybe you can look at that if you have enough time. Okay, yeah, that's the same one I posted earlier also. So let's do a problem like this. So let's say find the inverse Laplace transform of. So find the inverse Laplace transform. Inverse Laplace transform. So like let's say you get like something like this. L inverse 2s plus 3 over s plus Yeah, actually, I'm going to let's slightly change the problem to this one because this can be like a little bit difficult. That's what we can do as a second example. Let's do this one first. S plus 2 over let's say S plus 3 um, and S minus 1, something like that. But this is easy to do. Like if you have linear factors, those are very easy to do. So let's look at how it can work. So we can write the partial fraction decomposition. So S plus 2 over S plus 3, S minus 1 is identical to, we can write the linear factors as A over S minus 1. There's no order, just pick one. S plus 3. And then what we can do, we can multiply the common denominator. So we can write this one as S plus 2 identical to A times the other one plus B times the other one. You see, you get the other denominator. Now what you can do, just substitute. Okay, that's the easiest way to do this. So you can substitute. So you're going to substitute. Let's say you want to find A. So you try to make this term 0. So that means you plug in S equal 1. So you plug in S equal 1. If you do that, you get 3 equal A. 1 plus 4. This says that A equal 3/4. This is S plus 3. So 3/4. And then again we're going to substitute S equal -3 to find the other one. So -3, you're going to get -1 on this side equals the first term is 0 now, and then from the other term B you're going to get -4 because -3 minus a -4. So this says that B equal 1/4. So that's it. So you can find the two fractions, two coefficients. So that means if you go back and substitute A equal 3/4 S minus 1, B is 1/4 S plus 3. Good. So we have those two. Now what we can do, we can find the inverse now. So we can start with the inverse, which is over S plus 2, S plus 3, S minus 1, which is equal by the linearity. What we can do, we can write this as a two separate ones. So it is 3/4 L inverse 1 over S minus 1. That's 1. The other one is 1/4 L inverse 1 over S plus 3. So now what's going to happen? S minus 1. We know the inverse of S minus 1, that is e to the t. So it is 3/4 e to the t plus 1/4 e to the minus 3t. So that's it. So you can see it's very easy to find. Only thing that we need is partial fraction decomposition. So if you know how to do that, everything looks great. Okay, let's do one more little difficult example. So B, let's do the other one that we're trying to do. So let's say we have 2s plus 3 over s plus 1 squared s squared plus 4. So we know how to write the partial fraction decomposition for that. So this is, we can start with 2s plus 3 over s plus 1 squared and then s squared plus 4. This is identical to, so when you have a repeated factor, linear factor, what we can do, we can start with the smallest one and then the next largest. So that's how we do it. And then plus this is s squared plus 4, and we know that B has the exact same format as A when they repeat, but here that's not the case. This is an irreducible factor, so we have write CS plus D. So that's how we write it. Now what we can do is the same thing. So we write 2s plus 3 identical to, write the missing term. Here the missing term of 1 of s plus 1 is missing, s squared plus 4 is missing. Here B only s squared plus 4 is missing. Here cs plus d, you can see s plus 1 squared is missing. Now what we're gonna do, we're gonna always do the substitution first and then the coefficient. That's the easy way to do it. So we're gonna go with the substitution. So we can see that this term is common. So we're gonna substitute s equal -1 to find b. So we substitute s equal -1. If you do that, you get 1 equal 0 plus b. If you plug in -1 squared, that means 1 plus 4. So you're gonna get so you can see you're gonna get b equal and then also this term is 0. So this says that b equal 1/5. So we already find the b value. Now what we can do, you can see that you can plug in anything else and directly find any other values, any other coefficients. So what we're gonna do, we're gonna go with the coefficients. So we always start with the largest coefficient that we discussed several times. So what's the largest coefficient? What's the largest term that you're gonna go with? S. You can see s cube is the largest. So we're gonna go with that. So there's no s cube term here. So that means it is 0. And then you can see you get a s cube term when you multiply these. So that means the coefficient is simply a. The same argument from the next one you are not gonna get one, but from the last one you will again get just s squared s. So that means there's another s cube term, that means c. So those are the coefficients. That means a plus c is 0. That means if you know one, you can find the other one. Now what we can do, we can write an equation for s squared. So what we need is just 3 more equations because we have 3 unknown. We need 3 more equations. I'm gonna go with because you know that all of them related with a. So because of that, because a has like is constant has a, s has a, s squared has a, s cube has a. So I'm gonna go with not s squared. I'm gonna go with s. Okay, coefficient of s. If you go with coefficient of s, it is 2 on this side. On the other side, you're gonna get from the first term, the coefficient of s is 4a from the first one, and then from the second one, there's no term, so that's easy. From the last one, let's expand this one. So if you expand s plus 1 squared, it is s squared plus 2s plus 1. So it's gonna help you to figure out what is the coefficient. So what is the coefficient of s? To get s, one way to get s is you can see you can multiply 1 with cs, so it's a c is a coefficient, and to get another s, you can multiply d with 2s, so that means 2d is a coefficient. Now what we can do, we know that a plus c is 0, so that means you can remove 1 of a plus c from this. So if you remove 1 of a plus c, you only have 3a plus 2d. So that's easier compared to the original one. And then let's go with the constant term. So if you get the constant term, you get 3 on this side. What is the constant here? 4a is a constant. 4b is a constant. And from the last one, you can see d is a constant. So now what we can do is, so we need 2 equations with the same variable. So to get that, what we can do is you can substitute for b in the last one. So if you substitute for b in the last one, what are you gonna get? So you can see if you substitute a b for the last one, you can see the b is 1/5. So it is a 4a. So this says that 4a. This says that 4a plus d, 4a plus d equal 3 minus 4b. But what is 4b? Which is 3 minus 4/5. That means 15 over 11. So that means you're going to get equation 4a plus d equal 11 over 5. Now what we can do is we can solve the last 2 equations. 4a plus 2d and 4a plus d. And if you solve those last two equations, and you can see that you can get a easily, because you can multiply the second one by 2 and then subtract the top one. So if you do that, so okay, again I'm just write the two equations here. So we have 2 equal 4a plus 2d, and here we have 11 fifth equals 3a, not 4a, 3a, and then we have 4a plus d. So what I'm going to do, we can solve these two. I'm going to multiply the second one by 2, and then you're going to subtract the first one. So once you do that, you're going to get 12 over 5th equal is 8a minus 3, 5a. So this is going to give you the a. So a equal 22. A equal, actually, what do you get? 12 over 25. So a equal 12 over 25. That's what you get for a. And then we know c. Because of that, then c is simply minus a. So this is negative 12 over 25. So, and then we can find d from one of those equations. And then we can find d. So I'm going to write the value so you can verify. So this implies that d equal, just plug into one of those equations. So it is d equal 1115 over 4a. So 1115 minus 4a. So this is going to give you the d value, which is 725. Okay. So we find a, b, c, d, all four. Okay, that's the only part like taking time. Otherwise, just the method is easy. So then after we know all four, so then we can write this expression. So we had, I'm going to rewrite this one, 2s plus 3 over s plus 1 squared, s squared plus 4, s squared plus 4 equal, we had 22 over it is 22, or a equal actually 12 over 25. So it is 12 over 25 1 over s plus 1, and then we had b is 1/5 1 over s plus 1 squared, and then we had 11, a negative 12 over 25 c, that's a c value, and the d was 7 over 25 over s squared plus 4, but you can split these two to get not the c, yes, to get a sine and cosine term. Okay, now we have everything we need. So the inverse of this 2s plus 3 over s plus 1 squared, s squared plus 4 equal, so we're going to find the inverse of each term. So that means this is going to give you 12 over 25 L inverse. I'm just writing this one. This is not really necessary, but for completeness I'm writing it. And then 1/5 L inverse 1 over s plus 1 whole thing squared. The next one, what I'm going to split that into two. So we have negative 12 over 25 L inverse. The first one, which is s over s squared plus 4, which is a cosine, plus 7 over 25th L inverse 1 over s squared plus 4. So what we can do, we can multiply by 2 and divide by 2, that we can do. So that means your final answer is simply going to be 12 over 25 e to the negative t plus 1/5 t e to the negative t. That's the second one. How it coming from? Because s plus 1, that means 1 over s square, s plus 1 square, that means 1 over s squared is the term, that means t, and the shifting is e to the negative t. That's a shifting term. And then we have negative 12 over 25, the cosine 2t, and then here what's going to happen is the sine 2 is missing, so you multiply and divide by that, so that means you're going to get 7 over 50 sine 2t. Okay, but this may be like little long to an exam, so you will get something you can manage. This is like little long compared to other problems. Okay, good, but I want to show you like how it works. It's not that difficult. Only problem is the how to find the partial fraction decomposition. Good, that's about that. And then let's talk about how to solve a differential equation using the Laplace transform method. That's the most important one. So solving differential equations using Laplace transforms method. Solving differential equations using the Laplace transforms method. So let's start with the Laplace transform of derivatives. Laplace transform of derivatives. We know these results. So the Laplace transform of the first derivative is s fs minus f0. Laplace transform of the second derivative is s squared fs minus s f0 minus f prime. You can see first term is positive, everything else is negative. That's something you can. So if you write the third derivative, so you can just keep doing it. If you write the third derivative, which is s cube fs minus, the power of s goes down, so that means squared f0 and then s f prime 0 minus s double prime 0. So you can see all the terms after the first terms are negative. So that's something you can remember. Okay, these terms are negative. Okay, and then so you can continue like that. So you can have the general one. So it is a Laplace transform of f to the nth derivative. So the nth derivative is Sn fs minus s to the n minus 1 power f0 minus s to the n minus 2 power f prime 0, like that, and then you're going to be f to the n minus first derivative 0. Okay, so that's the idea. So you can see that except the first term, everything else is negative. So there's a negative sign. Okay, all negative. Only the first one is positive. Good. So now let's see how we can use this to solve a differential equation. So let's do solving differential equations. So let's look at this example. So solve x double prime minus x prime minus 6x equal, let's say, 5 e to the negative 2t, along with x0 equal 1 and x prime 0 equal negative 2. So if you get something like that, so what we normally do is we can take the Laplace transform of the equation. That's how we're trying to do, and then we can use the initial conditions given. So the answer, so let xs equal the Laplace transform of the expected solution, and then what we can do, take the Laplace transform of the equation. So taking Laplace transform of the equation, you're going to get s squared xs minus s x0, these are small one, minus x prime, that's the first term. The second term says minus, there's a minus sign, so let's plug in here. So s xx minus xx. So it's a good idea to write this one to avoid errors, and then minus 6xs equal Laplace transform of that term is a 5, and it's a eat function, so it is s plus 2. So that's what you get. Now what we're going to do, we're going to substitute the conditions that we know. We know that this is this equals to 1, this equals to 1, and this equals to a negative 2. So if you plug in that, then you can bring, so you have a negative s term, you can bring the other side, and we have negative 2, so it becomes positive 2, and positive 1, so it's 3. So we have negative s plus 3, so you can bring it to the other side, take the common, so we have s squared here, and then we have minus s, and then we have negative 6 xs, and you can see this is exactly equal to the characteristic equation, but with the s, not the lambda, but the s. So that happen always. And then now we're gonna bring the other terms to the side, so we have s minus 3 plus 5 over s plus 2. Now what we can do, we can divide by that, and then you can see this we can actually factor. What are the factors of this? The factors are s minus 3 and s plus 2. Those are the factors. So let's divide. So when you divide, what's going to happen? We have s minus 3 here, and then we have s minus 3 s plus 2 plus 5 over, so we have s minus 3, we have s plus 2, and there's another s plus 2 already over there, so that means this can be s plus 2 whole thing is squared. And the interesting thing is sometimes see, this get cancelled, so it simplifies well. So we only need to find one partial fraction, but otherwise what we can do, we can simplify this here. So we normally what we do here is we simplify this. We simplify this before we find the partial fraction, so that it's gonna make the calculation much easier, because it's gonna be an internal calculation. That calculation gonna take care of most of the terms. So it's always a good idea to simplify this first. But here you can see we don't need that because that term cancels, so we have nice one already. So we can separate those two terms. Okay, so so what we have is 1 over s plus 2. So we leave that there because we already know the inverse of that. And we only need to find the partial fraction of this term, s minus 3 s plus 2 whole thing squared. Normally what we do, we're going to simplify this because it's going to make the calculation easy. So let's try to find the partial fraction of that. So now we're going to go with the partial fraction of that. So it's 5 over s minus 3 s plus 2 whole thing squared, which is equal to a over s minus 3 plus b over s plus 2 plus c over s plus 2 squared. So we're gonna and then after that we're gonna get 5 equal a, the missing term is s plus 2 whole thing squared. In the next one, the missing term is one of the s plus 2 is missing, s minus 3 is missing. Last one, only s minus 3 is missing. So we can use a substitution technique now. Always use substitution first. So we can substitute, let's say s equal 3. If you do that, you get 5 equal, you can see plug in 3, this goes away. So you get a. So a, if you plug in 3, this is s equal 3, so it is 3 plus 2 squared plus 0 plus 0. This is going to give you a equal 5 over 25, so 1/5. That's a. Now we're going to substitute. Let's try to find what is the other common term. You can see this is common. See, so that means you can find c. So we're applying a c equal -2. So we're applying a c equal -2. 5 equal is a 0, another 0, and c, if you plug in -2, this is -2, -3. This can give you 5 divided by 5, the c equal -1. Okay, and then so we only need to find one more. What we normally do is equate the coefficients of the largest term. Remember that, okay, because that's going to make the calculation much fast. So coefficient of the largest term. What's the largest term? S squared. So we're going to go with the coefficient of S squared, the largest term. So it is 5 largest degree. So you can see how to get S squared term. The first one getting S squared term, the coefficient is A. In the next one, when you FOIL, you get S squared B. So that's the next one. Since we already know A, we can find B from this one. So this is that B equal 5 minus A. So that means no, actually. So what I did, there's no 0 here. So there was a problem here. So you can see there is no S squared term. So this is 0 on this side. Okay, there's no S squared term. So it's 0. So you get B equal minus C. So since we already know A, so it is -1/5. Sorry for that. Okay, so it's 0 because there's no S squared term on this side. So it's 0. So you get A, B3 like really quickly. Now what we can do, we can substitute that. So that means so is 1 over 5 over S minus 3 S plus 2 squared equal, you can write equal now. It is 1/5 S minus 3 actually let's write the S term. It's not this one because we already know yeah, so let's write the S one. It's very important. So if you write S term, so what do you get? So excess which is 1 over S plus 2 plus the partial fraction of these. Okay, so we're gonna have the partial fraction now. This is 1 over S plus 2 we had already. So let's try the partial fraction here. So it is 1/5 over 1/5 of S minus 1/5 of S minus 3. So we have minus 3. That's A, and then we have B. B is -1/5 over S plus 2, and the C which is -1. So it is -1 over S plus 2 squared. That's what you get, and you can see that you can combine these two. So they're going to simplify. So they're going to simplify. So you're going to get so you're going to get 4/5. So we have 4/5 S plus 2 plus 1/5 S minus 3 minus 1 over S plus 2 squared. So we can find the xt now. So xt is simply, so I just wrote like completely, but some steps you can ignore. Okay, not really necessary. So this is the inverse of this. So we're gonna go term by term. So the first one says it is 1/4 e to the -2t. Next one says 1/5 e to the 3t. The next one is, you can see it is the base function is 1 over S squared, that means it's a t. E to the shifting is -2t. So that is the solution of the differential equation. This one is not that long. It like kind of came quickly. Even like it's not that difficult to find the partial fraction decomposition for that. So these are a kind of good problem, especially for a final exam. Good. Next we can talk about the convolution method. So let's discuss the convolution method. Convolution method. So we know that the Laplace transform is linear. That means if we have a sum, we can write this one as LF plus LG. So we can do that. But if we have a product F times G, this does not equal to the Laplace transform of F times Laplace transform of G. So there's no such result. So instead we have what we call the convolution. So let's say, let's look at the definition. So what we call the convolution product. Convolution product. So the convolution is defined as an integral. So the notation is star. So f star g, that's the convolution of f and g. So which is from 0 to t. What we can do, let's introduce a new variable called tau. So it's f tau g t minus tau. So t is the variable sitting there, and d tau. Or you can even switch the order. So you can say, you can put the t minus tau for the first one, and then g tau for the second one. The interesting part is you get the exact same answer from them. So in other words, this means that this product is so you can switch the two. So that means it is commutative. So you can write it like that. That's what it means. You can switch the order, you still get the same answer. So now the question is, we put t minus tau for the easy one, so that is easy to integrate. So that's how you're going to pick it. So whatever the easy one. So we're going to see when you look at a problem, it will be clear what we mean by easy one. And then we have this major result. So the theorem is that it says, let's say fg are piecewise continuous, continuous and exponential order, and the exponential order and of exponential order. We need that to guarantee that the Laplace transform exists. Then what happened? The Laplace transform of the convolution product f star g is simply the product of the Laplace transform of f and g. So in other words, we write this one as fs times g. This is just the product. So this is the major result. This is very useful. So that's what we have. So if you look at the convolution, Laplace transform of the convolution, you're going to get the product of the Laplace transform. So the benefit is, this is very useful when you want to find the inverse. So that means, so let's try this as a knot. So that means, so if we have an inverse of a product of two transforms, if you know that the two functions, what are the two functions are, just take the convolution. So that's the idea. So this might be much faster compared to partial fraction or other techniques. So that's how we can use it. So useful when finding inverse. Useful when finding inverse Laplace transform. So let's look at that in a problem. So let's try to do this too. So example, find the inverse Laplace transform. Find the inverse Laplace transform. So let's do the first one. Let's say L inverse 1 over s plus 2 times s squared, something like that. So we know how to do this one using partial fraction method. We write the form, find the ABC, because there are three terms now, and then invert. But how to use the convolution? So we know that, so we're going to kind of try to identify. So we can write this one as 1 over s plus 2 times s squared. So we isolate that. Now we can see this function is corresponds to e to the minus 2t. This one corresponds to t. So those are the two functions. And then if you do the Laplace, that's what you get. So that means, according to the theorem, this is simply the convolution between those two functions. So that's the idea. Just take the convolution of those two. So now what we can do, we can use the definition and try to find it. So the question is, which one we're going to put t minus tau. So when you have exponential function, it's always a nice idea to put the t minus tau to the exponential function. So we can do that. So it's 0 to t. E to the negative t, we put t minus tau here for the exponential function. Other one is just become tau d tau. So the reason is, you can see you can pull out e to the negative 2t because that's a constant now. And then 0 to t, e to the negative, not negative, it becomes negative positive because you can see there's a negative. So e to the 2t tau d tau. So this is a very easy integral using partial integrating by parts. So let's do that. So it is e to the negative 2t. Now we can use integrate by parts. So we can use the di method for this one. So let's use the di method, d and I. So we're gonna say for the d we put tau, I we put e to the 2 tau. So take the derivative 1, take the integral 1/2 e to the 2 tau, take the derivative 0. So that means 1/4 e to the 2 tau. And then what we do, we multiply plus minus. So that's what we get. That means the answer is simply we're going to multiply the 2, so it's a 1/2 tau e to the 2 tau, and then minus you get 1/4 e to the 2 tau, and then we can evaluate that. So let's change that. We can evaluate that at t and 0. So that's it. So that's the answer. So what we get? So you're gonna get e to the negative 2t. When you plug in t, so you get 1/2 t e to the 2t, and then minus 1/4 e to the 2t. And then when you plug in 0, the first one is gone, the next one becomes simply 1/4. And then what we do, we will multiply by e to the negative 2t, so you get 1/2 t minus, no, plus. Yeah, so it's going to be plus 1/4 good, 1/4, and then we have no, that's actually, so it is negative because we multiply negative 2t with 2t, so you get negative 1/4, and then the last term going to be plus 1/4 e to the negative 2t. So that's the answer using the convolution method. So it looks like it's a little faster compared to the partial fraction because we just need to evaluate a simple integral here. Good. Good. So let's try to do one more. So let's do this one. So the inverse Laplace transform of 3 over s squared plus 4. So this one, if you do the regular way, it's a little lengthy, but let's see how it's going to be now. So what we can do is we know that if you look at s squared plus 4, that's related to the sign. So what we do, we take 2, we multiply and divide by 2. So this is L inverse. So we're going to arrange it. So 1 over s squared times 2 over s squared plus 4. So we can write it like that. Now you can see this is t, this is related to sine 2t. So we have the two functions. Now what we need is, according to the theory, this simply becomes 3/2, that's there, t convolute with sine 2t. So that's what you get. Now what we can do, we need to find the simple convolution and you get the answer. So that means this is equal to, so we have, again we can use the DI method for that. So the D and the I. So D, first let's write the integral representation is a 2/3, 3/2, 0 to t. I'm going to put t minus tau for the first one and then sine 2 tau d tau. So this one we can use do using the DI method. So t minus tau goes here, sine 2 tau goes, the tau is the variable, so we take the derivative, t is a constant, so you get -1 here, and the other side you get -1/2 cosine 2 tau, and then take one more derivative, 0, so cosine, that means you can divide by 1/2, so it's a -1/4 sine 2 tau, so plus minus, so we can write that now. So you're gonna get, so let's plug in that. So we know the two product here, so let's plug in that. So it is 3/2. The first one is -1/2 t minus tau cosine 2 tau minus 1, so because we have 3 minus sign, so it's minus 1/4 sine 2 tau. We can evaluate that at t and 0. So if you evaluate, if you plug in t, the first term is 0. And then if you plug in 0, so you get t/2. And then from the next one, when you plug in 0, you get 0. When you plug in t, you get -1/4 sine 2t, and then finally if you multiply it through, you get 3/4 t minus 3/8 sine 2t. It looks like simple compared to the partial fraction method, a little lengthy. So like it's up to you, like whether you want to use the convolution or partial fraction method when you get a problem, unless it says that use the convolution. So that's the kind of idea. So how about this one? So how about this Laplace transform? So this is another example. So find the Laplace transform of the integral from 0 to t sine 3 tau d tau. So you can see that this is a convolution problem. What happened? Why you don't see the t minus tau term? Because that's a constant term. So that means it is simply convolute with 1. So that's why you don't see the t minus tau, because you can put the t minus tau to the constant. So that means this is simply the convolution between 1 and sine 3t. So if you do that, 1, so that's a convolution. So actually we need to write it like that. So this is the convolution of, let's write it like this, the convolution between 1 and sine 3t. So by the product, this is the convolution of 1 times the convolution of sine 3t. So if you use convolution, Laplace transform for 1 is 1 over s times 3 over s squared plus 9. So if you write as just one single expression, s times s squared plus 9. So so we can do that. So like sometimes it's not really visible, what is there. Yeah, so that's a good one. And then so we can use convolutions if you want to find the inverse. Okay, so let's put it off inward. So we can say use convolution Not a must, but you can. Okay, use convolution when finding inverse. Finding inverse Laplace transform. So let's go to the next topic. That's the Heaviside function. Heaviside function and switching. So we talk about the switching. When we have a piecewise function, you can use this as a switch. So let's go with the definition of a Heaviside function. Or unit step function. That's the other way. So if you look at the graph, it looks like that. So what's going to happen until 0 is 0, and then at 0 it's going to jump to 1, and it stays at 1. So that is what we normally write as ut at 0. And then we have the shifted version of that. So let's say it's going to jump at a. So until a is 0, and then at 1 at a is going to jump and it stays there. So that is the Heaviside function shifted by a. So it is ut minus a. This is 1 at that point. So that's the function. Good. Now, so the Laplace transform of those. So we have the Laplace transform of the Heaviside function. So Laplace transform. So we have Laplace transform of ut minus a equal e to the minus as over s. So that's one. It's very useful. It's very easy to show this one. Just use the definition. And then we have also second shifting theorem. Second shifting theorem. So what it says that the Laplace transform of ut minus a times ft minus a. So it has the exact same format, t minus a, t minus a. So see that t minus a term and t minus a term. So what's going to happen? This simply become e to the minus as. So they have the exact same format again, minus as times the Laplace transform of s. So that's what we call the second shifting theorem. Now let's try to use this to find the inverse Laplace transform of a certain function. So let's do this one just to see how it works. For example, find the inverse Laplace transform of this one. So L inverse s plus 3 over s squared plus 4 e to the minus 2s, something like that. So let's say you have this one. So it's clear that that is the exact same format that we have the second shifting theorem version. So what we're going to do, we're going to shift this first. So we can write this one as L inverse. We can go with s first. So s over s squared plus 4 e to the minus 2s. And then look at the next one. The next one we have 3, but we actually need 2. So we can do that 3 halves, L inverse, 2, and then we have s squared plus 4 e to the minus 2s, like that. Now we can see this is the cosine 2t, this is the sine 2t. So what we want to do is from that we need to just shift this. So that means the answer is you can shift by 2. So it is ut minus 2, the cosine 2 times t minus 2, plus we have that 3 halves again ut minus 2 sine 2t minus 2. So that is the inverse Laplace transform. So that is how we use that idea. When you have a e to a function like that, it's just a shifting. You just use a second shifting theorem for that. Now let's look at how we use this for switching. So let's do a problem like this. Let's do rewriting a piecewise function using switches. So rewriting a piecewise function rewriting piecewise functions. Okay. So let's look at the idea like a problem like this. So example, so let's say you have a function like this. So let's say rewrite using a Heaviside function. So what we can do, let's say ft. Let's say you have a piecewise function like this, t minus 1 on the interval 0 to 1, and then sine t after that. So if you look at the graph, this is how it looks like. So from 0 to 1, it is a t minus 1. So that's a t minus 1 function. This is going to go with 1, negative 1. And then what happened? It's going to jump to the sine function at 1. So sine 1. Sine 1 is a number somewhere. And then it's going to follow the rest of the sine function. So it's going to go like that. So that's the idea. After 1, it's going to follow the sine function. But until then, it's t minus 1. So these are what we call piecewise function. So this is a nice piecewise function. So the question is how to write this one as a using as a single function using a Heaviside function. So what we can do, we can add a switch here. So you can see we want to switch for the first interval from 0 to 1. The switch on at 0 and then off at 1. So that's what we do. And the next one gonna switch on at 1. So that's the idea. So that means we can write this one as, we're gonna multiply just by the switch. So we have the function t minus 1. We're gonna multiply by the switch. So the switch here is ut minus 1, and then plus, that's the first one. That's gonna switch on only in that interval. The next one is sine t. That's you're gonna switch on after 1. That means you multiply by t minus 1, the function, whatever the function. So sine t. So that's how you write using switches. And if you want, you can even combine them into one function. For example, there's only one ut function. So that means you can write this one as t minus 1 times ut. And then there are t minus 1 function. There's a t minus 1 here. And then also sine t, that's positive. So what we're going to do, we can write this one as plus 1 minus t plus sine t times ut minus 1 as two separate u functions. So that's how you write this using switches. Simple idea. You can switch on at the first node, off at the other node. So that's the off part, that's the on part. Yeah, just pick the two values. So that's the idea. And then after, what you can do, you can use this theorem to proceed with this. So let's just solve one example to see how it works. Probably we can combine this and the convolution in this problem. So let's solve this one. So solving a differential equation, with a piecewise input. Solving a differential equation with a piecewise input, like that. So the example is this. So let's solve this one. Let's say x double prime minus x prime minus 2x equal ft, along with x0 equal 0. and x prime 0 equals 0, just to make things easy. So where, let's say ft equals something like this, 3t 0, t greater than or equal 1 and 0 otherwise. So that means if you look at the graph, this is how it looks like. So what happened until 1, it is 0. At 1, it's exactly start with 3t graph. So that's that. It's going to follow that. So that's the how the ft function look like. At 1, it jump to that, and until then it's 0. Just stay 0. So no input. And all of a sudden, it's going to exert a some input like voltage, current, something like that, which changes linearly. So now what we do, if you get a problem like that, we first use the switches to write it. So you can see you want to switch on at 1. So that means this is simply 3t ut minus 1. That's what happened. 3t times ut minus. This is switch on at 1. So the goal is to use the second shifting theorem, because you're gonna try to use the because there's no other way to do it. You can directly use the theorem like a integral that you can do. You can use the integration and you can integrate this one. That's one way to do it. But if you use the second shifting theorem, you have to write this in t minus a form. So a in this case is 1. So let's do that. So what we're gonna do, we're gonna subtract and add 1. So we write this one like this. There's a trick here. So what we're gonna do, we'll start with t, we're gonna subtract 1 and add 1. And then ut minus 1. Now if you distribute with the first one, you get t minus 1, ut minus 1. In this case, the function is ft. That's the function, ft equal t. And then the other function is simply 3 times ut minus 1. We know the Laplace transform of that. So that's how we find. So we can simply get the two Laplace transform of these two if you write it like that. So that's the point. We write it in this form. Okay. So the answer here, because you're writing ft in this form, so we write it like that. Now we can simply find the Laplace transform. So if this is the case, then the Laplace transform of ft is so it's 3 times the Laplace transform of t minus 1 ut minus 1 plus 3 times the Laplace transform of ut minus 1. And we know that there are formulas for both. So the first one is simply 3 e to the minus s over the function is 1 over s squared. That's the Laplace transform of 1. Why 1? Because that's the function. Plus the second one, it is 3 times e to the minus s. That's the second one. So what we can do now over s actually. So there's s. So now what we can do, take the common denominator. Common denominator is s squared. So we can write this one as 3s plus 3 over s squared e to the minus s. So we can write it like that. Okay, so that's the Laplace transform of the signal, the input function. Now let's take the Laplace transform of the differential equation. So we have the inverse, not the inverse, the Laplace transform. No, yeah. So let's do it like that. So let's say taking the Laplace transform, taking the Laplace transform of the differential equation, we're gonna get s squared sx. There are no initial conditions, so only the sx terms, minus and then minus 2sx. So that's what we have. On the other side is the fs that we already know. So this is s squared minus s minus 2 times sx. On the other side it is 3 s plus 1 over s squared e to the minus s. So what are the factors of this? S minus 2 and s plus 1. So that means when you divide, s plus 1 get cancelled. So you simply get sx. S plus 1 get cancelled, so you get 3 over s squared s minus 2 e to the minus s. So if you have e to the minus x, what we normally do is first try to find the Laplace transform of the rest of the function, and then use the second shifting theorem to transform. So that's what we normally do. So to find the inverse Laplace transform, let's use a convolution now. So we need, let's see, we need the inverse Laplace transform of 3 over s squared s minus 2. So this is L inverse. We're gonna break this 3 over s squared times 1 over s minus 2. So this simply says that it is 3t convolute with e to the 2t. So that's what you get. Now we can use the definition. So 3 times, when you have exponential function, that's where we're going to put the t. So it is 0, t minus tau. So it is tau e to the 2t minus tau d tau. So we did this a lot. So now we know what to do with this. So it is 3e to t, we take it out, 0 to t, tau e negative 2 tau d tau. So that's what you get. And then we can integrate this one using the DI method again. So we have tau e to the negative 2 tau, so 1, 0, 1 half e to the negative 2 tau, and then we need one more, so it is 1/4 e to the negative 2 tau. We multiply these two and multiply those two, plus and a minus. So now we can write the answer here. So this is simply going to be 3 e to the 2t times, let's try the first product, so it is 1 half tau e to the negative 2 tau. Next one is 1 half negative 1/4 e to the negative 2 tau, and then you're going to go with t and 0. So if you plug in the 2, so what happened is, so you have 3e to t. So let's plug in t, so you get 1 half t e negative 2t, and then when you plug in 0 is gone, and from the other one when you plug in t, you get 1/4 e to the negative 2t. When you plug in 0, it's positive 1/4. So that's what you get, and multiply through. So you're gonna multiply by that. So 2t get cancelled because the negative sign. So you get, the first one is negative 3/2 t. Next one is 3/4, and then next one is plus 3/4 e to the 2t. So that is what you get as the inverse Laplace transform. Now what you want to do is you will use the second shifting theorem to shift. Okay, so by the second shifting theorem, so by the second shifting theorem, we have xt, which is the L inverse of 3 over s squared s minus 2 e to the negative s. So that means you're going to shift by -1. So that means everything would be so we get the function first. So this is the function. So we're going to go with the function. You replace t with t minus 1. -3 4, there are no t here. And then 3/4. We have e to t minus 1. And then everything multiplied by the Heaviside function ut minus 1. So that is the final answer for that problem. Yeah. To get the same answer, you can also use the partial fraction method as well. Okay. So you may also use the partial fraction method. Good. So now let's try to go to the last topic of Laplace transform, that's what we call the Dirac delta function. So let's talk about that. So the Dirac delta function impulse response. So the Dirac delta function and impulse response. Response. So let's talk about what's the Dirac delta function. There's the impulse. So like the sudden force acting like a at a single point. That's the kind of idea. So we can write this one as delta t. So like a so it is acting at the 0 point, so it's called delta t. And then we have the shifted version of that. So the shifted version is at a. That's impulse at a. So that's a, and then everywhere else it's 0. So this is what we normally write as delta t minus a. So impulse at a. And then we have the Laplace transform of that. So the Laplace transform, the first one is delta t, that is 1. And then the Laplace transform of the shifted version, delta t minus a, which is e minus as. So this is useful to remember. And if you plug in a equals 0, you get the other one. Good. I mean, that's it. So let's try to see how we can use this to find the inverse Laplace transform. So let's do a problem like this. Find the inverse Laplace transform of, so let's say find the inverse Laplace transform of the first one, L inverse s plus 3 over s plus 1. And you can see that this is not a proper fraction. So if you have improper, this is what we call improper fraction. What you can do is you can do the lone division and find the remainder and the quotient that you can do. Also, you can use some kind of tricks here. So that's much faster. So what we're going to do, we try to create the bottom term in the top. That's the argument. So how we do that? We can write this one as s. We can write this one as s plus 1 plus 2 over s plus 1. Then we can write with this and with the other one. So we're gonna separate this now. So we can write this one as So L inverse s plus 1 over s plus 1 plus 2 over s plus 1. So that means this is simply L inverse 1 plus 2 over s plus 1. We know that the 1, that means a delta function. This is delta 1. It's a delta t. That's 1 plus 2 over s plus 1 means e to the negative 1t, because a equal 1 in this case. So 2 e to the negative t. So that's what you get. So that's how we find the inverse when you have an improper fraction like that. So the delta function comes into play in this case. So let's just do one problem also, another problem like that. So how about this one, L inverse? So let's say s, let's look, s e to the minus 2s plus 3 over s plus 1. So what we can do with this? Again, we can split this. So this one we can write as L inverse. So you can see we have s here. So we can do the same idea. So we can write this one as, we try to create the denominator. So it's plus 1 minus 1. E to the minus 2s plus 3. So this is over s plus 1 over s plus 1. So you can write it like that. Now the same trick. So you can go with s plus 1 with the bottom term. So that means we can write this one as, if you go s plus 1, you simply get e to the minus 2s. If you go with minus sign, you get minus 1 over s plus 1 e to the minus 2s, and then we have this 3s plus 1. Now we go term by term. So the first one is simply delta t minus 2, where a is in this case 2, so it's a t minus 2. The next one is so we had to use the Heaviside function for this one. We find it and then we can transform that. You can see you have to the function is 1 over s plus 1. That means e to the minus t. You replace t by t minus 2 and then multiply by the shifting function as well. So it is e to the minus t. You replace t by t minus 2. So replace t by t minus 2. Multiply by ut minus 2, that's that, and the next one is simply 3e minus t. So that's the kind of idea. So this is how we can do it when you have a term like this. This is special case. So you either get this or you either get that. So it's gonna come with one of those. Good. Now let's try to solve one problem using this method. That's the end of Laplace transform techniques. Let's just do one example. So find the impulse response. Find the impulse response. Find the impulse response of a system. Okay. So for example, let's say, so this is the question. So I'm going to give the exact same wording. Find the impulse response, or simply say solve the differential equation. Find the impulse response of this one, x double prime minus x prime minus x equal, let's say 4 delta t minus 3, something like that. Okay, so where this is coming from, and also with x0 equals 0 and x prime 0 equals 0, just to make things easy. So where this differential equation coming from? So this is a kind of situation. Let's say you have a mass on a table which is connected to a spring with the friction stable. Now what we're going to do, you're going to give a sudden impulse to one direction at the time t equal 3. So you wait, and just give a sudden force in one direction. So that's the kind of situation. So now you get a differential equation like that. So let's try to solve and see what's going to happen. So what we normally do, so just the same procedure. Take the Laplace transform. Take the Laplace transform. So you get s squared sx plus sxs minus xs equal, okay, let's apply the Laplace transform of that. We know that just the e minus whatever the number is 3s. Very simple. Initial condition 0, so you don't get that. So here we have s squared. There's a minus sign. Yeah, this is minus s squared minus s minus 1 times sx equal 4e negative 3s. So sx equal 4e minus 3s over s squared minus x minus 1, and you know that you can see that there are no factors for the bottom function. So what we can do, we can go with the completing square technique. So let's do that. So it is 4e minus 3s. What's the completing square here? So it is s, half of the s term, half of the coefficient s term, that is 1/2. We can square that. So it's going to give you the first two terms, and it also give 1/4. But there's you have to get -1, so that means you subtract 1/4. So if you subtract 1/4, this can be 5/4. So that's what you get. Now this is you can see this, you can invert. So what's gonna happen now is yeah, actually I'm gonna change this to that number. So it's a change this to plus, 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 and a plus, and a plus. So it's simply change to that. Change plus. Just to make things easy. I don't want to make it too complicated. It's already complicated. So now what we can do, we're gonna kind of clear the terms. So you can see this is 1 plus 1 s plus half squared minus. So what is this is a Shin function. This is Shin. We know that that's a form of a hyperbolic sine. So what is missing is square root 5/2. So we're gonna multiply and divide by that. So it's a 4. So we are missing square root 5/2. So we're gonna divide and multiply. Good. So yeah, I didn't write it properly. So what we're gonna do, so we can write this one as s plus 1/2 squared minus 5/4. So square root 5/2 is missing, and then we multiply outside upside down of that. That's what we do. And then we have also e to the minus 3s term. So this is simply the hyperbolic sine, and then we're gonna do the shifting part. So that means the final answer. So we can see, so this simply corresponds to e to the negative 1/2 t sin square root 5/2t. So that's the function coming from there that you know already. Now what we can do, we can use the e to the minus 3s to add a switch here. So taking inverse Laplace transform, taking inverse Laplace. So what we have is xt equal 2 square root 5 ut minus 3 ut minus 3 e to the minus 1/2 t. So what we're gonna do, what's gonna happen, you have to shift by minus 3, so t minus 3 comes there, and then sin square root 5/2. This one also t minus 3. This is because of the e term. This coming from the e term. Good. So that is the answer for this problem. So you can see that it suddenly start at after 3. Then that's when the impulse. So I mean you can see this. That's the whole problem. So this is like a kind of simple problem compared to other problems. Okay. Good. So that is the end of Laplace transform method. Next we're gonna do we can learn how to solve systems. So we can talk about some examples there. In this, we're gonna talk about how to solve system of equations, system of ODEs in this case. So we can talk about 3 methods. The first one is the elimination method. Elimination method. So there are 2 types of problems that we can try. So there are 2 types. We're gonna go one by one. And then the next one is the Laplace transform method. Laplace transform method. So this is actually kind of sophisticated because you can handle a lot of cases with that. And then the third one is the eigenvector method. Eigenvector method. So under the eigenvector method, we're going to consider 2 cases. We can do 2 by 2. 2 by 2 case is very easy. And then we can do 3 by 3. When you do 3 by 3, there are actually 3 cases to consider. One is there are 2 eigenvalue case. That's kind of easy. Very easy to find eigenvectors. We can use shortcut for that. So we will use the shortcut. And then there are 3 eigenvalue case. 3 eigenvalues. Uh, 3 eigenvalues. In that case, what we normally do, we use the eigenmatrices for that. Eigenmatrices. That's the new concept. We discussed that earlier in a different video, so you can look at that. And then there's a case also what we call defective matrices, and we are not going to discuss that in this, but we have that in the in another video. So the defective matrix. Defective matrix, but we will not discuss that here. So we're gonna discuss one from 2 by 2 and one from 3 by 3 with 2 eigenvalues. So that's what we're gonna do. Okay, so let's start one by one. Let's do the elimination first. So the elimination method. Elimination method. So there are 2 types. So let's start with type 1. So let's do that with the problem. So let's say solve the system. Solve the system. So let's say 3 dx over dt minus dy over dt, and on the other side you can see some function of the independent variable. So let's say just put something. So like let's say sine t, and then we have another one dx over dt plus 2 times dy over dt, which is equals to 2e minus t minus 3 let's say cosine 3t plus 1. So what we can do, we're going to call this equation 1 and equation 2 for references. So this is like just like how we do this, like as like when we solve linear systems, like when you have like with several variables, if you see like linear systems, we know how to do. We can just eliminate one variable. So we're going to use the same argument. For example, in this case, you can see when you see plus and minus sign, that's the kind of we're going to pay attention to, because that's going to make it easy. So what we're trying to do is, so in theory, what we do, eliminate one of the x prime or y prime. So that's the kind of goal. So eliminate one of x prime or y prime. For example, when you see plus minus sign, that's we're going to pay attention to that. For example, if you multiply the first equation by 2 and add it to the second one, you can see the dy term going to go like eliminated. So that's what we're trying to do. So we can see by 2 times the equation 1 plus 2. If you do that, if you multiply the first equation by 2 and add it to the second equation, you can see dy term get cancelled. So you're going to get 2 times 3, that means 6, plus 1, so you get 7 dx over dt equal. So you multiply the first one by 2, so that means 2t squared minus, okay, let's look at what's going to happen here. So we're going to multiply this one by 2, so you get negative 16, and you add, there are, in the second equation you also have 2, that means you end up with 14 e to the negative t. And then we have 2 sine t you're going to get. In the bottom you're going to get 3 cosine 3t and then plus 1. So that's what you get. Just a long expression because there are many terms. Just integrate now. Once you integrate, you get x. So x equal the integral of dx over dt. Actually, before we do that, we're gonna divide this. Yeah, let's try that instead. So dx over dt, if you divide by 7, you can see it is 7. It is 2 over 7. 2 over 7 t squared minus 2 e negative t plus 2 7 sine t minus 3 7 cosine 3t plus 1 over 7. So that's what you get. Now what we can do, we're going to integrate the two sides. So just integrate with respect to t, you get x. Okay, so now what we're going to do, integrate. So once you integrate, you get x, which is the integral of dx over dt from calc 1. So just integrate. So we have a lot of terms, so integrate term by term. So we have 2 over 7 t squared. I'm going to write everything, but you can skip this step. It's not really necessary. So it's negative 2 e to the negative t plus 2 over 7 sine t minus 3 over 7 cosine 3t plus 1 over 7 dt. So if you integrate, I'm going to write the answer here. So you're going to get, you have to divide by 3. So it is 2 over 21 t cube minus, okay, when you have exponential function, you divide by the constant. So it's negative 1. So that means it's going to be positive 2 e to the negative t. Sine means negative cosine. So it is negative 2 over 7 cosine t. In the next one, this is a cosine, but there's a 3. That means you have to divide by 3. It's a cosine and sine, so it's a negative 1/7 sine 3t, because you divide by 3, plus 1 over 7 t plus c1. You introduce a constant name. So that is the solution for x. Now what we can do, there are two ways to find y. One way is you can plug in this solution in one of those equations. So if you plug in that solution in one of those equations, you can see that the dx over dt is going to go away, and then you only have dy over dt. Then you integrate that to find y. The other way is just do the same thing as we did before to eliminate the x term, dx over dt term, and then you're going to get dy dt, and just do the same thing. So so I'm going to write this, find dy over dt as before. There are two ways to do it. Okay, so we can use one of the methods. So we can do by 1 minus 3 times 2. Because why we do that? Then you can, because you have a 3 and a 1. So if you multiply the bottom one by negative 3 and add, dx over dt gonna go away. So that's exactly, so we're gonna get -7 because you multiply the top one by bottom one by 3, so you get -6, and there's another one, so you get -7 dy over dt, and then you're gonna get t squared minus 14 e to the negative t plus sine t minus 9 over 7 cosine 3t minus 3. That's what you get. Good. And then what we're going to divide by 7 as before. So you get dy over dt equals -1 over 7 t squared positive 2 e to the negative t negative 1 over 7 sine t, and then it's again negative 9 over so there's a, I don't know whether it's -7 9 or 7, it's just 9, so you have plus 9 here because we multiply, so let's look at that one again. So we have, so we can multiply the bottom by -3, so it becomes positive 9. I don't know why you're right there. Positive 9. Now here is going to be negative 9 over 7 cosine 3t, and then we divide by -7, so it's going to be positive 3 over 7. So that's what we have. And then integrate. Okay, so integrate. So once you integrate, you're going to get the answer. So y equal the integral of y prime dt. So just integrate, so you get negative 1 over 21 t cube, negative 2 e to the negative t, and then sine means negative cosine, so it's been 1 over 7 cosine t, and then negative you divide by 3, so you get 3 over 7 sine 3t plus 3 over 7, you add another constant c2 for that. So those are the two answers. So we have the x and the y. So you can see it's just very direct way to simplify that. So that's a type 1. So let's talk about the type 2. So what is type 2? So type 2. Type 2, like the situation there, we cannot do this. Okay, so let's look at the problem again. So let's say solve the system. Solve the system. Let's say x prime equal 3y, y prime equal 2x minus y plus 3. So that's a system. Sometimes we write the curly brace like that. It's not really necessary. We're going to call the equations 1 and equation 2. Now you can see there's no way you can just solve for 1 here because there are no other derivatives. So that means the method that we used for the previous one doesn't work here. So what you're going to do is you're going to take derivatives. We can take derivatives and then try to substitute from the other one to remove one variable. Now you have two options. You can take the derivative of the first one or take the derivative of the second one. But you can see the 3 here. Since we have the 3 here, to avoid undetermined coefficient method, we can take the derivative of the bottom one. Then that's 3 going to go away. So that's the trick we use here, because if you take the derivative of the top one, you end up with the equation which is undetermined. You have to use the undetermined coefficient method, so that's going to be a little difficult. So we can avoid that, take the derivative of the bottom one. Okay, so we have to think sometimes. So take the derivative of the second equation. So the answer, taking the derivative, of equation number 2. So you're gonna get y double prime equal 2x prime minus y prime, and then plus 0. That's gonna go away. Now what we're gonna substitute for x prime. Okay, so substitute substitute for, let's say substitute 4. substitute for x prime. So if you do that, you get y double prime equal 2 times, what is x prime? X prime is 3y from the first equation minus y prime. Now what we can do, we can bring everything to one side. So it is y double prime plus y prime minus 6y equals 0. This is a simple constant coefficient differential equation, and we write the characteristic equation for that. So the characteristic equation is lambda squared plus lambda minus 6 equals 0, and which has factors lambda plus 3 and lambda minus 2 equals 0. This is gonna say that lambda equal negative 3 and 2, so that means you can write the solution. Okay, so the y is simply using the formula. So y is simply c1 e to the negative 3t plus c2 e to the 2t. So that is the y. Now what we can do in this problem, since we know y, you can, because the goal is to find x. So what we can do is you can plug in that to one of those equations wherever you see y, and then solve for x. So you can see that you can do that in two different ways. The one is you can just substitute for take the derivative, because we already know what is the derivative y prime, and then we can substitute that, take the derivative and plug into the equation number 2, then you get x, or substitute in the 1. In the 1, we know that this y value, substitute there and then integrate again. So we can use that one because that looks little simple. So by 1, we're gonna say x prime equal 3y. So now just plug in for y. So it is 3 times c1 e to the negative 3t plus 3 times c2 e to the 2t. Now what we do? Integrate. Okay, so integrate. So you're going to get x, which is the integral of x prime dt. Just integrate the terms. So that means you can divide by negative 3. So you're going to get, let's write 3c1 times e to the negative 3t. So this step is not really necessary, you can just write the answer directly. And then here the same thing, so 3c2 e to the 2t divided by 2. Now there is a question whether we are going to add another constant, and you can see that this is we have two first order equations. That means you only need two constants. We already have the constants, so that means we are not going to add anything new. Okay, we are not going to add c3 here. So I'm going to write, but I'm going to say we are not going to do that. Okay, because we already have two constants. So that's the reason. We have c1 and c2. We only need two constants. Good. And then we can simplify if you want. So that means the final answer going to be negative c1 e to the negative 3t plus 3 halves c2 e to the 2t. Yeah, that's how we do it. So you can see it's not that difficult, but you have to kind of think before jump, okay? Because which one you take the derivative depend. So can give you like a different answer. I mean, it can be a little lengthy if you take the derivative of the first one, because you have to solve undetermined coefficient problem. Okay, but if you take the derivative of the bottom one, is much easier. So it's always depend on the problem. You can't say beforehand what's going to happen. Okay, let's go to the next next topic, the Laplace transform method. So Laplace transform method. So what we can do, let's again look at a problem. So what we normally do is, so let's discuss the argument. So we can take the Laplace transform of the equation. So because you can see it's a system now, so you can see many equations. So we take the Laplace transform of all the equations. So take Laplace transform of the equations instead of one equation, and solve. And so after you get the equations, you're going to see a system with those xs, ys, things like that. So we're going to solve for them as we did before, okay, and solve for xs, ys, like that, because we don't know how many we have. So solve for them using the elimination method. So you can see, yeah, let's try it. I'm going to say fill up using elimination. Then take the inverse Laplace to find xt, yt, like that. So it's a very simple idea. Take the Laplace transform. So you get a system. In that system, you can see it is just there are no derivatives. We just use the elimination to find them and then take the inverse Laplace. So yeah, so take the Laplace transform, eliminate, and then take the inverse Laplace transform. Those are the steps. So let's just do one problem, but I'm not going to completely solve the problem because those going to be a little lengthy. I'm going to show you the steps and then you can finish this. So let's do this problem. So example, solve the system. Let's say d squared x over dt squared plus 3x minus y equals something, and then let's say we have dy over dt. So this is the interesting part. You can have anything here, not like before. So it is negative 4x plus 2y, some numbers, and then 3e negative t. With the one of the problem here, you need to give the initial conditions because otherwise you can solve. So let's say x0, y, x0, x prime 0, and y0, all of them are 0, just to make it a little bit easier. Okay, so that's the problem. Now what we can do, take the Laplace transform of those two equations. Okay, so answer, taking Laplace transform, we can have, in the first one we can have s squared xs plus 3xs minus ys equal, what's the Laplace transform for? 4 of s. So we will get that equation, and you can see that just xs, there are no derivatives, no other powers. From the second one you're going to get s ys minus 4xs plus 2ys equal 3. This is the it function, so it is s plus 1. Those are two equations that we get. So we can isolate the sx term as a factor. So, and then you can also combine these two. So let's do that. So if you combine them, okay, so combining, let's say combining, we have s squared plus 3sx minus ys equal 4 over s. In the other one you can see negative for sx. It's a good idea to write sx first and then yx next so that you see the pattern. The other one you're going to see s plus 2. Yeah, I'm going to write this a little closer to that. So it is plus s plus 2 ys equal 3 over s plus 1. I'm going to call this equation 1. I'm going to call this equation 2. Now think of how to remove, how to eliminate one of the variables. So for example, you can see, let's try to eliminate the ys. If you want to eliminate ys, think of this term because that's the coefficient. So what we're going to do, we're going to match the coefficient with the opposite sign. So for example, if you multiply the first equation by s plus 2, the whole equation by s plus 2 and add it to the second equation, the ys term gets away. It's going to go away. Okay, if you multiply the first equation by s plus 2 and add it to the second equation, the ys term going to go away, so you can solve for sx. So that's the whole point. So let's do it. So by we can do s plus 2 times equation 1 plus 2. If you do that, you can see the ys term has the same coefficient, so when you add them, same and opposite coefficient, so when you add them, they're going to cancel out. So you simply have s plus 2 times s squared plus 3 minus 4 from the bottom one times sx. That's what you have. On the other side, you have 4 times s plus 2 over s plus 3 times s plus 1. That's what you get. Um, so if you want, you can simplify this in to get one expression, or leave as two. So it's how you want to do it. Now you notice something. You can see that if you simplify the what is in the bracket, you get s3 plus 2s squared plus 3s plus 2, and then which has factors s plus 1 and s squared plus s plus 2. And if you don't know how to do this, look at the other video about factoring polynomials, so that explain how to find factors like this. So now what we can do, we can divide both sides by that, so you're going to get sx. So let's divide both sides. So we have I mean, if you had s plus 2 here, then you can cancel, but it doesn't happen like that. So we get 4 4s plus 8 divided by s plus 1 s squared plus s plus 2, and also we have extra s in front, and plus 3. What's going to happen here? You have s plus 1 already, so it is s plus 2 squared s squared plus s plus 2. Now what we want to do is just invert. So use the try to find factors, the partial fractions, and invert. So you can do either that way, or also you can use the convolution if you want to find inverse. So whatever the method that you use, what you want to do now is the inverting, but I will not do that. I will say, okay, so invert to find xt. And then what do? You can plug in this xt in one of those equations and solve for ys, or do the same thing as before, try to eliminate the sx term by just switching the variables and multiplying the opposite one and adding. So you can use one of those methods to solve for yx and xt. Okay, and then you can say so you can do an invert. Okay, and then the next one is find ys similarly. To do that, substitute xs, because we already know sx in 2, and we can say solve for ys and invert. This is just one way to do it. The other way is just do the elimination as before and solve for ys. So it's sometimes, I mean, it depends on what we have, or use elimination to find ys. So you have two ways to do it. Either you substitute into the other one, because we already know ys, we already know sx, and solve for ys, or just use the elimination to find ys. So it depends. Okay, so that's how you finish the problem. So I'm not going to do it because it can take too much time, but this is the way to do it, because this is very useful when you have like a larger system. So Laplace transform method can help you to find the solution. So we know the method. So let's move on to the last one, that is the eigen vector method. So let's talk about that. So eigenvector method, eigenvector, or you can say eigenvalue method. Okay, eigenvector method. So let's talk about the steps. So we're going to go with the first step. What we're going to do, we're going to write the system using a matrix form. So write the system, in write the system in matrix form. That means x prime equal ax form. That's the first step. And then what we can do, find the eigenvalues. Find eigenvalues lambda I of a. That's the second step. The third step is use any method. Use any method. So you can either use a shortcut that we discussed earlier. So there are several videos for that, for the 2x2 case and 3x3 case. So use the shortcut or the regular method, the Gauss elimination method. Okay, the shortcut or the regular method to find the corresponding eigenvectors, So you can do the shortcut or the regular method. Shortcut is really short. Okay, so and then let's say vi eigenvectors vi is the corresponding vector, and then we write the solution. So write the solution. So we know that the solution is xt, which is given by C1, the V1 E lambda 1 T. So the V1 is the corresponding eigenvector of lambda 1, and then just like that. So we're gonna go V2 E lambda 2 T. So like that. So there are n many. So it is Cn Vn E lambda n T. So there are so not. So lambda i's may be equal, but the vi's v1, v2, vn should be linearly independent. So that's the only requirement we need. Those eigenvectors has to be linearly independent. But there's a fact, this we discussed earlier. The eigenvectors of different eigenvalues are linearly independent always. So eigenvectors of different eigenvalues are linearly independent. That you can show. That's the case. They are linearly independent. But sometimes what happens, even if you have some repeated eigenvalues, you can show that those vectors are linearly independent. In that case, you can still write the solution in this form. Okay, so we can use this form for two cases: the distinct eigenvalues or repeated eigenvalues, but with linearly independent eigenvectors. Okay, so those are the two cases: one with distinct eigenvalues or one with some equal eigenvalues, repeated eigenvalues, but with linearly independent eigenvectors. So if you want, we can kind of repeat that, because that's a kind of important step. So we use this form of the solution when for distinct eigenvalues, or some repeated eigenvalues some repeated eigenvalues with linearly independent eigenvectors v1, v2 through vn. So for those two cases, we can use this form of the solution. So some repeated eigenvalues with linearly independent. This is important one. Linearly independent eigenvectors. Okay, so let's try to do two examples. One from 2 by 2 and another from 3 by 3. So let's start with the 2 by 2 one. So example 1. So let's say use eigenvector method. Use eigenvector method to solve the system. Let's say we have x prime equal 3x plus 4, 3x plus, let's say 3x plus y, and then y prime equal 2x plus 4y. So that's a system. So we can do this using the type 2 elimination method. You can take the derivative and plug in from the other one. You can do that and then eliminate one of the variable. Let's see how to use the eigenvector method. So the answer. So we're gonna let x, which is the vector of x and y, those are the solutions. Then we know that x prime is simply x prime y prime. So we can write the system in this form. So write the system in matrix form. So the next one is write. So I'm gonna write the steps, but you don't want to do that. I mean, it's just guiding you. But in the exam, you don't write those things. So write the system. I mean, you can to make it like more logical. So write the system in matrix form. So we have x prime, the coefficients 3, 1, 2, 4. So those are the coefficients times x. So we just put the coefficient and put x there. Now what we do, we're gonna find the eigenvalues. Okay, so we're gonna so this is A. So I'm gonna call this is A. So we're gonna find the eigenvalues of. So next step, find eigenvalues of A. For that, we can look at the determinant of A minus lambda I. So that is the you subtract the lambda from the diagonal entry. So it is 3 minus lambda, 1, 2, 4 minus lambda. So this is simple. So this is a 2 by 2. So we're going to multiply the diagonal first. So multiply the diagonal and subtract the other diagonal. So minus other diagonal means 2. You set this equal to 0. And you can see that this simplifies to lambda squared minus 7 lambda plus 10 equals 0. This has factors lambda minus 2 and lambda minus 5 equals 0. This implies that lambda equal 2 and 5. So those are the eigenvalues. Okay. So the eigenvalues are lambda equal 2 and 5. Now what we can do, we're going to find the corresponding eigenvectors. So find eigenvectors. Find eigenvectors. For that, we can use a shortcut method. That means eigenvectors are simply the columns of the complementary eigenmatrix, the other eigenmatrix. So remember, the eigenvectors are the columns of non-zero columns of the other eigenmatrix. So we're going to do that. So for lambda equal 2, we're going to calculate the kappa matrix of 5. because that's the other eigenvalue. So that means you subtract 5 from the diagonal, 3 minus 5, 1, 2, 4 minus 5. So you're going to get the columns as negative 2, 2, 1, negative 1. These are the eigenvectors. And you see that they are just a multiple of each other. So that's the eigenvector. So that means this implies that eigenvector for lambda equal 2 are the column. Just pick any column or any multiple. So 1, negative 1. That's the eigenvector. Okay. So you simply pick one of them, or even a scale version of that. So I pick that one. Or you can pick the other one, or you can even multiply by something. Now what we're gonna do, we can do the same thing with the other eigenvalues. So for lambda equal 5, now we're gonna calculate the other one. So we're gonna use 2 here now. So if you use 2, subtract 2. So it is 3 minus 2 and 2, 1, 4 minus 2. So you're gonna get 1, 2, 1, 2. So you can see they are the same, and that's the eigenvector for lambda 5. So which is as eigenvector for lambda equal 5. So which is 1, 2. So we find the eigenvectors. Now what we can do, just use the formula. Okay, so very simple. So the formula. So now write the solution. So we can write the solution. So which is xt equals c1 v e lambda 1 t plus c2 v2 e lambda 2 t. So that means c1 eigenvector of 2 is 1, negative 1. So e2t plus c2 eigenvector of 5 is 1, 2. So it is e to the 5t. So that's the solution. Also, you can simplify if you want, but that's not necessary. I'm just gonna write it in a you may simplify. But that's not necessary. So let's say how to simplify this one, then you can write xt. So what we're going to, we can distribute this. So that means you can first say c1 negative c1 times e to the 2t, and if you multiply by c2, it is c2 to c2 e to the 5t. Now we're going to multiply inside and add. So that means if you multiply inside and add, you're going to get c1 e to the 2t from the first one. From the second one, it is c2 e to the 5t. And here also it is negative c1 e to the 2t plus 2c2 e to the 5t. That means those are the two solutions. So, so therefore, you can say the x solution, that's the first component, which is c1 e to the 2t plus c2 e to the 5t, and the yt, that's the second component. Well, that's how we define the x. So actually this is not simple x, this is the vector x. So this is the big vector. That's a vector solution. Yeah, even here. So that's the vector solution. Good. So it is, and then we have c1 e to the 2t plus 2c2 e to the 5t. So that's the solution. So you can write it like that, or you can just leave the first version. That's fine. Good. So that's how we solve the system of 2 by 2. Now let's try to do one from 3 by 3. So let's solve this one. So example. Yeah, actually, to be better, we're gonna put everything in one side. Okay, and then one more thing. If this is just a note, if initial conditions are given, we can find C1 and C2, because if you know the initial conditions, just plug in them here and solve for C1 and C2. So it's a simple task. Okay, so let's do the 3 by 3 now. So the 3 by 3, let's do just one example just to recall what we did. But there are like four examples solved in the main lecture. So you can look at them if you need more examples. So let's say solve the solve the system of ODEs. So it is dx over dt equal 3x minus y minus z dy over dt, which is x plus y minus z dz over dt, which is x minus y plus z. So what we can do, we can write the system in the matrix form. That's the first step. So the answer, if it is not in the matrix form, write in a matrix form. So so we're going to define the x vector, which has three components, x, y, and z. Now what we're going to writing the system in matrix form. Okay, writing the system in matrix form. So we have x prime equal the coefficients 3, negative 1, negative 1, 1, 1, negative 1, 1, negative 1, 1 times x. That's the system matrix A. Now what we can do, we can find the eigenvalues first. Okay, so find the eigenvalues. Find eigenvalues. So the 0 equal the determinant of A minus lambda I. So that means you subtract the lambda from the diagonal entry. So 3 minus lambda, 1, 1, negative 1, 1 minus lambda, negative 1, and then negative 1, negative 1, 1 minus lambda. So that's what you get. So you can use the Laplace expansion or the cofactor expansion to find get the equation, but sometimes it may be a good idea to use the determinant properties to simplify this first. Like, try to get like more zeros. You can see there are 1, 1, they are equal. So if you subtract them, that means if you add the negative 1 of the other row, you get a 0. So it's always a good idea to get extra zeros, then the calculation going to be easier. So we can do that. So the first thing we're going to do is we notice that there's a 0 here, they are equal, so we're going to get a 0. So we're going to subtract. So what we're going to do is I'm going to add the negative 1 of row 2 to row 1. So let's do that. So if you do that, so that means you subtract row 2 from row 1. So you get 2 minus lambda, and you get lambda minus 2. So they are equal, just opposite sign, and this is 0. So that means you can take the lambda minus 2 as a factor. So that's a good thing. And then here we have 1, and then 1 minus lambda, negative 1, 1, negative 1, 1 minus lambda. So what we did, we want R1 minus R2. Now what we can do is we can pull the lambda minus 2 out as a factor. So if you do that, it is lambda minus 2 as a factor from the first row. So you get minus 1 and then 1, 1, 1, 1 minus lambda minus 1. So we have a 0 here, minus 1, 1 minus lambda. Now what we can do is you can add row 1 or column 1 to column 2 to get another 0. So let's do that. So we're gonna do that. So we're gonna get one more 0 by doing so. I mean, you don't have to do that, but this gonna make the calculation much easier because it's easy to find the factor. So what we're gonna do, we're gonna add column 1 to column 2. So it is negative 1, 1, 1. You get another 0 and 1 minus lambda. No, it's 2 minus lambda because you add that. So this is going to be 2 minus lambda. You add column 1 to column 2. So this becomes 2 minus lambda. This is 0. And then 0 minus 1, 1 minus lambda. So what we did, we add column 1 to column 2. Good. Now we can write the expansion. So once you write the expansion, you can expand at this point, and you can see you only have one term you get. So that means if you write the expansion now, you're going to get it's a negative because negative 1 times lambda minus 2, the 2 by 2 determinant, which is 2 minus 0 minus 1. There's a 0 here, 1 minus lambda. So that means you already get the factored version. So negative lambda minus 2, 2 minus lambda, 1 minus lambda. Okay, so this is simply if you switch a term, this is lambda minus 2 squared, 1 minus lambda. If you set this equal to 0, this says that lambda equal 1 and 2 2. So that's a repetition. So that means there are only two eigenvalues. So this is an easy case because there are only two eigenvalues. What we normally do, we're gonna find the so let's write that two eigenvalues because that's the exaggeration. Two eigenvalues. So what we normally do when you have two eigenvalues, we're gonna multiply the corresponding eigenmatrices. So the find the eigenvectors. Find eigenvectors. So what we do, since there are only two eigenvalues, we're gonna use eigenmatrices. So we can use eigenmatrices for that. So what you're gonna get is, so we're gonna do the eigenmatrix product. So it's one eigenvalue is 1 of A times the other. So we just get the two kappa matrices and we're gonna multiply them. So let's do that. So what is the first eigenvalue? Is 1. So we can subtract 1 from the diagonal. So you're gonna get 2, 1, 1. And then negative 1, you subtract 1, so you get 0, negative 1, and then negative 1, negative 1, and 0. That's the first one. The second one is you're going to subtract 2 from the diagonal. So you get 1, 1, 1, negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Now what we can do, we're going to multiply. We're going to multiply and see what you get. If you get 0, you're lucky. The columns are eigen vectors. So you can see that, for example, if you multiply this row with this column, you're going to get 0. You get 2 minus 1 minus 1, so 0, and you can see that everything is 0. Okay, very good. That means the columns are the eigenvectors of the other eigenvalue. Okay, so that means so these columns, there are three columns here. These columns are the eigen vectors of lambda equal 2, and these are the eigenvectors of lambda equal 1. So it's always the opposite one. Good. So let's try the eigenvectors. So the eigenvectors are for V lambda 1. You can see they are all the same. So it is 1, 1, 1, or just a multiple of that. So you can see that's exactly, you see that there. And for lambda equal 2, we need two eigenvectors. Just pick any column you like. So any column, or even any linear combination or rescaling. For example, I can divide the second column by negative 1, so you get 1, 0, 1. And then if you divide the third column by negative 1, you get 1, 1, 0. Also, there are more things. For example, if you add the column 1 to column 2, you're going to get 1, 1. So that's another one. So you can do a lot of other things. So you can just add them, you can multiply by one something and add them. Okay, just any column operation. So but we need only 3. So, and then you can also see that those 3 are linearly independent. Okay, so they are linearly independent just by observation, because where the 0 is, because when you have a 0 like that, it has to be linearly independent. Okay, so they are linearly independent. Since they are linearly independent, you can have the solution. So the solution vector xt, which is simply c1 v1 e lambda 1 t, c2 v2 e lambda 2 t, c3 v 3e lambda 3t. So if you substitute, you're gonna get C1 times the first one 1 1 1 e to the lambda. What's the lambda value? Is 1, so it's t. And the second one is C2 times 1 0 1. The lambda value is 2t. The third one is C3. The eigenvector is 1 1 0 e to the 2t. So that is the solution of the system. As before, we can, if you want, you can just multiply through and add them and then get 3 equations, but that's not necessary. But this is a solution. Yeah, C1, C2 and C3 are constants. So you can see it's not that difficult, it's very simple. But this is for 2 eigenvalues. If there are 3 eigenvalues, what we normally do is we're gonna pick like if you need the eigenvector for lambda 1, what we can do, we're gonna pick the other 2 eigenmatrices and just multiply them, but we only need one column multiplied by the other matrix. So it's very easy, you can get the answer really fast. You only pick one column, normally with many zeros, so we can multiply that with the other eigenmatrix, so you get the eigenvector. Just keep doing it for other ones. So you pick the other 2 matrices, pick a column, multiply by the other matrix, you get the eigenvector. So just simple multiplication. So that's the end of this review.